myself and gathering information on things that I think are pertinent to what we're talking about. As we all know, our purpose in life on this board is to ensure PNT for all users and to encourage system improvements, new techniques, advancing PNT, again, for all applications. And we've come up with a strategy to protect, toughen, and augment. I don't intend to go through that again because hopefully it's part of the litany that exists within all of our hearts now. But I do want to talk about toughen. This is toughening GPS receivers against the natural and human interference, such as jamming and spoofing, and of course to other system threats. So what is the world we live in today? Well, this is one representative view, and it shows examples of GNSS interference and incidents formally and publicly reported. Our guess is that the number of incidents exceeds this by a factor of at least 10 and perhaps 100. So the point is a signal, which is a tenth of a millionth of a billionth of a watt, can be interfered with. And it is happening, and because of the worldwide dependency, it is extremely important that we worry about it. Mideast and Ukraine areas have been particularly susceptible. Surprise. Why is that? I'll let you speculate on it. But recently, we've had the incident in Denver and the incident in the Dallas-Fort Worth area, which I think brought to our own individual recognitions that it is a problem right here in the United States, and furthermore, in terms of particularly aviation, it's very disruptive. So this is the military likes to do bluffs, bottom line up front. So this is the bluff, and then I'm going to go into some details, not for very long, but just to make them a matter of record. The point is that technology and designs are well known and available to defeat a 1 kilowatt GPS jammer. And I tend to prefer beam steering. Some people like null steering, but the heart of the matter is the controlled reception pattern antenna. And the illustration that we show here is clearly a map centered more or less on Texas, actually centered on Dallas. And if you consider a 1 kilowatt jammer, the vulnerability area is that circle, and the vulnerability range is approximately 550 kilometers, and operating against an untoughened L1 CA run-of-the-mill GPS receiver that is perhaps on an airplane. And the point of what I'm about to say is, let's look at a blown-up map. That is this? Naturally, the pointer does not work. Well, that is Dallas-Fort Worth Airport, and the point of what I am talking about is take that same 1 kilowatt jammer, put them in the center of that small circle there, and that is the effective area of that 1 kilowatt jammer against a receiver which is receiving the new L5 signal. It's integrated with inertial components to allow longer averaging and goes through periods of interruption. And it has a multi-element beam steering antenna. And so in terms of the bottom line, the radius is now reduced to less than 250 meters. And the point is that any reasonable jamming threat is certainly in the United States. Such a capability would make us virtually immune. It would inoculate us to such threats. So let me expand a little bit on the toughen GPS receivers. I'm going to go into a little depth. I apologize because many of you on the board are already well aware of what I'm about to say, but I think it's important we make it a matter of public record. The point is the techniques to do this are well known. They were demonstrated 40 years ago and tested in 1978, and the techniques are very straightforward. The newer signals, the ability to average longer and have greater bandwidths, the deep integration and the use of those multiple antennas. But it's a largely unemphasized strategy, in my opinion. It's being pursued by some manufacturers with some constraints. But the reason for the neglect, and there's certainly, in my opinion, neglect, because for 40 years we haven't made much progress, the perceptions that it's excessively expensive, particularly for retrofitting airplanes, and that perception is real, of course. You could build it into the airplane to begin with, and that would help. The size. In many cases, users are very sensitive to how big the antenna might be or how big the receiver might be. And with that, of course, goes power and other constraints that we normally measure. The availability. The best signal around is L5, but it's not really available yet. It's being broadcast, but there's some issues getting it to the full operational state. But perhaps the biggest constraint, at least in my thinking, is that the federal regulations, the international traffic and arms regulations, have precluded manufacturers from generally manufacturing such CRPAs, controlled reception pattern antennas, if they have more than 3 elements. And frankly, in talking to the CEOs of some of these companies, they say, look, we can't build it because the United States will not allow us to sell it, and puts steep controls on such a thing. But that receiver technology, that toughening, is clearly the quickest route. If you look at other techniques, even augmentations that have lesser capability but might be around, the quickest by far, in my opinion, is to go ahead and allow these improved antennas to function. So what are the key issues? Why would we not do that? And I've highlighted a few. There are probably others, but I think these are the important ones. And of course, what we're trying to do is somehow prevent technology falling into the hands of someone that might be hostile to us. So the first is the theory of phased arrays well known and understood worldwide? The second issue might be, have they been deployed extensively? And how long has that been going on? What about the components that one uses? Are they available and affordable? Are there existence proofs of actually using this in receivers that are for sale, perhaps without the restrictions that we have on ITAR? And based on those answers, 1 through 4, number 5 is, are the restrictions currently in place reasonable and effective against any potential enemy? So I'd like to rapidly go through each of those. Is the theory of phased array antennas well known and understood worldwide? It turns out, in many circles, this gentleman, Vladimir Alexievich Veryukin, is generally considered a father of digital antenna arrays. He is a Ukrainian, Russian, or Soviet professor, and he did his work very early on. If you can see the perhaps you can't quite read it, but he wrote a textbook on this way back in '93. What is that, almost 30 years ago. So the point is, it was well known. But what about how you actually design them? Well, it turns out if you go, one of the go-to programs that all of us in control engineering and estimation engineering use is something called MATLAB, which allows us to manipulate matrices and do, well, for an old professor, wonderful, wonderful things. And one of those wonderful things is they actually have a whole toolbox devoted to phased array design. And the little diagram you show is a colored diagram of a resulting array's antenna pattern and the beam that might be either transmitted or received. It works both ways with such technologies. So the theory, yeah, it's around. What about general knowledge, though? Is that promulgated? Well, it's staggering, the number of articles, technical articles in journals and such. In English, there are literally hundreds of articles on this subject. And as a matter of fact, we have reason to believe that if you go away from just English and you consider Chinese as the language, that in that language there are perhaps almost 1,000 papers on this subject. So any thought that this is somehow an obscure technology has to be put to bed right away. It's well understood. Have they been extensively deployed? That's the second issue. For how long? Well, in my youth, I actually ran search radars back in the old days when we had huge dishes. But right after I left that endeavor, we moved rapidly in this direction. That happens to be an L-band pencil beam phased array antenna that was deployed over 50 years ago. The point is, everyone knows that this works, and as a matter of fact, is heavily deployed. But wait a minute, what about for things that relate to our use, like satellites? Well, you can go online and find such devices as this one. I'm not advertising this company, I don't know anything about them, but the point is, if you go online, you'll find lots of examples of antennas that are either beam or null steering and actually operate in the L-band. In part, they are enabled by the fact that there are components now that do very high-speed analog to digital conversions with lots of precision, 14 bits and more, and they are employed in these devices, and the things that I'm talking about are very inexpensive for sale and generally widely available. Well, but wait a minute, we're talking GNSS. Are there existence proofs of worldwide GNSS AJ receivers for sale? Well, before I address that, I should point this out. Now, back in 1973, when we just got this thing going, it was clear that weak signal was going to be a potential threat to approval of the system, GPS, and we sponsored and encouraged at the Air Force's Avionics Lab a demonstrator. We wanted to say, how good can you be in a high AJ receiver? And I have to mention a guy's name, long dead, Roger Brandt. He threw himself on the railroad tracks to get this accomplished. The program overran badly because we were doing a lot of things that were brand new. They produced this little receiver. That's supposed to be sort of amusing. And today, of course, that little receiver, like everything else, including the receiver in my wristwatch, has shrunk considerably. But the point is, it was built, and the point is, it was tested. Again, I don't have any stock in Rockwell Collins, but they're the ones that did it. And it demonstrated over 50 decibels, a factor of 100,000, over 100,000 of AJ improvement. And the field test showed you could fly directly over a 10-kilowatt jammer and not even see it. The results were forgotten for at least 20 years. I have that on good authority. Mine, because I went totally away from the JPO and then was invited back to be a part of something called the Independent Advisory, IRT. Yeah, the Independent, it was finally stopped. But the point is that what we're talking about here has been known and verified for over 40 years. And again, my plea is to balance the search for GPS replacements with a vigorous, i.e. augmentations, with a vigorous pursuit of toughening. So what about the examples? Well, this happens to be a Turkish company. I think they are TUAL. I've got a couple of brochures from them. It turns out they come to this country. They were at both the recent ION conferences, and they demonstrated what they consider to be the world's smallest anti-jamming solution, kind of a cute little cartoon with the user umbrella and the nasty musician there playing jamming music of some sort. I don't know who invented that. I have met the guy in charge of this, but they are selling 8 elements. ITAR restricts United States manufacturers to 3 or less. They are selling 8 elements already, and the claim that I got, again, you have to be cautious when you talk to a CEO. Sometimes they are inclined to exaggerate slightly, but he says they've sold over 2,500 of these devices, and perhaps even more interesting, he said we're just about to come out with a 16 element, and of course the advantage is narrow beams, deeper nulls, better resistance to jamming. And I'm hoping that some of my friends in various organizations are going to actually buy one of these and see how well it actually does. But the point is, worldwide market, on the market, available right now. And this shows that they don't just have one trick, they have several tricks, and I highlighted the greater than 50 dB. That's greater than a factor of 100,000 of improvement that they are claiming exists. So allegedly, UAVs with 8-element GPS AJ antennas from Turkey are flying in the Middle East somewhere. And the jamming resistance is claimed to be over 10,000 times that allowed by our government for our commercial companies or our commercial aircraft, which, if they were so equipped, would be virtually immune to all the interference, including, by the way, bad word, legato, the L word, including that one. Any concerns would virtually vanish. And one of the concerns or questions that I have, and I assume that our State Department are working hand in glove with us to try to figure all this out, is who in the United States government, or what is the process for looking at this and perhaps coming to a different conclusion. Again, I don't pretend to be an expert on any of that. So let's quantify it slightly. This is a build chart, and it is showing along the left. I'm sorry, my pointer is not working. Definitely isn't working, right? No. Okay, along the left is the radius of a 1 kilowatt jammer. That is the effective radius. And a normal L1CA receiver. This is state 5, normal RTK carrier tracking. This is state 3. Think of it as code tracking, less accurate, perhaps meters rather than centimeters or decimeters. And so what it shows is that 560 kilometers that I just showed you as the effective radius. And then if we were to move back to code tracking, 162. What can we do? We can use the new international signal, L1C, reducing the red and blue bars down by a factor of perhaps 30 or 40%. Or we could go to the brand new signal, the L5, which is the real highlight of what we're doing. And you can see then we have reduced the effective radius for full accuracy to 90 kilometers, and with code tracking to perhaps 22. So that's the story if you don't put in the augmentations we were just talking about. But let's consider beamforming controlled reception pattern antennas and integration with inertial components. The first two bars have now been reduced to the two bars we show here, 5.6 kilometers or perhaps 1.6 kilometers. Did I do something wrong? Oh. Will this actually work, do you think? Oh, okay, thank you very much. So we're down to 5.6 or perhaps 1.6 if we use the L1 signal. But if we go to the L2C, or the superhero of signals for us, the L5, you can see we're down here to on the order of a kilometer effective radius or not. At which point a hostile 1 kilowatt jammer is an exercise in futility. It can't jam enough of an area to justify pumping out a kilowatt of microwave power. And so the point is that this is the payoff, and it is potentially there for commercial users, should that be an appropriate thing to do. And so let me summarize those issues I just said. Is the theory well understood and worldwide? Yes. Have phased arrays been extensively deployed? Yes, for over 50 years. Are the key components affordable? Yes, even more affordable today. Are there existence proofs of actual GNSS receivers that exceed that constraint in the worldwide market today? And the answer is clearly yes. So based on all that, are the restrictions effective at preventing such systems being used by potential enemies? I think you can form your own answer to that question. And I personally hope that we can move rapidly within the United States government to solve whatever bureaucratic constraints and processes are necessary to allow that freedom. So The technology's been known and deployed for at least 45 years. The greater number of elements allows greater immunity to hostile or inadvertent jamming. And for GPS, with deeply integrated inertials, factors of up to 50 dB, 100,000 or more, but the current state of play is we are not allowed to do that. Usually the question that's asked next is, well, okay, what if we don't do anything about it? What if we leave it in place? Well, what we've done is deny the United States civil and commercial users of techniques to mitigate exactly those threats. And here are some of the implications. We tend to focus on aviation. It's because a lot of us fly, I guess. I don't think it's a safety of life issue. I think the FAA has put in place a lot of backups that ensure that the safe landing of airplanes will still occur, but at much less efficiency and with much more disruption. Maritime, though, is another area that is particularly of concern, and in the Middle East we hear many examples of spoofing and jamming that have safety of life or commerce implications. Russ is on the phone, intelligent highways, public safety users, UAVs. So what we're doing is denying a design and cycle of improvement to United States users. Excuse me. So here are my proposed recommendations. Develop a white paper, which is underway, and highlight on the agenda of the next XCOM a request for endorsement and support of removal of all GPS antenna constraints. And in terms of L5, complete the activation of the signal with full data at the user's risk. Incorporate L5 into WAS integrity, and I think that is going on. Is that correct, Karen? So that's what I had to say. Make it a matter of record. And our assessment remains this: no current or foreseeable alternative to GPS can deliver equivalent accuracy, integrity, and worldwide availability. This is not an argument against augmentations. This is simply a recognition of what the state of play is in terms of what satellite navigation does, and perhaps an argument that we reemphasize the toughening of our three strategies, not simply the augmentation. Thank you.
Thanks, Brad.
Mr. Chairman, do you want me to take any questions, or?
Why don't we, one or two, and then I've got a couple of comments we can move on.
Okay.
Any comments or questions from board members? Jeff?
Brad, great briefing. At the end, you said that our next task is to prepare a white paper, and assuming the white paper is embraced and the recommendation therein embraced by this board, it would go to the XCOM, and then the XCOM would call for the adjustments that you're advocating. But who actually is responsible for acting on the XCOM's recommendation if they accept this board's recommendation?
As always, you give very good questions. Yes, as I understand it, the State Department has published a paper that, please, Dad.
Yeah, I should have mentioned this earlier. Because of travel and scheduling and so forth, after lunch at 1:30, we're going to have Jeff Howard back from State in to brief us. For the folks in the room that don't understand the acronym ITAR, it's International Traffic and Arms Regulation. There's a separate set of regulations that are administered by the Department of Commerce. So what we're dealing with are two sets of regulatory schemes from Commerce and State, and we would have to figure out how to actually make that transmittal to them. It wouldn't necessarily be an XCOM issue, although they have a stake in it, and at the recent XCOM meeting, I put up a slide and I raised this issue with them, and they are working it. So we can talk about the pathway forward, but there is a pathway. We just have to make sure we follow who has the responsibility for the regulations. We'll get an update on that this afternoon.
Thank you.
Another question over here, Matt.
Yeah, thanks. Brad, I'm interested in the advantages of using L5. And I guess that raises, I've got a screenshot here of my phone in Brisbane a month ago tracking 7 Galileo E5 channels, 2 GPS and 2 QZSS on L5. So should this be, are you seeing that this should be done as a multi-GNSS solution or a GPS-only solution?
Well, I think the multi-GNSS would fall out of it, but let's recognize the difference between the multiple satellites, which is GDOP, a multiplier of accuracy in the approximation we generally use. Ranging accuracy times GDOP gives you system or navigation accuracy. L5 has a different, it certainly helps, but it doesn't help any more than L1C does. But what L5 does, it gives you a wider bandwidth, more robust signal that has a dataless channel that allows you to average, if you have a really nice inertial, beyond the 50th of a second data bit constraint. So what effectively it does is give you simply a more robust ranging signal if you choose to use it that way. Is that an answer? All right. Is that enough, sir? Thank you very much.
I think we're good. Thanks, Brad. I neglected to add one other administrative comment earlier. This week I received a report of a GPS disruption exercise that was conducted by the Coast Guard New York Harbor back in May.
Mandate and the subcommittee mandate. One of the things that we've been talking about, okay, there we go, is the interesting topic of the value of GPS and the impacts of loss. Really interesting. Many of you may know, for example, there was an RTI study done by the Department of Commerce in 2019, I think it was, found that $1 billion a day would be lost to the American economy if GPS was no longer available. Sounds like a big number, but when you consider the U.S. GDP, that's really, I think it's about 1.7% degradation in gross national product. So it doesn't seem like a real big impact or part of the economy. And we all have a sense that the GPS is essential to so many things. So not sure that that's an accurate reflection. And then so we talked about that. We also talked about on the extreme other end of the spectrum, Greg Milner's book Pinpoint, in which he says, what's the value of GPS? Well, what's the value of oxygen? So a couple real extreme things there. So we've been exploring that idea. We also have been talking about how the government talks about or doesn't talk about GPS disruptions. Brad mentioned these two particular incidents we had this year. Most folks didn't find out about the one in Denver until the ION, or a presentation at the CGSIC in Denver some 8 months later. And most folks that weren't in aviation, it was, at least. And then certainly the Dallas one did hit the news, but we haven't heard a whole lot from the government on either one of these in terms of what happened, what went wrong, how it's not going to happen again, that sort of thing. So we've been, another topic we've been talking about in the committee. We've also been talking about how we talk about, how the government talks about PNT. So is it a cyber capability? Is it an IT capability? Is it electronic warfare if somebody tries to attack and does attack PNT? Is it something else? I mean, words do mean things, and they really impact public and leader understanding. They impact our understanding. So we think it's very important, just from a 50,000 foot level point of view, as to how we talk about PNT and PNT disruption. We also had some input from other folks. As Karen had input's good, right? And they pointed out some points that were, that folks at industry, and in fact some of these individuals had made at the roundtable with, excuse me, the Department of Transportation. And this is a communications issue from our perspective because they said, well, the government's talking the talk, but they're not walking the walk. Excuse me. They're telling us that we should go out and protect ourselves and subscribe to services and use good equipment. We don't see a whole lot of evidence of that, the federal government for doing it. Why should we take it seriously if the federal government's not going to take it seriously? Also had somebody reach out to us about some language in the Federal Radio Navigation Plan. And we have discussed, this is a fairly recent one, so we're still in the process of, well, I think we'll continue to discuss all these things, but we discussed the value, again, of GPS timing, the impact of free-to-use GPS on commercial markets for PNT services, and associated issues. So, and then finally, we've been talking about, well, so we understand it, or we think we understand parts of this whole PNT picture. What about the public? What do they know about PNT and the need for resilience and so forth? Which is a really, yet another really interesting question. So we've been exploring various facets of that. And as you can see, I don't want to give away anything or make any findings at this point, but I think the young lady on the slide pretty much sums up the majority of the public's attitude and understanding of what we have as a primary part of our world. So that is my report. I'd be happy to, that's what we've been talking about. I'm happy to take any questions. Okay, yes, sir.
Okay. Next up is the Education, Science, and Innovation Subcommittee, headed by Dr. Jade Morton. We have a guest presenter. Jade is dialing in remotely. Go ahead, I'm sorry.
Yeah, and Jade sends her apologies. She actually came down with COVID at the weekend, and so has stayed in Boulder rather than coming here. So my name's Terry Moore. I'm the vice chair of this group. So we are the Education and Science Innovation Subcommittee. As you can see, chaired by Jade. I'm vice chair, first vice chair, and Dorota Grainer-Bazinska is the second vice chair. And you can see the other members there, of which a number are in the room, a number are online. Next slide, please. So what is the group going to be doing is looking at the state of education and training in the US related to STEM subjects, and in particular the issues related to the PNT workforce. What are the, obviously, what is the state of that and what are the implications of that, and perhaps what recommendations we could make to try and mitigate some of those problems. But also to look at scientific applications, which are not really considered by any other aspect of this group, scientific applications of PNT that have perhaps unexpected uses of PNT, but also because of that now highlighting unexpected effects of interference and jamming, for example. Next slide, please. So just summarize what we said at the last meeting, which was held, of course, in May. There was this issue related to what's called the crisis in Geodesy, or the Geodesy crisis, from an open letter. I'll refer to a bit more about that in the next slide. That was particularly focused at the issues related to the education and training of geodesists, but obviously that's a key factor within PNT. It's not PNT alone, it is geodesy, but I'll use that as an example of an impact which has been detected, and the start of a mitigation has been put in place. The NSF National Science Board reported on the state of, again, education and training in US science and engineering. I'll give the links there. And this goal stated in that from the board there in terms of growing the leadership role in the United States. Next slide, please. So coming out of last time's meeting, from the discussion that took place in this board in May, then the subcommittee was tasked with following up on a number of those items to provide more of an evidence base. So looking at the sources of research funding and how funding for research in the United States compares with other countries around the world. Looking at the evidence based on publications and where does the US sit, again, with comparative metrics with other nations. Looking at two specific items, one on this geodesy crisis aspect from the NGA, National Geospatial Intelligence Agency, which I'll report on later, and also for myself on work that was being conducted in a similar time frame in 20 and 21 as part of the draft UK PNT strategy work in terms of skills, education, and training, and I'll be reporting on that in the next couple of slides. Next slide, please. So let's look at those first, just some quick slides. So these are, as I've just said, a report, a draft report, which was conducted by a group of representatives from academia, industry, organizations, to try and study the state of skills, education, and training related to PNT in the United Kingdom, and if the UK was to produce a strategy to say what we should be doing about PNT, then what would need to be done in terms of addressing whatever we detected in terms of perhaps a skills gap related to PNT. So that was the group that took place. I must state that anything I show here, which the report sadly has been, is heavily redacted, although I have now provided that report to the group, and I'll give some slides here. None of the recommendations or conclusions are included in that report, so you can actually question the value of it to some extent. The group was led by the Royal Institute of Navigation as an independent learned society. I guess the first thing we did was just state, what do we mean by education, training, and skills? And came up with the definitions that are on the slide there. Education, that learning provision at schools and at universities and other colleges. Training, more dedicated, specific instruction related sometimes to a specific task or higher level through short courses and the like. And skills are sort of the on-work training that takes place, supported by the education and training, but the development of the skills arising from those. Next slide, please. And not surprisingly, we investigated the different levels that might be that level of education and training, from a basic awareness at the bottom of the tree here to an expert at the top of the cone, and the width of that triangle showing the number of people that would need to be instructed, educated, trained, or develop their skills at those different levels. And the contents of the triangle are just indicative areas to try and show what we mean by that. So the high-level R&D, a small group at that level, the use of understanding PNT technology and then applying as we go further down. Oh, we seem to have changed slide. And that's one, okay. And then right down the bottom, just that general user awareness is about of it. So it's not just a matter of saying we need this many experts. The level of education at different depths is required at different levels. So we tried to put a metric on that and say if the UK was to become more active in PNT, develop a strategy, how many people would be required to go through this education and training? And again, the figure is actually in the report. If we move forward, please. So this is a really meaningful slide. So here are the key findings. Well, I guess the main one at the top there is the importance of the close collaboration between industry and academia. There's no point developing courses that aren't needed by people in the industry that are developing systems and technology, and vice versa. If the industry has those needs, then the education sector needs to be responding to those, and that's critical for growth. We looked at the current state of provision of education and highlighted a number of key points, a key factor being there is no PNT or GNSS overall degree course at any university in the United Kingdom at master's level or at undergraduate level. What we found was modules or individual courses within schemes. We also looked at provision of training as well. Again, very ad hoc. There are a number of good examples of where training has taken place, organizations that are providing this, but there's no systematic provision. There is no single provider that provides it in the UK. I'm sorry for the next line, but there are 8 recommendations, but I can't tell you. But there were 2 red flag conclusions, as I call them, really hitting home as the headlines, as Brad put it, just picking out that key headline. 2 absolutely critical situations that are current in the UK that must be addressed. And the actual recommendations were on different timescales. The figure down the bottom, again, heavily redacted, I apologize, shows those 8 recommendations and how they fit in terms of short-term, medium-term, and long-term on the bottom axis, and whether they are strategic or more tactical in the direction of those. And the 8 recommendations are mapped onto that slide there. Carry on, next slide, please. Again, I thought this might be interesting, without saying what the recommendations were, of course, but saying if we look at what's in the United Kingdom called the Regulated Qualifications Framework, it means that you can compare the level of training or education in a university with a high school and at different levels on these 8 different levels on the left-hand side here, going up to PhD at the top and down to school qualifications equivalent of down the bottom here. And you can see, just as an example here, that some of those recommendations are coming in at those different levels, and we're not just targeting at one level. There is a need to address the education related to PNT at all levels, and that's what that slide's trying to show. So let's move on quickly to the next part of it. The next action item was to look at research funding, and these have been produced by Jade, very kindly, these slides. This is actually originally from a Chinese source, but Jade has helpfully translated the Chinese on there, so we've actually got different countries highlighted in terms of the different colors, as you can see. Won't go there through more, but obviously some key factors. We've got the United States as the large blue sector on the right-hand side there. Largest next comparator is China down the bottom. There are numbers on there, but I've got numbers on the next slide, which are probably easier to see. And you can see other countries as well, where it's broken down into some of the smaller slices on the left-hand side. Next slide, please. So now adding some numbers to those. These are the top 14 countries in terms of the level of funding they spend on R&D, and represented as a straight numerical value converted into US dollars, and then the next column as a percentage of GDP. And as you can see, again, the United States at the top of this table in straight numbers there, but close comparison now with a number of other states, and the points we were making that the money you spend in R&D probably buys more things in some countries than it does in others. So although there may be more spent there in the United States, there is probably more value in the amount of money that is spent, for example, in China as the second on the list there. You can see other countries you might expect, United Kingdom down there at sort of 8th on the list, and Australia down to the bottom. And so I just state this is the top 14. We also looked at the EU as a single entity, as a major funding, but that wasn't on these top 14. The next slide, please. So if we put that as a graph, and this just shows how those figures have changed over time from 2000 to 2020 across the bottom axis here, and then the different lines showing as a percentage of GDP for each of those countries. And you can see the trends along the bottom here. We do have a laser. I guess most notable is the historical high investment in the countries such as Israel, the growth in some areas such as South Korea here, and in China in particular. And the blue line across the middle here is the United States as a comparator. And what's striking with this is how this gap, if you like to compare US and China, how the gap is closing. First of all, the rate of growth of this, Sadly, for some countries, it's very flat, like the UK. Some countries, it's even declining, as you can see, in terms of investment. But this gap closing here is one of the most notable findings. Next slide, please. Again, if we look at that in terms of one of the metric might be how many, what is the head count of research staff in government-funded organizations, just as another indicator of investment. And again, only showing a few lines here, very short data we had for China, and then Russia, Germany, Japan, and the lot down, this gray block down the bottom here. We couldn't, or Jade rather, couldn't find comparative data, sadly, for the United States, which I guess was the main impact of this, but again, showing trends in different countries. Next slide, please. And then we looked at publications in terms of technical journal publications, and again, top 12 shown on this slide here, starting at the top with China, and the bottom here with Spain. The number of publications in 2020, and as a comparator metric to compare that with the number of the population of the country, so per capita. And again, you can see perhaps ones you might expect. We have, many of us are aware of the number of publications coming out of China now, but also United States and the United Kingdom as the next values on the table there. Again, all these numbers are, of course, available. If we hit next slide, please. And also what we're seeing as well is a number of countries are launching new journals all the time, but in particular in China, we just take this as a highlight of the changing situation. A new journal of satellite navigation is already being well reviewed. The papers are of high quality in those journals. And also the establishment now of a full Institute of Navigation, if you like, within China. There has always been an Institute of Navigation, but it was mainly maritime-based, but there is now established Institute of Navigation within China as well. So if we move on, please. So if we look at those, I won't show you all of it, there's more in depth that we've been doing, but to try and summarize that, we're basically highlighting that China and other countries are effectively gaining on the investment within the United States in terms of R&D. And in particular, we've seen that in PNT because of the growth of the other systems, so Beidou, Galileo, and QZSS, for example. And our simple belief is that the US needs to expand the funding in education. Oh, sorry, next slide, please. And we'll show some examples on the next couple of slides of potential mechanisms, perhaps. Next slide, please. So we just did a quick study that was led by Penny Axelrad, looking at what sorts of funding schemes are available in US universities. And a whole range of them here from the NGA, and this I'll talk about on the next slide, and you can see the title of the scheme there. Other ones from the Department of Education, National Science Foundation, from NASA themselves, from defense-related ones, and down at SMART, they're related to transportation. I won't go into details of those, but I'll say a couple of words about the first two on that slide there. So there are mechanisms available, potentially, if we can get PNT into those programs for funding. Next slide, please. So the NGA scheme, this was almost a direct result of that Geodesy in Crisis paper that I talked about and discussion. And this is a scheme that has now been run or awarded to the Ohio State University for, as you can see, Geomatics Emerging Scientists Consortium for, I won't read the whole title out, but it's of the order of $30 million or so for a 3-year period and then potential expansion. So we are seeing here, just to use that as one example, again, this is related to Geodesy, but the problem was recognized, it's been adopted, accepted by the NGA, and a measure has already been put in place, which is good news. Next slide, please. This, again, is a general scheme from the Department of Education. I just show this as one idea is that it is available for US students for PhD studies. There's a co-funding aspect of it, and I give the indicative numbers there to the level of support there's been at the moment, which is not huge numbers. Again, this is for any subject area, but the key thing, it is thematic. They set priority areas every few years, and so I guess the challenge here would be to get PNT recognized as one of those priority areas. Okay. Next slide, please. The focus today of this presentation has been mainly on the education side. I say our other role is to consider scientific applications, of which I'm not going to spend much time on, just this single slide. I've given the link to show one example on it as a YouTube video clip. And why do I show that one? You can look at it on your own time. The link is there. I'm not going to show it now. We don't have time. It's about measuring soil moisture using GNSS reflectometry. Okay, so a good scientific application, and the scientist was calibrating her data by looking at, first of all, data over a desert area, where you're expecting, of course, low levels of moisture. But what she found in those repeated attempts over North Africa, in terms of the deserts of North Africa, that around the area of Libya, she was getting very noisy GNSS data to the extent that she couldn't use it. And this, through further investigation, is interference and jamming taking place in Libya, causing now, we talk all the time about the impacts on critical national infrastructure, on transportation and everything else. Here we're seeing where interference is affecting a legitimate scientific investigation. And that's one of the key points we want to draw out of this. So let's not just, when we talk about the protection we talk about for CNA, for GNSS signals, and PNT, we need to think about scientific applications in that same context as well. So I'll leave it there. I'm happy to take any questions. Thank you very much.
Thank you very much, Terry. Next up, we have emerging capabilities, applications, and sectors. And Penny, are you up for this? Thanks. Penny Axelrad.
Sorry, I'm the only one who can't see over this in order to see the slides down there. So I want to acknowledge the the chair of our committee, Frank Van Diggelen, couldn't be here today, and so I'm representing on behalf of the ECAS group. You can see the names of the members there. On the right are the list of topics that our subcommittee intends to study. For this past half year, we focused on the first one, so the High Accuracy and Resilience Service, or HARS. And the other topics, some of the members have been looking at, but today I'm just talking about the first one. Do I switch the slides? Yep. So in terms of HARS, the motivation for it is to make sure that GPS is maintaining a leadership role in the PNT world and in the GNSS in particular. In fact, the National Space Policy calls this out as a requirement, and GPS is certainly in this primary role in a lot of contexts, but in particular, the one that's highlighted here is that GNSS chips, the kinds that go into receivers and phones, even the ones that are made in Europe and Asia, use GPS not as the primary GNSS service, and then they also acquire other signals after that, but the focus has been on GPS. The problem is that GPS is now falling behind Galileo and Beidou. Part of the reason is because they're accelerating, they have less need for backward compatibility. But one of the things that's holding us back from making faster adjustments is the need for backward compatibility and the fact that the satellites have such longevity. Am I missing an important conversation, or it's just, wow, okay. One of the things that has come up is that Galileo, QZSS, Beidou are all providing high accuracy services now in their satellite broadcast signals. It's simply not feasible for GPS to do that, right? It would take a long time for us to implement something like that. Well, it turns out that Galileo, and I think Beidou as well, are also providing corrections and high accuracy services via the internet. And the question we investigated is whether it would be feasible to provide higher accuracy, 1/10 of a meter to meter level improvement in accuracy with GPS and also greater resilience. Is there a way we can do this within the existing GPS structure? And the answer is yes. So we've been talking about the possibility and what it would take to implement some kind of GPS high accuracy and resilience service. Bringing innovation to GPS, we believe, can't wait for a full replenishment of the GPS constellation, and Brad already talked about this morning the need for more L5 and how long it takes to get there. But there's an alternative for some capability to use a flexible delivery mechanism to implement some changes more rapidly. There is a requirement when you do something like this for the user equipment to have separate connectivity in order to get these corrections. And I think, when GPS was first envisioned, there was, the idea of being able to navigate without access to anything was extremely important because we didn't have the internet out there and everybody wasn't walking around with a computer in their pocket. And so today, the idea of having constant access to the internet is like having constant access to air, right? It's just what we expect. So this is no longer a severe limitation. Being able to provide additional data to users through the internet would also allow us to get around and provide additional information beyond, not subject to the GPS 50 bit per second data rate, and also wouldn't impose the requirement on backward compatibility. So what we've been investigating is the possibility for GPS high accuracy and resilience service to leverage existing capabilities of US government organizations in order to do the things that need to be done. In particular, to compute corrections for GPS satellite orbits and clocks, which are one of the main limitations of the current accuracy, and to provide improved models for ionospheric and tropospheric effects. These things are well established, it turns out, and there are already existing capabilities to do this. We heard from JPL about the GD-GPS service, which is doing many of these calculations and has the ability to implement these kinds of estimates. So we've tried to figure out how you could provide initial performance at the less than a meter level, or about a meter level, with flexibility for such a high accuracy system to continue to improve and enhance service for users. So here's a picture of the kind of content that would be transmitted to users potentially in such a service. So the first one is the state space correction, so the satellite orbit, clock, and differential code biases. Ionospheric corrections for single frequency users who don't necessarily have access yet to L5 or for power reasons are not using multiple frequencies, potentially tropospheric corrections. JPL presentations have showed that the GD-GPS capability is already gathering the required observation data and is already generating high accuracy products that are compatible with something like this. The other thing that we've looked at is the idea of providing the raw navigation data bits to users via the internet. So if you are providing navigation data bits via the internet, it would allow users to authenticate the transmitted signals. They could compare those signals, those data bits that they receive over the internet to the ones they get from space, and by that, confirm that the signal that they're tracking is what they think it is. And alternatively, it also provides flexibility for tracking under more challenging signal conditions. I'll talk about that on a different slide. And this piece of HARS would require the navigation data to be provided somehow by the GPS operations or extracted from the other data sets that are being used for the state space corrections. An important question, of course, is how do you ensure secure delivery of the data? And so here we have a diagram that Frank put together that describes the different components of it. Data encryption and delivery is provided through existing methods that are well established. There's some more information on this on the next slide. What's useful to look at about this picture is that every piece of this block diagram of these elements actually exists with the exception of the dotted box, which is the actual distribution, right? So the distribution of high accuracy services to GPS users doesn't exist yet, But that's the piece that needs to be identified of who would actually implement that, where it would happen and how it would be done. But the service would provide GPS users with higher accuracy and security of their signals than they currently experience. A little bit more about the data distribution over the internet and how it helps user resilience. So providing the encrypted nav data over the internet would free receivers from their entire reliance on open data service. So they have ways of checking it, they would have ways of getting that data if it wasn't available directly. It's very compatible to the distribution of assisted GPS to today's cell phones, and cryptographic means can be used for authentication of the data that's received. Secure connections are well-known, well-developed techniques for this. In particular, users could access the information via a VPN-type connection that you would use when you're connecting to the internet, let's say from a hotel room or something like that. Additional commercial services could also be developed for enhanced security beyond what's being provided via this potential HARS service. And then finally, at the bottom is the idea of pre-broadcasting raw navigation data, enabling receivers to compare what they receive directly from the satellites with what they get over the internet as a way of potentially improving the resilience of a receiver, or allowing a receiver to operate in a very energy-efficient snapshot mode, or to use longer coherent integration times for challenging signal environments. That's it. Any questions?
I guess rhetorically, and we've had this conversation before, who would you send this recommendation to?
Well, we're not making a recommendation, right? This is a,
In the event that we decide to, I'm just rhetorically,
yeah.
who gets this?
Well, the
And
interesting,
it's not for you to answer, Penny. But go ahead and make it.
I was gonna speculate. I guess what I was gonna say is the thing that why we really like this idea, and one of the things that came out in the discussions and the fact finding was the fact that it can be done in a way that's not impacting the satellites. It doesn't require any change to the satellite at all. And the impact even on the control segment would be minimal in terms of passing along the navigation data. And the fact that these capabilities exist and they have an excellent route to improvement, is really exciting. So the fact that all these tools are sitting there just waiting for us to figure out how to knit them together seems like a recommendation could just naturally arise from, but there are services that do distribution of data, right? That's also not a new thing.
Penny,
Questions, comments?
this is Jade, and can you hear me?
Thanks, Penny. Great brief.
Can anybody hear me? This is Jade.
Next up, international engagement, and our brilliant Aussie, Matt Higgins.
Thank you, Mr. Chair. So yeah, I'm here to present on behalf of the International Engagement Subcommittee. We met yesterday in person, which was good. And I'll just run through the typical sort of slides as introduction, the members of the group. Unfortunately, our vice chair from Brazil had to step down from the board, so our second vice chair, but we're still powering on. As I commented last meeting, we have a nice mix of non-US citizens to sort of give an international perspective, and also some US members, which is good for getting a reality check on what the US needs, as opposed to some ideas that some crazy Australian might come up with. The study areas that were, or a crazy Croatian or a crazy Englishman. So, the study areas we were identified are these. We've basically been concentrating on that question, which goes to that, is GPS still the gold standard discussion? Looking at what other GNSS services are providing and any gaps or synergies that there might be. Where do I point this? So you may recall from the last board meeting, we put up a couple of tables where we suggested some system capabilities that other systems have, and also some service capabilities. So we've been developing a series of fact sheets on these, assessing the characteristics of other GNSS that are not currently available on GPS, or that perhaps where GPS could be improved. And so these are the sort of areas we looked at in terms of system capability. Some satellites, some systems like Beidou, for example, have geo satellites directly in the system. Obviously, in the case of the US, you have WAS, so that probably would not do anything for the US case. Some of the systems have those inclined geosynchronous orbits, such as QZSS, the figure 8 type orbits, that give you extra satellites at that longitude band. And in the case of QZSS, for example, was designed to be deliberately high in the sky to get more satellites in urban canyons. One low-hanging fruit that Jade has identified is to improve the broadcast INO model from GPS. Other things are being considered. Galileo 2, for example, is talking about configurable payloads, software-defined radios. Several of the systems are either have implemented or will implement inter-satellite links. There is ground segment coverage things. So, for example, Galileo has more uplink stations around the world, and therefore the age of data problem is better with Galileo than currently with GPS. And then, of course, there's developments in improved satellite clocks, and again, Galileo's clocks are probably the state of the art at the moment. Can you, next slide? I can't get this to work. Thanks. So these are some of the service capabilities. Search and rescue, obviously GPS does have some satellites that have the MEO-SAR type implementation, but for example, Galileo is now introducing a downlink that tells the user that their beacon has been received, which is extremely important. In Australia, for example, people think they're going to be rescued, they give up and they wander off into the desert and die. Whereas if there was a return link, it says, we've got your beacon, say where you are, we're coming. So it's quite powerful. Both Galileo and QZSS are talking about emergency warning services and developing them, which takes advantage of the ubiquity of the GNSS chip in a smartphone. So that, for example, if the entire mobile phone network is wiped out by a cyclone or a tsunami or whatever, you can get an emergency warning still to the phone through the GNSS chip. Beidou has short messaging services. That's probably not something you'd want to necessarily do on a GNSS, I think, in the case of the US. There is a high accuracy service, which we've deliberately steered clear of because, as Penny just presented, is being done in the ECAS subcommittee. Another area is open authentication. So the Galileo Open Navigation Message Authentication Service, for example, and also Galileo talking about a higher level of that as a commercial authentication service. So next slide, please. So this is just an example. We have filled out 4 of the fact sheets. This is one that I put up because it's reasonably short and fits on the slide. But we are trying to do these at about a 1-page type fact sheet. So inter-satellite links, for example, we talk about a description of the problem, the advantages. So in this case, it can be deployed as radio or optical comms links, and the inter-satellite communication improves the timeliness of orbit and health information. You can also do inter-satellite ranging, which improves orbit accuracy. The German Space Agency is working on a follow-on to Galileo in a Kepler project where they're also talking about a real-time ensemble of the clocks, which reduces your satellite clock offsets and satellite clock errors because all of the satellites are synchronizing themselves permanently all the time through their optical comms links. That's a bit of a generation away, but it's very interesting. So then there's questions like, well, would that be valuable for GPS? And for example, it would enable increased performance and accuracy with decreased reliance on ground infrastructure. Is it planned for GPS? We're unsure at this stage. And that's one part of getting these fact sheets out there, whether we need to discuss with government what is actually planned. And then another thing, so for example, I talked about SMS that Beidou has implemented. It probably doesn't make sense to do that on GPS, but what you would probably do, given that this is about the system itself, obviously you consider that for future GPS. And we deliberately I took our draft recommendation out because I think we need to discuss how we want to do these fact sheets and handle them. So next slide, please. So progress, we've drafted a number. So actually, I say the first two lines there, we discussed yesterday that before considering or recommending or even analysing the use of GEOs or IGSOs, we probably should also have a discussion about LEO PNT, which we are later today. So you'd consider that as a future discussion. Improved broadcast ionospheric model. Jade has drafted a fact sheet on that, which is basically proposing the fact that the Klobuchar, I can never pronounce that, the model currently used as the broadcast model for GPS. There are newer ways of doing that are available. And Renato's going to look a bit more into, there's also work around using machine learning to improve that. I've done the draft on the intersatellite links that I mentioned. Configurable payloads we will be doing in the next few months, and improved satellite clocks. I think Todd was going to take that on. So we'll work through these. The ground segment coverage one is kind of linked to intersatellite links, pardon the link. But that needs to be discussed a bit more. Next slide, please. Next slide. Sorry. Oh, back one. Okay. Back one or back two? Sorry. Forward. Forward. Yes. Right. I didn't change that. I should have changed that from system capability to service capability, sorry. But these are the other service capabilities I mentioned, and we have drafts on emergency warning service and open authentication that we've done. And then we have some others to be done, and as I mentioned, the high accuracy service we're steering clear of because ECAS is working on that. So next slide, please. An important additional discussion I think that's worth saying is, obviously we discussed in general how we might progress this, what we should do with this fact-finding, but that's for discussion tomorrow in the board as well. Our meeting was also attended by some US government representatives, so Rick Hamilton, Coast Guard, Jeff Albach from State, and Chris Erickson from Space Force, which turned out to be extremely useful. Because one of the things that's concerned me all along is if we just have these closed steering committees, we make some recommendation and it goes across down to government and they go, we're already doing that, or we've already considered that. It'd be good to head those off at the pass, so to speak, by having the likes of Jeff in the room and others. So that I've discussed that with Barbara. I should have mentioned Barbara is our designated federal officer. And we think that it would be good to include them, and they're quite interested in being involved in our meetings going forward. So I think that's really good. An example of that is, for example, Jeff Albach, who's speaking later, is also heavily involved from State Department in the UN International Committee on GNSS. So if we wanted to discuss something in this subcommittee that's already being discussed or being progressed in the UN ICG, then we should be aware of that and we should think about that. So, as I said, we intend to continue to include those US government reps where we can. Next slide, please. So my final slide is just on next steps. We need to finish those draft fact sheets, which we'll do in the next few months, and aim to have them available for the next board meeting. We need discussion from the wider board on the best way to progress these findings. So, for example, do we have an individual recommendation on each fact sheet, or do we have an overarching recommendation of how these fact-finding may be dealt with by the government? And I guess that's something for Tad to think about and find the best way forward. So between now, the other thing I should say is between now and the next meeting, we'll once we kind of get these fact sheets done to draft level, we'll also, and we have been discussing generally broader issues in the international engagement, but we'll probably start to address that more between now and the next meeting. So thank you.
Questions? Comments? Thank you, Matt. Next, we have Protect, Toughen, and Augment Subcommittee. Tim, I think you're standing in for John Betts.
Morning, everybody. As Admiral Allen just mentioned, I'll be standing in for John Betts this morning. John, the chair of the PTA committee. I have some slides, I hope. Okay. So what I'll be giving this morning is really just a status overview of the activities. I don't have a lot of detail to go into because this PTA group has actually covered a lot of ground. I'll be focusing on a high-level status as soon as my charts are up. Okay, thank you. Next chart, please. So here's the committee membership. John Betts is our chair. I'm the first vice chair, and Tom Powell is the second vice chair. That's because the subcommittee is actually separated into three subcommittees that each focus in the areas of protect, toughen, and augment. So in the right-hand side of this chart, you can see the focus areas for the protect, toughen, and augment. So under protect, we're looking at transparent and balanced spectrum management. Under toughen, at least in the beginning, we're focused on the subject of export controls and seeing if they unduly constrain civil and commercial interests. And under augment, we're looking at GPS and complementary PNT and signal monitoring and so forth. There's quite a bit of overlap there in the augment with Frank's group that we heard a report from earlier today, and there's been a lot of cross-pollination, I would say, in between those two groups. Next chart, please. Just to reiterate, we're organized like this. We have a PTA subcommittee led by John, and then we've broken it up into a Protect subcommittee, which is led by Tom, and a Toughen subcommittee led by myself, and then John continues to lead the Augment subcommittee. We resolved early on that we wanted to work with the key implementers of our recommendations and not just the XCOM. So we've, in our fact-finding meetings, been trying to include or reach out to other stakeholders that have an interest in what we're working on. And I'll talk more about that as we go along. Next. So we'll just give an update of the Protect group. Do you want to talk to these next two slides, Tom, since they're reporting on the activity or subgroup, or I can do it? Why don't you do it?
So for the Protect subcommittee, we held two fact-finding sessions, one in June, one in October. In June, we had a presentation from Logan Scott, who was actually repeating a presentation that he gave to the advisory board in 2014 about a concept to detect interference using the ability of cell phones to sort of crowdsource interference. And a very interesting presentation. And that was followed by a second fact-finding session in October with Karen Van Dyke and Mr. James Aviles from FAA, where Mr. Aviles talked about some of the efforts to locate these interference events at some major airports that you've heard about earlier. And then Karen spoke about some of the efforts that they are doing to prepare for any potential adjacent band interference as that may occur. And I think I have one more slide here.
Next slide, please. Thank you.
So again, Karen and her team are preparing for possible adjacent band interference, and we have a couple of ideas that we're considering for recommendations that we'll talk about tomorrow.
Next chart. So the Toughen Sub-Sub Working Group has been pretty active. We've actually had 4 fact-finding meetings at the dates listed there. The outcomes were after our first fact-finding meeting was focused on trying to understand what the export control regimes really are and understand how they're impacting the potential market for adaptive antennas. We learned a lot, and we also learned a lot about the established process for making changes or modifying those controls. Followed that up with a second fact-finding meeting, which was a more general discussion of potential improvements to the export controls, and we noted at that meeting that we really wanted to get more information from manufacturers about how the current export rules were potentially impeding their ability to develop these technologies for civil use. And we also decided at that meeting that we would pursue capturing all this information in a white paper. Those 2 fact-finding meetings, I believe, actually happened before the last meeting of this board, and I reported on those and reported to the board that we would start working on a white paper. Next chart, please. We followed that up with fact-finding meeting number 3, which is the first meeting where we started to bring in SERPA manufacturers, and we simply gave them 15 minutes to present about their current products, and to the extent that they were willing to talk about what their future products would look like, they did that. But we also asked them specifically to address how they felt the export controls were potentially hampering their ability to develop future products. I'm happy to say that we got a pretty broad participation from industry, and we still had many government people attending and supporting the discussions. That was followed up with another fact-finding meeting where we had 2 more SERPA manufacturers. One was actually a repeat from the first time. And even more interest and participation from industry in general. And I would say most of all, gratifying most of all, was the fact that we had direct participation by the State Department and DTSA, sorry, that's a typo there, Defense Technology, I forget what the acronym stands for, but working level people that are actually involved in the process for maintaining and updating these controls came to this last meeting and participated in that, actually, I would characterize as an enthusiastic way, seemed to be genuinely interested in the data that we were turning up from these discussions. So that's nice. Another outcome is that we now have a draft white paper which captures the learning so far and actually includes some preliminary recommendation material. It's really just a beginning. It's been circulated among some select members of the committee at this meeting to make sure that we're headed in the right direction with the white paper. It still needs considerable work before it's going to be ready for wider distribution. Next chart. So the way ahead is there's one more fact-finding meeting we hope to have before the end of the year. We'll get presentations from at least 2 more SERPA manufacturers, and at that meeting we'll be putting the white paper on the table for wider comment. So we want to continue that white paper development. And I think that's the last chart. Next chart. Yeah. So overall, from the PTA committee, there will be 3 recommendations to discuss tomorrow, one from each of the 3 areas. So with that, are there any questions?
Thank you. Let me, it's obvious the threads are coming together here. You heard Brad's briefing earlier. We see where you're at on this. We're going to get the State Department side, and you referenced the regulatory regimes out there. Clearly, there's a way ahead, and clearly a white paper is something that we need to collectively put together on this. The question is, who gets and where does it go? And we'll take that for consideration, but this is something that needs to be put forward at higher levels, and we'll certainly deal with that tomorrow and then take it on accordingly. But thank the committee for their work. Any comments or issues or anything? Okay. Thank you very much, Tim. Appreciate
I'd point
it.
out that Brad's been a very active and supportive member of the Tuffin subgroup. I think you've attended all the teleconferences, and just want to acknowledge that. Thank you.
Thank you. Final presentation is the Strategy, Policy, and Governance Group with the Honorable Jeff Shane.
Sorry about the delay. It looks like the slides didn't quite make it, but there they are. Thank you. I am going to speak on behalf of the Strategy, Policy, and Governance Subcommittee. I would start by just, reminding everybody of something that we all know, which is that GPS is not just a miracle, but probably one of the most profoundly important gifts any country has ever given to humankind. I mean, we all know the history. It began, I guess we were jarred out of our indolence by Sputnik back in the 50s, and by the 60s we were producing Navstar in the early 1970s. In fact, in 1972, just half a century ago, a young Air Force lieutenant named Bradford Parkinson was put in charge of taking Navstar and taking it to the next level, and thus we have GPS. We should be extremely proud of GPS. We pat ourselves on the back, and rightly so, but it has been a long time. We made it available to the world 30 years ago. And now, instead of having a single constellation of miraculous satellites circling the globe, we have a constellation of constellations. We have systems that are actually doing better than GPS today. And perhaps that's not surprising. We should be proud of the fact that we engendered copycats who are the next generation, if you will, who have capabilities that we have not yet been able to match. It's a bit of a wake-up call, as indeed Sputnik itself was a wake-up call. And the question is, are we going to wake up? That's as much as anything what this subcommittee, Strategy, Policy, and Governance, is all about. Let me have the first slide, if I may. Yeah, this is the makeup, and I have to say, Matt, I was so intrigued with the template that you used for the International Engagement Subcommittee that I actually entitled ours the International Engagement Subcommittee. I thought I had changed it, but I forgot to press save, and so I apologize for that. But look, plagiarism is the highest form of something. So there's the cast of characters, and I have to say what a privilege it is to work with these folks. Every one of them has precisely the most relevant experience, years of experience. And most importantly, it's not only about the technical side, it's about what makes government work. And so that's pretty much what we've been sort of pouring our energies into. We've been looking not just externally at the way government works, we've even been looking internally at the way this advisory committee works. Next slide, please. So we, early on, early this year, submitted a bunch of recommendations to the leadership of the advisory committee, the advisory board, forgive me. We felt that the meetings that we had were covering too many issues. The briefings were fascinating, and we all came away with a tremendous amount of interesting information, but at the end of the day, to what effect? The briefings were sometimes too long, too detailed. Some of us got more out of them than others, depending upon our backgrounds. There wasn't sufficient opportunity, we felt, to dialogue with the presenters themselves, and most importantly, we didn't have time even to talk among ourselves, to actually have discussions about where we were taking this subject matter. Our recommendations, to the extent we had them, were perhaps not as realistic, not as targeted, not as mindful of the audience for those recommendations as they should have been. So we identified all of those issues, and I'm very happy to say that there was no real resistance to them. Funnily enough, the most important recommendation we could have made but did not was to create subcommittees. That came from our leadership, and the subcommittees were created, and you will have seen from the presentations that have preceded me how valuable they have been. They are generating a quality of information that this board has never before generated. It's rich information, it's in depth. The recommendations almost don't have to be made. The recommendations are implicit in the fact-finding. And we can all be proud of the amount of work that's been done in those subcommittees, because I think they are going to inform the future activity of this board and indeed the government itself in ways that we have not seen in the past. So if I could just move on to the external focus, the next slide. If you take a look at the page 3 of the program that you found at your place, you will see what's called an organization structure. The question that leaps out from that page, I think, is pretty clear, and it is, who's in charge? In fact, if I were going to edit that page, I would simply put a question mark after the words organization structure. Nobody is in charge. That to us seems like the most compelling fact of our GPS sector. We have an executive committee consisting of 2 deputy secretaries, Deputy Secretary of Defense, Deputy Secretary of Transportation. Recent reports have been that the deputies themselves have not actually come to those meetings. There aren't many meetings, but the ones that are held simply proceed without the principals being present. Now, it's easy to say, well, shame on them, they should have come. I think the relevant question is, do they believe that attending those meetings is the highest and best use of their time? And maybe they don't think it's the highest, best use of their time. It may be their comment on the structure. Now, I don't know, I haven't spoken to them. But the fact is that the system seems to be running itself. We don't know where the leadership is, and we're not going to try to prescribe an alternative structure. That would be a silly thing to do. The government knows more about that than we. But we feel that without a single focus of leadership, of identifiable leadership, someone with authority to actually make decisions based on input from all of the relevant agencies, and all of the agencies in our government are relevant today, we are going to continue to fall short of the decision-making that we need, the quality of decision-making that we need. And the rest of the areas that are listed on that slide sort of fall from that. So we don't have the kind of clarity within our government about what needs to be done to protect GPS or our PNT capability, or to toughen it, or to augment it. You saw the very interesting presentation by Brad Parkinson about ITAR restrictions. We've been talking about ITAR restrictions for quite a while, and presentations have been made to the government. We don't know, I don't know what's going on within our government. It seems to me a very compelling presentation, if in fact you're worried about the resilience of our PNT system. The fact that we don't know what's going on, the fact that we haven't been able to find a single point of contact. You heard my question to Brad. What happens if the XCOM actually accepts our recommendation with that? They have to make a presentation to somebody who's in charge of ITAR, whether it's the State Department or the Commerce Department. There are too many layers between the ideas and the execution. And that's a function of the structure and the governance for our PNT system. We talk about vulnerability. There's been talk about redundance. We had a presidential directive as far back as 2002 calling for a backup. Now we have a federal radio navigation plan that says a single backup doesn't make any sense. We're now revisiting whether a backup, as we used to think of it, is the way to go. Well, what's the answer? The answer seems to be a number of systems rely on the private sector, rely on users to protect themselves. Is it reasonable to think that the private sector is capable of protecting itself if GPS is actually taken down? I don't know, but it doesn't seem like there's a tremendous amount of clarity about that. And then my own pet peeve, and I've spoken to this a number of times before this group, is the fact that we tend to kick what our British friends, soccer fans, would call own goals. So we decide on the allocation of spectrum, and we know that spectrum is getting increasingly crowded, in ways that executive branch agencies like the Department of Defense and the Department of Transportation and others feel are suboptimal, are capable of creating out-of-band interference with critical systems, with GPS itself. I'm not going to go back and rehearse the Legato saga. We've all talked about that too many times, and it was good to have. We hope we will get an update, but it's just an example. It's an example of what has happened too many times, the 5G kerfuffle around airports. There was no reason why that had to happen. The governance within our legislative structure today should have prevented that. We didn't need any new laws. It's just that we weren't paying enough attention to the equities. And so, because we have an independent regulatory agency in charge of spectrum, which has been systematically providing miracle after miracle after miracle to the American people through its decisions, we nevertheless get this conflict where suddenly the safety of aviation is called into question. I don't have to worry about, and you don't have to worry about safety because the FAA will protect the safety of flight, but it will obviously create disruption if we don't do something else. These are things that just shouldn't be happening. And we, within this subcommittee, attribute a lot of that to the fact that we don't have anybody clearly, decisively, conspicuously in charge of PNT. So I will stop there and invite your questions. Thank you.
Thanks, Jeff. Comments, questions? Dana?
Yes, sir, I'm very glad that this was all recorded because that's worth keeping.
Eloquent as always. I note for the first time since I joined this board, which I think was in 2012. So that's what, 10 years? We are ahead of schedule. Congratulations to you all. Are we prepared to have the others go ahead, JJ? Queued up? Stormy, you ready to go? Okay. What we're going to do in the next two sessions, and I mentioned this earlier, between these two sessions, we're going to cover some other material, but we're also going to address the current situations once and for all, at least for today in this meeting, what's going on with Legato as well. But we're going to start with Stormy and the XCOM update. Stormy?
All right, thank you very much. Okay, so again, thanks for having me here. It's an honor to talk to the board. Like GPS, this board is really a national treasure. You are a brain trust that this country needs. Although you may not hear it a lot, I think they really need to understand across government the great ideas that this board can bring to the table. So thank you for that. And also to piggyback on what JJ said about the Artemis launch, you know, it's really incredible that America is going back to the moon and also GPS is going to the moon, right? There's some GPS equipment on that Artemis flight as well. And it's just, I just giggle sometimes that we're going to be using GPS when we're flying near the moon. You know, maybe Dr. Parkinson planned that way back when, but I was never aware of that as a possibility. So
We're going to put
again,
his ashes on the next launch.
there you go. So congratulations again to NASA for that great work. Thank you so much. Okay, so I will talk to you today about some activities that the XCOM has been going through the past couple of years, specifically the strategic plan for potential interference to GPS from Legato transmissions, which we call the SIPI. Next slide, please. Okay, so just a little bit of background, and most of you have lived this along with me and some others, so you know it as well or better than I do. But, you know, a U.S. telecom company, Light Squared, back in the 2010-2011 timeframe, applied to FCC for a terrestrial system in the spectrum band, you know, just to the left of GPS, right, adjacent to GPS, and FCC gave them a conditional waiver. Over the next couple of years, the XCOM, the Department of Defense, Transportation, other departments and agencies banded together and conducted testing to take a look at that plan and determined that there was going to be harmful interference to GPS. The XCOM sent a letter to the Federal Spectrum Regulator, the National Telecommunications and Information Administration, or NTIA, aimed at the FCC, right? And NTIA did send that letter to the FCC. At the end of that chapter, Light Squared filed for bankruptcy. In the 2015-16 timeframe, Light Squared emerged from bankruptcy and became Legato Networks and modified their application to the FCC for terrestrial communications. Fast forward to 2018, and rather than continue to test plan after plan from a potential telecom vendor, the Department of Transportation conducted the Adjacent Band Compatibility Study, the ABC study, where they really determined the maximum tolerable adjacent band power limits for a wide variety of GPS receivers, and they published that in 2018. Based on that, the XCOM sent another letter to NTIA for FCC stating that proposals to operate services in bands adjacent to GPS should not be approved unless at a minimum they do not exceed the tolerable power limits in the ABC study. Next slide, please. Unfortunately, in 2020, the FCC approved Legato's application to deploy their terrestrial network in that adjacent to the GPS L-band. There were a bunch of conditions. Some of them are shown on this slide, right? Legato had to provide a 6-month advance notice of deploying and activating any base station in that band. It must include, a coverage map showing where the network's going to be deployed. And then also there had to be a 30-day notice with specific base station information prior to operation of any of those sites. Next slide, please. So in that 2020 timeframe, out of concerns about potential impact to GPS receivers across America, if those legato transmissions were to actually begin, and again, that FCC-approved power level was about 10 watts, which is higher than the maximum tolerable power limits determined by the ABC study for a wide variety of GPS receivers. The XCOM directed development of a mitigation plan for that potential interference. The NCO established a working group to develop that plan with membership from across the XCOM. So that's where we started the SIPI-WIG, and it's met quite a few times since 2020 to develop and refine that plan and then begin to put the plan into action. And the plan itself has some major elements, including outreach and communications, spectrum monitoring, and impact monitoring. Next slide, please. So again, in terms of outreach and communications, some of the potential areas that plan talks about is to, create awareness of the issue and what reporting processes are out there, help identify what capabilities are available for users to determine whether their applications are actually being affected, because as you know better than I, most GPS receivers do not have something that alerts you when interference is present. Communication to try and ensure that interference reports are actually provided to the government, such as to the Coast Guard Navigation Center, and that actions are taken in response, and then determine potential options to remedy the issue. Potentially develop, for instance, government best practices documents that would help guide users on how to identify interference, report it, et cetera. And then it talks about a variety of potential outreach mechanisms, right, including meetings such as this. So this is kind of our first meeting where we're doing this outreach, and then it shows a bunch of other outreach mechanisms that we may use on there as well. So next slide, please. So in terms of spectrum monitoring, the goal there was to monitor and be able to characterize emissions to enable attributing legato transmissions to actual performance degradations in GPS equipment. And there were four main tasks in the spectrum monitoring. Develop GPS equipment interference metrics, validation of metrics with laboratory testing, develop field monitoring and measurement recording capability and integrate those into test vehicles, and then get out there both before legato would deploy and continue operating afterwards so that baselines could be developed and data could be characterized. And both Department of Transportation and Department of Commerce, specifically NOAA, have done some great work in this, and you'll hear some more about that here in a little bit. Next slide, please. Just a little bit about the DOT monitoring capability. I'm not going to read you much on this slide because Karen has a much more detailed presentation coming up that I'm sure you'll be very interested in. But again, talking about lab stuff, mobile capability, potentially eventually fixed capability. For harmful interference metrics, right, transportation and the XCOM stand behind the ITU 1 dB interference protection criteria. We've stood behind that for over a decade and continue to do so. The technical team that transportation worked with also looked at other metrics, carrier noise degradation, loss of lock, increase in acquisition time, et cetera. With a lot of input from departments around the XCOM in the SIPI-WIG and with NTIA as well. And they did a lot of great coordination with Commerce, Energy, NASA, FAA, et cetera, about not only putting together the monitoring capability, but getting some receivers that could then be tested during that. And then also vendor outreach. So next slide, please. So some other things that have happened recently that are of note. Legato submitted an application to Canada for terrestrial communications there. Same band adjacent to GPS, but at a power level of 776 watts, or roughly 77 times the power in the US application. So that's of interest. You will recall back in 2021 that the National Defense Authorization Act chartered the National Academy of Sciences, Engineering, and Medicine, NASM, to do a technical review of the whole issue, of the FCC order, et cetera. And NASM did that study and released their report back in early September. That same day, Defense, NTIA, and the XCOM released coordinated statements about the NASM study. Just a few comments about that. Again, the XCOM appreciates the NASM study and that report on the important topic of interference to GPS capabilities, including those critical to national, homeland, and economic security. And the XCOM, co-chaired by the Deputy Secretaries of Defense and Transportation and with membership from over a dozen departments and agencies, supports the stated national policy goal to protect the spectrum environment that GPS uses and its augmentations, including critical systems for federal government, the men and women of our military services, the economy, scientific advancements, and U.S. critical infrastructure. Also, the XCOM statement said that it agrees with the statements by Defense and NTIA about the NASM study, that the XCOM is going to review the lengthy study carefully, but agrees with statements that our nation requires a solution that ensures continued operations of critical systems. And the study confirms that the GPS interference testing approach used by Defense and Transportation based on signal-to-noise ratio is more comprehensive and informative. And in addition, XCOM agrees with NASM's assessment that the FCC proposed mitigation and replacement measures are impractical, cost-prohibitive, and possibly ineffective. And the XCOM looks forward to continue to work with departments and agencies on this. Shortly after that statement, or those statements came out from Defense, NTIA, and the XCOM, Legato filed a letter with the FCC saying that it does not intend to move forward with its trial deployment in Northern Virginia. But again, we don't know what, how often intent might change. What we do understand is that that letter of intent to FCC did not formally withdraw the 6-month notification of deployment that they had filed with FCC. So at this point, their 6-month notification had said that deployment in the Northern Virginia area would occur on or after 30 September. It has not yet started, and our understanding is we're basically kind of on a rolling potential 30-day clock because they could put that 30-day notice in at any time. Next slide, please. So going forward, NCO will keep leading the SIPI-WIG regarding potential interference from Legato. The departments and agencies are committed to continue efforts for outreach and communications and both spectrum and impact monitoring. And I think we've got presentations from both Commerce and Transportation on some of the great work they've done on that. So happy to answer any questions you have on that.
Thanks, Stormy. Brad?
Thanks. As always, you do a great job of presenting, Stormy. But one of the things that suddenly struck me as a taxpayer from time to time, especially in April, is some groups of people in the United States government have been paying literally tens of millions of dollars to try to resolve this issue that was obvious 12 years ago to many of us and has simply been confirmed again and again and again. Why is Legato not liable for all the costs they have incurred in this massive and relatively futile exercise?
Yeah, that's a really good question. I think it's more of a legal question, and, I can say that, the NTIA, right, took the rare move of sending a petition for reconsideration to FCC, and there are legal discussions going on about that. FCC has not yet made a ruling on that, so I'm not really able to comment on those legal discussions going on right now, but I don't think that was specified in the FCC order and authorization. And, it says Legato is liable for certain things, but I don't think, the cost of the ABC study, et cetera, I don't think that was included. But again, I'll defer to the legal experts on that.
Yeah, Stormy, we won't force you to practice law without a license here.
Thank you.
Jeff, you got a comment? We do have a counsel in the room.
I'm not licensed to practice law in California, I should say, but I am in the District of Columbia, which is where all this nonsense is taking place. And the answer to your question, Brad, is that they have a license from the Federal Communications Commission to do what they're doing. So there's no occasion for imposing liability on them. The license includes liability for federal expenditures to address interference, and there's legislation still pending in the Congress, I think, that would extend that liability to the harm that befell any citizen, anybody who experienced interference. But that legislation isn't passed, and I don't know what its prospects are. My question, however, Stormy, and thanks for the briefing, because it was a model of clarity as always. In addition to attempting to mitigate the perceived interference or the harm, if you know, or if you can say, has there been any discussion of the fact that this whole problem could have been avoided by simply having the FCC pay more attention to the equities being expressed by federal agencies? Is there any concern about the possibility of replicating a case like this in the future? We've seen several of them, as I said. We're the only developed nation in the world, to my knowledge, that repeatedly shoots itself in the foot when it comes to protecting critical spectrum-based infrastructure.
Yeah, so I can't comment on the discussions, but I can say that, the FCC and NTIA recently published, a new memorandum of agreement for spectrum management, right? And that's out there in the public domain. And so there is certainly a realization that improvements can be made to spectrum management for the U.S., and that MOA lays out a process that they're trying to work through. And I don't think it's going to be a quick process, but there is at least a new MOA, and I think it'd be really interesting if the board took a look at that and gave some thoughts on what they think of the proposals, in that MOA.
Just, Jeff, do you hold that MOA in your subcommittee?
I'm sorry, say again,
Do you
please?
hold the MOA in your subcommittee? Have you seen it yet?
No.
Okay. We'll get that. Dana?
Yes, sir, just a comment to build on. It's hard to imagine that the FCC would want a replication of this multi-year, multi-decade debacle, and so I would think that they would go to great lengths to try and avoid that. And I think that the announcement of the establishment of a space bureau is evidence that they're proactively trying to keep it from happening again. Now, how they'll resolve the present dilemma, one would hope that they would respond to the 7 petitions for reconsideration, but that remains to be seen. They've got to do something, I think.
Yeah, thank you, yeah. Agreed. A lot of good people are trying to work through it, but there's some unfortunate challenges that have to be overcome.
Yeah, I would just say I was at the last XCOM meeting. Stormy was as well. The FCC recused themselves from the meeting. It's rather extraordinary when you have an interagency meeting and another government agency recuses himself. So I'll let that comment stand on its own merit.
Yeah, and so deference to Jeff, but they seem to be, over the decades, become more and more legalistic in their approach and less engineering and technology oriented. But that's certainly in keeping with the legalistic, and perhaps that's a necessary thing. I don't know. I'm not part of their business, but.
I think we need to be honest and, you know, fair to the FCC. The FCC operates pursuant to legislation, including the Administrative Procedure Act, that actually does make it independent. And it can't play fast and loose with the rules. We understand that. Whether the agencies like the Department of Defense and the FAA and others who manage critical systems which rely upon clean spectrum should be treated as parties of interest in a litigated proceeding, an administrative proceeding before the FCC, to me, is the salient question. The answer today is absolutely. That's what the law says. My question to Stormy was, is anybody asking whether that is fit for purpose today? To me, it obviously is not. You've got the FCC making decisions that affect national security, the safety of life, and the Communications Act of 1934 was not intended to give it that power.
Yeah, great questions.
Well said, Jeff, thanks. Other comments? Yeah, Matt?
At the risk of accusing Dana of being optimistic, which is rather rare, the press release around the new spaceport in FCC talked about 60,000 satellites in the last 2 years and being able to better license them. I'm not sure there were 60,000 PNT satellites in the last 2 years, so is it really about, I don't think we should assume that that's necessarily, that they're necessarily focused on PNT when there's 60,000 comm satellites going up. Just a thought, yeah.
Thanks, Stormy.
Hey, thank you much. And now on to some more technical stuff that's a little less political.
Yeah, we've been talking about high accuracy services and monitoring and so forth. At the recent XCOM, there was a, oh, I'm sorry, you going up next, Karen?
Well,
Yeah,
I think Miss Juliana Blackwell was next
Oh, I'm
on
sorry,
the
yeah,
agenda.
let me continue with what I'm sorry. I saw DOT and I thought of you, I apologize. We had a brief at the last XCOM, and I don't remember what the acronym stands for, CTORS, but it's a monitoring system that's out there trying to look for anomalies, and I thought it would be relevant to the group to hear this. Go ahead, I'm sorry. Juliana, correct? Oh, okay, I'm sorry.
Yeah, Department of Commerce, Noah, are you there? Over.
That's what got me misdirected. I saw the DOT slide.
Yeah, so as a backup, Stormy's agreed to present her chart, but she was going to try to present.
Yeah, I'll be happy to talk to it. So if you want to bring up the T-Cores slide.
I don't see her listed on the,
Ken, you have I think it's in Stormy's last presentation, a couple of charts in the back. Or
Yeah,
one chart.
I don't think it's actually in my presentation. I think it was, it was an attachment, an email from Juliana to you and and I think Leisha.
Okay.
if we can't find a way, we can bring it up later.
Yeah, we can, I can bring it up after DOT if you want to do it that way.
Perfect, thank you.
Then that does bring us to Karen. Sorry about the confusion there. Karen Van Dyke, DOT.
Great, well, thank you. Good morning, everyone, and it's always a pleasure to brief the PNT Advisory Board. And if you have the slides, and just while they're bringing the slides up, so I will talk a little bit about what Juliana was going to speak to as well, and then Stormy can follow up later. For DOT, I just want to underscore that we very much appreciate everything that the advisory board has been doing on the PTA principles, protect, toughen, and augment. So those very much resonate with us, and we have embraced them in the way that we think about PNT resiliency and the steps that are needed to protect, toughen, and augment. So the talk today is predominantly going to focus on interference detection and mitigation, but also I understand at the prep session yesterday there was a lot of interest in Space Policy Directive 7, which of course guides the XCOM and our partnership with Department of Defense and Space Force in particular. And so since the last advisory board meeting, and certainly Admiral Allen, you and JJ participated, we did hold a space-based PNT summit at the end of May. That was co-chaired between our Deputy Secretary of Transportation and General Thompson, the Vice Chief of Space Operations for Space Force. And it was very beneficial, particularly to have that in-person event. I think we recognize that Space Force was stood up in 2019, and a lot of us hadn't had the opportunity through the pandemic to meet face-to-face. And a lot of other topics are related to work that DOT is doing that we would be happy to brief on, particularly related to work on the executive order. But for today, we're going to talk about IDM and our strategy and through all of the great work that particularly the PTA subcommittee and others have been doing. I think it was a great setup for the importance of interference detection and mitigation, and the fact that we do need to actively identify sources of L-band interference. And today we rely on user reports, whether that's reports coming to air traffic control from pilots, Coast Guard Navigation Center receiving reports from other civil users. And as Dr. Parkinson showed, we're only receiving a fraction of all of the interference incidents that are out there. So we need to embrace both in-band and adjacent band interference and be able to address that. And it's a multi-layer approach, and this isn't Department of Transportation alone. It really is an interagency effort in harnessing all of our capabilities that we can bring to the table, as well as certainly commercial capabilities in state and local. And I'll underscore law enforcement, because the mitigation, the M part of IDM, that is not Department of Transportation. And so we're focusing on detecting sources of interference, but we can't actually go and remove those sources. So we've been working on a concept of operations, and really thinking about how do we embrace technology. And I think Dana brought up a good point of, when interference events occur. So Denver and Dallas were the big ones this year, but we have interference that's going on every single week of the year. And for those of you who know James Aviles from FAA Spectrum Engineering, and he's been on detail to my office in OSTR for the past couple of years, and he's just phenomenal. And he's lived and breathed GPS interference and hunting down sources, and he'll be the first to tell you that relying on user reports and going and chasing after the sources got old a long time ago, namely after the infamous Newark incident. And so when users experience interference, I think this is analogous to other disruptions, whether it's electricity, internet. When something happens, you don't know, is it your user equipment or is it something larger that's going on? And so really having that heat map, that common operating picture, so ranging from inside the US government to all of the end users, and pushing out that common information and description of what we know about the event in the area that it's impacting. So if you as a user are having a problem, and you can go and look at your operating area and say, okay, maybe in a way it's comforting to know you're not alone and others are experiencing the problem, but if there is nothing, then maybe it is your specific user equipment. And so this really, shared situational awareness and bringing in sources from all of the capabilities that are out there. And I think this really builds upon the work that Logan Scott has advocated for in terms of crowdsource interference detection. So taking it beyond just the cell phones, though, we, DOT, have recently entered into a partnership with the Defense Innovation Unit. So they have a program called Harmonious Rook, focused on GPS interference detection. And the basis of their program is essentially leveraging GPS receivers that are out there. And every GPS receiver, in a way, can monitor the environment and interference that is happening. And if you can harness all of that information and bring it into a common operating platform and apply artificial intelligence to that, so you're basically correlating a lot of sensors of interference and being able to hone in on what the location of that interference is. That becomes really, really powerful. So they started using the ADS-B data, Hawkeye 360. For NASA, they're very interested in capabilities on the International Space Station and other space-based assets that are going to be available. The automatic identification system for the maritime environment, and then information that can come in from fixed and mobile ground surface sensors. So they've been talking to some of the automotive OEMs, and also recognizing that we have a lot of reference receivers across the United States. And we were just talking about CORS, the continuous operating reference system from NGS, that again, we can tap into all of that information helps us. So why this is important? So I think we've already talked about Denver and Dallas, but the fact that we're relying on these user reports and embracing the process that the Purposeful Interference Response Team put together, the PERT, and the Crucible process. But we recognize that is really inadequate. It's very time-consuming to gather these reports. And we're talking about shooting ourselves in the foot. We really are not taking advantage of technology and all of the receivers that are out there. And so for Denver, in January, 33 and a half hours. We were able, through multiple sources, to get the radio line of sight down to 2 miles and locate that source of interference. For Dallas last month, 46 and a half hours, and a radio line of sight of 126 miles, and we never found the source. And that is really disconcerting with the impacts that were going on at DFW, and not knowing to this day what the source of interference was. And that was not for lack of trying. The FAA had 2 flight check aircraft flying all over Texas during that event. So that was quite expensive. I won't quote a number, but it was a large dollar figure for FAA. Between the flight check aircraft, which I'm told is $3,800 an hour per aircraft, as well as all of the ground-based sensing that was going on to determine the source. And it wasn't FAA alone; it was across the federal government, reaching out, and then the source just poof disappeared. So, again, as Stormy said, in-band interference as well as adjacent band. And when Legato announced in March that it was going to deploy by the end of September in Northern Virginia, we were already thinking about this and concerned, and having lived and breathed this dilemma for quite a long time, going back to Light Squared. We certainly recognized even before Legato filed with the FCC in March that we were going to need to get out ahead of any Legato deployment and be able to directly attribute interference to Legato. So we also recognize that the mitigations that FCC had put in place in the order and authorization were not adequate. And so we started through the great work that our Volpe Center did, and MITRE and Zeta Associates working late last year to start strategizing about what it would take to get out ahead of any Legato deployment. So the March 30th filing, which gave 6 months notice, that really ramped things up into to high gear. As Stormy mentioned, we were focused on two major components. One, interference metrics, and going beyond the 1 dB CNR degradation to correlating actual impact to receivers. And the second was having a capability through a mobile monitoring van that was able to, in the case of Legato deployment, be able to characterize both before and after, and have that spectral baseline, because I think we who have been dealing with this issue would not expect Legato to admit to interference. They likely would try to say that interference was already in the area, that it wasn't them causing the source. And so we spent quite a bit of time with stakeholders, understanding what it was going to take to have a capability that would stand up to scrutiny. So this is the graph that the FCC, that Legato included in their FCC filing in March. So that's the graph on the left. So in terms of the deployment, they didn't actually specify where their transmitter or transmitters were going to be. So that is what we anticipated with the 30-day notification that would come in advance of their deployment. So I mentioned we were working with MITRE and Zeta. So fortuitously, they're located very close to the footprint of where Legato is looking to broadcast. And then a shout out to NGS with their temporary cores network. So we certainly know that the core stations are very sensitive to adjacent band interference. And so the temporary cores, or T-cores, they did install on the MITRE building in Tysons. And then our Virginia DOT building in Reston is actually directly across the street from Legato headquarters. So maybe it seems like we're stalking them, but we did, through great work at NGS, put a temporary cores capability on that Virginia DOT building. The mobile monitoring capabilities, so the van that the Volpe Center has was equipped to have the spectrum monitoring capabilities. So again, we were waiting for Legato to actually announce where their transmitter was going to be, so that we would be able to go out and collect information and create that spectral baseline. We also were working with the interagency on receivers that they wanted to have included in that monitoring network once Legato did start transmitting. And importantly, we recognized that we couldn't carry around all of the receivers that likely everyone was interested in, so that mobile monitoring equipment had the ability to record and play back in a lab, so that we could evaluate impact on other receivers as well. And then in terms of the harmful interference metrics, I think Stormy did a great job in describing some of the interagency discussions that we had through the SIPI working group, and in particular with NTIA in the interagency, and being very clear that we absolutely embrace the 1 dB CNR degradation interference protection criteria, but we recognize that FCC did not accept that criteria in its order and authorization. and they were very clear that they did not accept that 1 dB interference protection criteria. So looking at other metrics that we could use to prove that the GPS receivers were being interfered with. So certainly increase to acquisition time, impact on ranging error, impact on position error were critical, and really applaud the NTIA leadership and engineers for working with us and very much wanting, again, to put together an airtight case in support of directly attributing interference to Legato that would hold up against FCC. And again, that direct attribution is critical, so ensuring that we could isolate the Legato transmission and its impact on ranging error, which meant removing all other sources of ranging error. So working a double differencing and code minus carrier approach to isolate the interference sources. And that works except for multipath, and then approaches to remove the multipath error as well. And again, that baseline approach to have the before picture, where then once Legato started broadcasting, we could clearly see what the difference in the spectral environment was. So fortuitously, for this community that Legato has not started broadcasting, not so good for us on the DOT side, where we put this capability together and we're ready to go. But now, a question mark of when or perhaps, if Legato is going to deploy its network. But I really applaud all the great work that our team has done in getting us to this point. And it was an investment. Penny was asking me this morning, sort of like, in terms of, resources. Well, we bought took the initiative, and really applaud Dr. Hampshire, Deputy Assistant Secretary for our Research and Technology Office, for saying this is the right thing to do. We can't wait until Legato deploys and then try to be doing this, after the fact. So for those of you who understand how small our budget is, that this was a significant, effort to really move forward and put this capability in place. And if Legato never deploys, we will certainly take these resources and apply them to our broader IDM initiatives. So in closing, when we think about IDM and PNT resiliency, the key metric is minimizing the duration from the time interference starts occurring to removing the source of interference. So we have to, I don't know that we'll ever prevent interference from occurring. Certainly that's a noble goal, but I think we recognize that just given how easy it is to interfere with GPS, that we just have to be prepared to detect, locate, attribute the source of interference, and remove it as quickly as possible. Relying on user reports, I've long stated this, that is just woefully inadequate, and it's subjective, and so a lot of good reporting that comes in, but a lot of reports that are just perhaps due to user equipment malfunction. So I think we're on the right path now for embracing that sensor information and harnessing as much that's out there. And I'll certainly, to the advisory board, we made this offer to the Protect subcommittee. If you know of sources that can be used to integrate into this overall common operating picture, certainly Defense Innovation Unit is quite interested in that. I think they're looking to prioritize, what are the best sources that maximize interference detection. And again, the direct attribution of the source is critical to rapid mitigation, and having the law enforcement, folks to work on the mitigation piece is critical as well. So with that, happy to take any questions.
Thanks, Dana.
Yeah, Karen, about your interference detection mitigation strategy, have you given consideration to a legislative proposal to empower state and local law enforcement to take action against illegal transmissions that interfere with GPS and other GNSS. That could actually motivate them to get their own equipment and to associate that activity with other criminal. Could be a great force multiplier.
Yeah, so I'll set aside the legislation part of it, but certainly in conversations with DHS, who led the after-action reporting activity from Denver, and reaching out at the state and local level, and always asking the question of, what can we do better? And I think harnessing those assets and like you said, equipping them with the ability to detect interference, and at the law enforcement level to be aware that this is an issue and be looking out for it, and to be ready to remove those sources. So.
Right, but at the moment, even if they have the equipment, which is easy enough to come by, and they find it, they really don't have the ability or the authority to do anything about it, right?
Yeah, I'm not sure in terms of their ability given that it is illegal to be interfering, with spectrum, and I think if.
So another follow. So the FCC has an enforcement capability or responsibility. So how are they playing into this interference detection mitigation thing, if at all?
Yeah, no, that's a great question. Yeah, like you said, they do have an enforcement bureau. It's not as strong as it has been in the past, but they have been really great partners with us when interference events occur. Their job is obviously easier when we can point the finger at where we think the source of interference is coming from, and I think that's some of the changing dynamics of what we're facing, where I think there's an increasing role and expectation for Department of Transportation and perhaps other departments and agencies to do some of that upfront legwork of detecting where the interference source is coming from. And because we have, I think, FCC, perhaps just because of some of their resource cutbacks, don't have that capability.
I'll leave it to others to be less generous than you in their assessment of the FCC's fulfillment of their responsibilities in that area. Finally, again, I won't put you on the spot on this either, but my experience in government, that when you have a strategy, that means you don't have any money. So best luck and support for your efforts to actually get a interference detection mitigation system in place of some sort.
Yeah, well, so I will comment on that. We did get resources in our FY22 budget request, and that, but thinking, long term, and this was some of the discussions that we had, and MITRE held a really great GPS interference situational awareness workshop in May. And the discussion was, where is the best place to invest our dollars, and going out and buying a lot of equipment that would then have an O&M tail on that did not seem to be a good approach. And so what Defense Innovation Unit is doing with really harnessing a lot of commercial capabilities that are out there was very attractive to us. And like I said, our partnership was just not signing on paper. We did send money to DIU to be good partners in leveraging the capability that they've been working on for DoD. But then I think that is an opportunity for all of us to think about assets that we have that might be able to contribute.
But nothing in terms of, so far, in terms of an ongoing program that for services or other kinds of things that would provide us that kind of common operational picture.
Yeah, I think it needs to be, it needs to be embraced as we're going forward. Again, I don't think these interference incidents are going to go away, and that we, as we have that, what I call it, the heat map, and really knowing where to send our assets, whether it's flight check aircraft or assets on the ground, will help minimize that duration. So I think it needs to to be part of our collective approach going forward. And that's not to say that we would move away from user reports or discouraging users to report interference, but my goal is when they report interference that we already know that something is happening and we can confirm that to the user, and then it just becomes a matter of how quickly we can remove that interference source.
Jeff.
Karen, it was a great briefing. I'm just curious, will there be, and forgive me if this question was asked and answered because I wasn't being able to pick up everything, but is there an effort, will there be an effort to socialize the findings, the effort that DOT has undertaken in this context with higher levels of government? I'm thinking about the NSC, I'm thinking about OSTP, I'm thinking about the Office of the President. I mean, this has been a cock-up of major proportions and attributable to an independent regulatory agency over which the executive branch has very limited power. It's not a mistake we should waste. How much of that is actually in DOT's thinking, and how much of it will go to the other participants in the XCOM and so forth?
Yeah, thank you, Jeff. That's a great question and very much part of our thinking. So certainly, Caitlin Durkovich at NSC is very interested in the efforts and has really been championing the Executive Order 13905 implementation. OSTP came out with a national R&D plan for PNT resiliency, and I think connecting the dots of the work that's going on, and while we never want an incident like what happened in Dallas last month to occur, I think we should use it as an opportunity to really show what needs to be done to solve it. I mean, it is a problem that certainly received attention at the secretary level, or Secretary of Transportation and the FAA administrator, and I think is the opportunity. They were actually shocked that we didn't have an automated way to detect GPS interference, and so this is an opportunity to say, yeah, we absolutely need to have that, and as Stormy likes to say, resilience isn't free, and that resources are needed to invest in that capability. And I some of you may have seen the GPSjam.org that a Disney engineer created. I think during the Dallas incident, they probably got more clicks on that website than they had prior. And again, I think it was recognition that the U.S. government needs to have that capability.
If you can say, is there any thought to a legislative proposal, any follow-up in that regard, where national security might be at stake through an independent regulatory agency's action of the sort?
Yeah, I can't speak to anything.
Karen, let me take a swing at that.
Thank you.
I was going to provide a comment anyway. I think there are two things we might want to consider, and I'm glad to go offline with this if you like, with Stormy. The first thing I would do is I would take a look at the legislation that was created in the FAA Reauthorization Act regarding unmanned autonomous systems and how that got propagated across the interagency and how the command and control works for that, especially. My second point is during national special security events like the Super Bowl. And it occurred to me, if you want to prototype or test bed this, and this is Caitlin Durkovich's area where she could get involved in it, will be to take this capability and make it part of the overall federal response architecture for a national special security event. That would be the Super Bowl, the World Series, a national funeral, inauguration, and those types of things, where it actually enhances the preventive and the resiliency and actually mitigates risk. But brings a test case on where you want to proliferate this out. That's what's happening with unmanned systems now, especially drone operations and around national special security events. I would suggest there's probably a way there. Don't want to draw out the conversation here, but I would start with the FAA Reauthorization Act that looked at UAS as both a capability and a risk.
Great. Yeah, no, thank you. That's an excellent suggestion. And I just like to acknowledge the great team of folks who have worked on the IDM capability. I mentioned James Aviles, but certainly Ken Alexander and Sean Memon from FAA, our Volpe team. I know Dr. Hansen's in the audience, and Dr. Wassoff, and Miter, I know all of you know Chris Hegarty, but also some of his colleagues, and then Zeta Associates. So it's just been a phenomenal team of dedicated folks, working on this, and again, a lot of great participation and support from the interagency. So thank you.
Thanks, Karen. Well done. I understand we have Juliana Blackwell on our team's platform, ready to have the conversation about cores. You there, Juliana?
Good morning. This is Juliana Blackwell. Can you hear me?
We can. Please proceed. Thank you.
Excellent. Thank you, Admiral, esteemed board members. My apologies for the lack of two-way communication earlier. Looks like we're set to go. Thanks for displaying the one slide that I have to talk through with you today. First of all, a little bit of background about CORS and NOAA's role in managing this network of GNSS stations. Under the Department of Commerce, NOAA has a responsibility for providing the National Spatial Reference System, on which we rely very heavily on GPS to do in our current work and mission. As part of this, there are over 1,800 continuously operating reference stations that collect GPS data that we assimilate into our National Spatial Reference System as geodetic control. They provide three-dimensional positioning information for meteorology, for space weather, and a lot of other geophysical applications. This network that we manage is owned and operated really by hundreds of partners, in the sense that out of these 1,800 stations, 40 of them are owned and operated by NOAA. The rest are from partners from government, academic, and private sector organizations. Because of our capability and the need for these stations to continuously operate in order to provide positioning information, both in a post-process sense, as well as contributing to connecting real-time networks, and within real-time networks, we have a role in managing the data, providing an opportunity for people to connect to these stations 24/7. Surveyors, GIS users, engineers, scientists, other people who collect GPS and GNS data use this NOAA CORS network data as geodetic control for their precise positioning for their surveys, and they align their work to the National Spatial Reference System in this way. In support of the strategic plan for potential interference and the work that's been done over the last few years in particular, NOAA's National Geodetic Survey has established two what we're calling test cores. These are temporary cores that were established near the locations where we thought there might be potential interference happening as early as September. The reason why these temporary test cores were established is because we did not have any permanent stations that were in the local area of the potential interference locations. So we went out and were able to establish a pair of receivers and antennas at two different sites, close to where the proposed transmission sites were thought to be operated from. At each of these two stations, there's a PNT resilient setup and a non-resilient setup. So we're going to have an ability to have both an older type setup as well as a newer type resilient setup in order to track if there was any interference detected. The picture on the left is in Ruston, Virginia. The test cores there is in a location where loss of L1 signal lock would occur on the non-RFI resilient receiver antenna pair. There are trees and a highway sound barrier wall that would prevent line of sight between the Legato headquarters, which is where we were expecting there would be transmission, and this Reston test cores that was established. On the right side, we have set up again, a pair of receivers and antennas on top of a MITRE building, a company in McLean, Virginia, and that is about 10 kilometers from Legato headquarters, but within the L-band broadcast area indicated by Legato several months ago. So we had set these temporary test cores up in the September timeframe prior to when we thought transmission might begin. To date, there is no indication of interference to the GPS L1 signals at either of these test cores. And we are continuing to look at the data to see if stations are continuing to track L1, and they are. And we're also utilizing a spread spectrum analyzer to look for any signs of interference. This could be intermittent, this could be, longer term. And we're looking at this data 24/7 to see if we detect any types of interference occurring at each of these locations. There are no reports of any issues at this time. There haven't been any reports from any of the local county or DOT surveyors in these areas that might pick up on any sort of other issues that might occur. So for now, NOAA's National Geodetic Survey is planning to continue to have these stations run. I expect that, within a few months, if there isn't any additional indication that things are going to change, we may be asked to have our equipment removed from these locations. So for now, we're keeping them up and running, and we have great partnership for Virginia DOT and from MITRE, but these are temporary in nature, and they are really just being able to look at things sort of as things come in and after the fact, we can take a look at the data. We do not currently specialize in identifying GNSS signal interference in real time. So that's one of the areas that is not our area of expertise, but we could work in the future with other network operators who are doing more real-time work to see if there are ways that we could enhance their real-time network or provide technical assistance to them if there were transmissions that we were trying to track down and monitor. That's the only slide that I have for today. Again, I apologize for the delay in getting this information to you during your meeting. And if there are any questions or any follow-ups, I'd be happy to try to respond to those now or in the future. Thank you.
Thanks, Juliana. And it was actually well sequenced and well timed, and we appreciate it. I'm going to ask for comments and questions here since we're working with you out of sight, if everybody could identify themselves when they ask the question. Brad?
Hi, this is Brad Parkinson. I appreciate your rundown. Obviously, you're performing a great service to the United States and what you normally do. I have a concern on the spacing of transmission towers from Legato, because the initial analysis we did assumed a series of spacings, but we were looking at on the order of 400 to 1,000 meters, simply because that was the normal laydown for the type of services that they were contemplating. And so if you're not monitoring it fairly closely in terms of geography, it seems to me you're not really understanding the total impact. I think this perhaps argues for, in addition to what you're doing, which is great, that there be reference monitor stations within at least a half the normal spacing distance of wherever Legato is planning to do their transmissions. And I don't know if you have a comment or Karen has a comment on that. Thank you.
I'll just start out This is
I was
Juliana.
asking
Can you hear
Karen
me?
had a comment first. Do you add any?
Okay.
And then we'll go to you, Juliana.
Yeah, I think that is a very good observation, and for us with the mobile monitoring capability, so we were intending to be able to drive that around, obviously, park the vehicle. I think as we got more insight into what Legato's, we know what Legato filed and is in the FCC order and authorization, not knowing exactly what their plans were in northern, Virginia, whether it was one transmitter or they really were going to go all the way to the 433 meter, spacing. But I think we would want to see what that laydown was going to be and whether we would want to put fixed sensors, in to tackle exactly what you're recommending.
So, Karen, that means we still don't have insight into what the ultimate spacing is supposed to be?
Only what they filed with the FCC, and the FCC agreed in their order and authorization. But when they filed in March, talking about their initial deployment, there was no information on the location or number of transmitters. So it could have been one, it could have been multiple, and they would need to provide that information, as Stormy said, 30 days in advance of their deployment.
Well, of course, that's the heart of the issue, the density of laydown of these transmitters. And if you recall back when that vice president, what was her name, that came to brief us, Valerie Green, we attempted to get her to state what the spacing was, because if the spacing's every 100 miles, okay, we got a little problem, but it's not big. If it's 433 meters, it's quite a different matter. And for some reason, we've never gotten to grips with what it is they're ultimately trying to do. So I'm puzzled.
Juliana, any comments?
I will just say we're all in the same boat and puzzled. And if we had more information, we could try to manage our monitoring differently. And again, this is one of the reasons why I was asked to speak, I think, in the sense that if we knew where locations were of the transmission, we could set up before, during, and try to provide some actual data on the impact and be able to connect with other surveyors in the area that are experiencing similar interference problems. So again, knowing those locations and being able to establish equipment that would be able to detect it and track it, I think is, what we're all seeking. And if it's to happen, I guess ideally we would hope that none of this would happen and we could go back to doing our main mission, but we'll see what happens. Thank you very much.
Thank you very much, Juliana. Oh, wait a minute, we have one more. Matt Higgins from Australia.
Hi, Julianne. I just wanted to ask, I didn't quite catch the bit about the spectrum analysis. It's possible to get cause receivers that have spectrum analysis in them. Are you actually using that type of receiver or not? Or is it just the raw GNSS data that's being analyzed?
I am not the one who's actually looking at the data, but my analyst this morning told me that they are using a spread spectrum analyzer. So I'm assuming that is something that comes with the equipment for these two setups, but I can verify that with him.
Yeah, thanks. So, yeah, I mean, Septentrio, for example, have analyzers built in, I think, is an option if you want it. So that's it'd be good to understand the capabilities you can buy off the shelf in that sense. So yeah, thank you.
Thank you again, Juliana. At this point, I note we have ended the morning session 2 minutes over, which constitutes a new world record. I congratulate the presenters and the board for their cogent and punctual and brief presentations, comments, and questions. Lunch, thank you. Admin.
Okay, everyone. So J.J. Miller here. I'm Just going to make some quick logistics comments. It is lunchtime. We have about an hour. It's not a lot of time, but it's buffet style. I want to emphasize that those working, so that means members, presenters, government representatives that are here working, lunch is going to be right across the hall. And so, please help yourselves. We are going to have a sidebar meeting. That's when you have a big meeting like we have, we need to have some side discussion. So there'll be a few people from Space Force, NASA, and Department of Transportation. We are going to be going to, after we grab our lunch, to the promenade room. You know who you are. It's up on the second floor. So let's grab our lunch and head there. And then the final, and Dr. Parkinson and Tim Murphy will be joining us. The final point that I want to make is apologies. This is the third meeting that we attempted to do virtual, and in-person plus virtual, not necessarily as smooth as we'd like every time. The first two meetings went very well. This time we had a new company. They might not have understood all of our requirements, but what we heard from Washington, D.C. is when we kicked off the meeting, the live stream was not active. They actually were sing on a different channel. Now that said, we all wanted the strong kickoff, but everything that was said is recorded. And so once the meeting is over, hour or so, will still be available. So just wanted to make sure everyone was aware of that, because we know there are people listening on the line right now that were quite frustrated, and it's a learning experience for us. We'll resolve that. And Jason Kim is posting all of the presentations. So by the end of the day, we should have the majority posted. So with that, I thank everyone for their
And we're live
morning.
henceforth, though, the rest of
Yeah,
the...
we are live
Okay,
now,
thanks.
and we'll double check for tomorrow. Yep. Thank you.
Matt?
Just a quick question, Jay. I think, were they saying we were going to take a photograph?
Thank you, Matt. I couldn't read my own notes here. I was scrambling at the end. As we file out, so the members, please go right in front of this hyperwall, this big TV screen. We are going to do a photo, because the one that we have up, we were all wearing masks and looked terrible. So we'll fix that for now.
So hustle.
to man it?
Yeah, no, just to move that.
Oh, yeah, yeah.
Physically.
Yeah, we can retape that. Let me see what we can do. All right. Let me first see. Excuse me. All right. Yeah, we didn't have to move it. Yeah. So Samuel, for that one, we're losing. So it should be fixed now. You want to undo the tape for this one? Undo it? Oh, I didn't have to move it at all. I was able to on Zoom. Still gotta. What do you want to do? That's fine. Yeah. Sure. I was just saying we need to not have an overlap of this because it takes up space. But I mean, it's a bad angle.
If it overlaps, it's
Yeah.
fine.
All right.
Just need to, the overlap is fine.
Yeah.
Like if we have these four in both shots, that's okay.
It seemed like just making sure everybody over here is represented. Yeah, so right now, this is the view of what we see on camera. It's not bad, but we'll put it back. Oh, yeah, yeah, yeah. I could stand right here.
Oh, there's no one sitting there. You can see up to the gentleman that's on that side of it.
Good? And then that side. Rocky start, obviously. But second day should be smooth. We hashed out everything.
This is the important day. The second day is mainly for the board members and the review.
So who has the recording?
Pardon me?
Who's recording? Are you all also recording him?
Not
It's
the
just the live one. So I don't know if we, well, through the stream, that if it
Yeah.
wasn't up and running, then it's not.
So the only thing that I would have noticed that is missing from this current setup is just JP's introduction.
Okay. It's completely missing?
It's on a separate file.
It's on a separate file. Can those two files be combined?
We would have to download both.
After this, if you all could download them, I'll edit it myself. I just need the two files. And I don't have to program it. So I'll go get a larger flash drive so that I can.
We're trying to give the actual members a chance to go first, because it sounded like some of them had to jump to the second. Buy some of it. Yeah. 2 tanks. I'm like, holy shit. It's fine.
sort of update you on the last couple of years, some of the accomplishments there. And then I'll get into the ITAR. Yeah, is that better? Okay. I don't know, let me see if this works here. Okay, so I'll start with the ICG, and next slide. This is the easy part, by the way. The ITAR piece is not my area of expertise, but I'm going to talk a little bit about that in just a minute. So, but I've been co-chairing one of the working groups in the ICG, and so I've been working this for quite a while, so pretty familiar with most of these issues. The ICG, this is just sort of the objectives, is pursuing a global navigation satellite system of systems to provide services that benefit users worldwide. We focus a lot on spectrum protection, interoperability, information dissemination, compatibility, all of those things that are important to the U.S. And we certainly have a leadership role in to the extent possible. Okay, so just briefly, our last meeting took place last month, 9 to 14 October in Abu Dhabi. It was held in a hybrid format. We had over 200 people participate. We had representatives from all 6 of the GNSS providers as well as other members and observers. We had a providers forum meeting. We had updates from all of the system providers. There was an applications and expert session, and we also had meetings of all 4 of the working groups under the ICG. Some of the important activities include interference detection and spectrum, or interference and spectrum protection. Within the ICG, we've conducted a number of interference detection and mitigation workshops. We're currently planning the 10th of those workshops. We've had them almost every year, I think with maybe the exception of 2020. So it's been going back for quite a while. We chair one of the task forces that organizes that under the Coast Guard Navigation Center. So they're very active in putting this together and sort of shaping the agenda for what we talk about. One of the things that in particular that we focused on recently is using AIS and ADS-B for interference detection. So was kind of one of the tasks, was to organize a workshop focused on those areas. We're tentatively planning to hold that next month in a hybrid format from the United Nations in Vienna. Also, related to spectrum, we certainly closely monitor the ITU and the WRC, especially with proposals related to RNSS spectrum. And we have a few experts who participate regularly who are really spectrum experts. And so they bring in input and areas of concern related to RNSS spectrum. So this is really another important aspect of what's discussed. And then we've also done some educational outreach focused on the importance of protecting GNSS spectrum. And we've done this through workshops targeted at spectrum regulators, basically trying to highlight how it is very important for all countries, not just GNSS providers, to be aware of spectrum concerns so that they don't end up with situations like we have with Legato in the US or other things of concern. So it's a pretty technical presentation, sort of a seminar that we've put together that lasts for about a day or a day and a half if we do the full seminar. And I think we've done it 4 or 5 times already around the world, and it's been, I think, very beneficial. Under interoperability and service standards, we have been working on developing some guidelines for providers to use as they develop their performance standards. And we've published a couple of recommended templates for how to do that. So this is something that the US has been pushing for in the ICG for more than 10 years, and it's finally really gotten a lot of traction. And so they continue to have monthly meetings focused on this. Also, international GNSS monitoring. We do have a trial project with the IGS. This has been ongoing for about 7 or 8 years, and it continues today as well. We haven't made as much progress here because of the pandemic, but it's still something that is discussed regularly within the ICG. And finally, under interoperability, we have interoperable time, which is focused on system time offsets. We're sort of trying to wrap that up and come up with some concrete recommendations there, but it's something that's been discussed for a number of years in the ICG. A few other topics that we discuss. Space service volume, this is a really big one for NASA, and thanks to NASA's leadership, especially Jim Miller and his team, for all the efforts in bringing this into the ICG. We have published a couple of booklets, well, 2 versions of the booklet, and they're working on a 3rd version. That booklet is available for download on the ICG portal. There's a lot of really technical, good information in there. And it's was prepared through one of the working groups, a subgroup that's chaired by NASA. As I said, they're working on a 3rd edition to this booklet. They're also doing some outreach efforts and focusing on what an interoperable space service volume would look like. And so a lot of good work here. Also, search and rescue has been discussed within the ICG. Again, focused on interoperability, given that we're moving toward a GNSS-based search and rescue system. So we're definitely having some discussions there within the ICG. And finally, we have a working group that's part of what they focus on is geodetic reference frames and interoperability with alignment of those reference frames. So those are some of the things that we're discussing in the ICG and what we've done over the last couple of years. I will also mention a couple of other things that have gained some traction within the ICG is the LEO systems that you're going to hear more about today. That was introduced into our working group that the U.S. chairs actually at this last meeting, kind of for the first time. But it's something that we're going to be looking at, and we're actually considering having a workshop with to include industry to kind of hear about all the different systems and what's going on and how see if there's things that within the ICG that we can focus on there that might be beneficial. And then the other one is authentication. We heard a lot about that at the last meeting that we had, and so that's something that we may consider expanding on within our working group. Okay, so that's all I had on the ICG. I can do questions, I guess, at the end. I'll jump into the next thing, which is, of course, ITAR. Again, I'm not an expert on this. This is really handled by another office within our department, and I don't really have actually a lot of insight into it, but I'm going to talk more about from a process perspective, just so that hopefully everybody's kind of on the same page. So real quick, I just want to highlight that our current Space Policy Directive 7, which is still active, highlights the ITAR regulations, and this is just not taken directly from the policy, but I do want to just point out that it is in the policy, and so it continues to be managed by both State Department under ITAR as well as Commerce Department under the Commerce Control List. So you can ignore the title on this chart. It's the wrong title, but it's this is basically the process for how these regulations work within the U.S. government. And the key here that I want to highlight is that there's really 2 separate tracks, and they're independent from each other. So on the left side, you have the ITAR, and then on the right side, you have Commerce, the process that's managed by Commerce under the EAR process. And so, the governance for these under ITAR, it's we have specific legislation that leads to the ITAR process, which is managed by State Department, and then under Commerce, on the right side is the Export Administration Act. And so items that are, if an item is on the ITAR list, then it's obviously not on the, handled by Commerce. But if it's not on the ITAR list, then it would move over to either be regulated by Commerce or it would not be on the list at all. So they're independent processes. So I think that's sort of the big takeaway from this chart. So I'm going to focus on the actual ITAR process here for this discussion because that's what State Department regulates. And this just highlights all of the different categories under the U.S. munitions list. And really for this discussion here, we should just be focusing on item number 11, which is the military electronics category. And I'll talk a little bit more about that here. So this is really this is how the process works. Basically, the State Department leads regular rolling reviews of all of the different categories, and sometimes several of them at a time. And this is an interagency process that involves Commerce, DOD, NASA, as well as other agencies. Of course, we work very closely with Commerce on this, but State has the final authority and really manages the ITAR process. So the way that it works is that you have advance notice of proposed rulemaking, or what we call an NOI, or which is issued or published initially. And so that's how you know when something is being reviewed, when one of these categories is being reviewed, is that there's a public announcement about that. And so for the Category 11 review, that NOI has already gone out and actually closed. But one thing I do want to highlight is that they did accept comments for a period of time, and that they closed that process, but they are still taking comments. So if there are additional comments that anybody wants to make, they can actually still be submitted. They may or may not get a response, but they will be looked at. And I think that's an important point to make here on this review process. Again, I mean, we can basically say this is what the rule that's under Category 11 that is specifically being reviewed, as we speak. And so I think probably most everybody has seen this or is familiar with this, but I just wanted to throw that up there.
I'm sorry, just for clarity.
Yeah.
Is this what they're proposing the standard to be? Or
No,
this is the
existing.
standard?
This is the existing one. This is what it says now.
Thank you.
Yeah.
Thank you.
Yeah. So this is being, I mean, I can't really talk a lot about where we are in the process other than to say that the initial review has started, and the notice of inquiry went out and the comment period closed. But again, there is an opportunity to make additional comments. And then we would move to the second phase, which would be notice of proposed rulemaking, which would then lead to a final rule. So we're basically in between the first and the second step here in the process is where we are right now.
I'm sorry, I have to ask again. What is proposed?
So basically the proposal is to review the existing rules. That's really all that's being proposed, is that there's going to be a review of the rules, and they're taking comments, or they've taken comments on
So if somebody
this
wanted
rule.
a standard other than the previous slide, they would submit that as a comment on either advanced or notice of proposed rulemaking.
Yes, correct. And one of the things I think that is most beneficial is really to hear, and this is something that I know Tim has been leading the discussion with industry, but I think what's most valuable is to hear about commercially available equipment and what's being done there. Because I listened in on the last meeting, there was a lot of discussion about what these companies are doing for the military and things like that, and that's not actually really very helpful for this discussion. What's more important is what's being done at the commercial level. And so I just wanted to highlight that. Yeah, comment.
Is information about the apparent effectiveness of the current rules interesting in this process? In other words, if we can show evidence that SERPAs are being deployed in Russia and China and
Yeah, I mean, that
places
certainly
like
could be
that.
helpful. Yeah.
Okay.
And could you specify how someone would get involved with this process rather than, searching the Federal Register and all? Is there a person at state, or are you the contact at state for this, or how do folks get connected?
I mean, I think the comments have to be submitted through the official, you have to go to the website and submit them.
Right, so could you provide a link to that?
Yeah, I can certainly find that and send that to you, sure.
Thank you.
Yeah.
Yeah.
Mm-hmm.
Thank you, Jeff. It's good to see you again.
Yeah.
This is appalling, It is totally appalling. This is a tail chase. By the time you get around to actually even reviewing the rules, industry in many other countries is going to be years ahead of us. And so is there someone in this process that is pushing back at the tremendous built-in lags? If you're a control engineer, a built-in lag is a prescription for instability. And this is a control system of sorts. And I'm not shooting you, because and for example, in this particular case, is this L-band GPS, or is that stricture that I'm looking at, does it apply more broadly? And if it does, it's already been violated all over the place. Yeah, I mean, if you look at Skylink or whatever, some of these other things, I'll guarantee you they're way, way, way down the road from this, and they're already deployed. So.
Yeah, and some of that would actually be good to hear in the comments that officially get submitted. I think that would be helpful to hear about some of these things.
But you would hope there would be expertise at the national level that would not have to go through this process. They already know that that's out there. And because if they're making the rules, it's incumbent on them to understand what the impacts are, or are they just some faceless bureaucracy and we can't ever figure out why they put the rules in the first place?
Oh, let me add, I'm no stranger to Title V here, like 5 decades. If there's a reason for it, can you go to an interim final rule on a particular topic?
Yeah.
Which is what they would do if it was an emergency.
Yeah. And I'm not an expert to know how long the process takes. I imagine that they could, if they needed to, they could move pretty quick. But I mean, I will say that this has, the fact that they participated in the meeting that was held a couple weeks ago is a good sign. That they're very interested in this topic, and it is being addressed. I can't really speak to how long.
Who is they?
The state office that's responsible for this. Yeah. So they are interested in engaging. They're looking for feedback. Again, that's helpful. And like I said, I can't speak to how long it's going to take. And I don't know all the ins and outs of actually how long it takes to do an approval and under normal circumstances and things like that. But yeah.
So the spaceborne GPS receivers got moved to EAR. How did that happen, and can we take anything from that?
Yeah, I mean, I don't know exactly the details of how that happened, but like I mentioned earlier, that once something gets removed from the ITAR list, it automatically goes over to the other list. So there was a review, and it was determined that it was no longer part of ITAR. I mean, ITAR is the most restrictive, and then of course Commerce is much less restrictive. So, but I don't, I mean, I can't comment on the details of how that happened exactly or how long that took.
I'd like to pick up on the line of questioning from my brother Parkinson. My guess is that in order to make a change, there has to be a case made. And so the comment process is the opportunity to make that case. Otherwise, it's not going to happen automatically or as a matter of self-propagation. So my question for Brad is, have you submitted comments?
I don't even know what the process is. You're absolutely, that's a great question. And if you expect somebody down in the bowels, and I bet there's some experts on certain manufacturers who also don't know what this process is. They have no idea what this process is. And so in my judgment, there should be someone involved in this process that is looking at a self-inspection, that's looking at the reasonableness of what they're doing. But to me, this is so utterly insane in terms of the state of the art, in terms of what's out there and everything else. It is certainly not helping our military in any way that I can see, and I can give you chapter and verse on that. So who the hell put it in, and why did they put it in there, and why isn't someone automatically taking it out? So I understand that you want me to get involved in that process. The chances of that happening are not great. They're very small. Yeah, but you're absolutely right. I am not, as an engineer, outfitted to do things like that, but I'm looking for you to help me.
Brad,
Let me see if I can shed some light here. In an earlier slide, there's a periodic review by category.
Yep.
So this thing came up just because it was time for the periodic review. There wasn't a demand signal to raise this and evaluate it.
Correct.
Had that review not come up, when would this ever have happened?
Yeah, well, it would have been part of the periodic reviews, however long that is. I don't know how often they do that. Again,
So
they
we
look
just
at, I
happened to
think,
hit the period where it's under review.
Yeah.
Serendipitously.
I think so. I think so. I mean, I'm again, I can try to find out like how the process works if there are specific ways to raise this, but that's.
Well, who's on? Thank you, whoever that was. We didn't bring you here to be the javelin catcher on a track team. All right. There's obviously an issue here.
Well, I think yeah, there is. I think the big thing is that this is an opportunity to do it right now, so we should try to take advantage the best we can.
That would be apparent, yes.
Yeah.
Real quick, Jeff, could you try to find out what the period is of that periodic review? What is it?
Like how often?
Yeah.
Yeah, I can inquire. Yeah, sure.
Thanks.
Yeah.
Did you mean what is the deadline for submitting comments?
No, is it
No.
annual, decade,
Yeah.
century, something?
Yeah, we don't know when this train's coming by again. Yeah.
Actually, the history of that came up in the fact-finding meetings, and these are not that old, right? They only go back to 2015 or something like that. The problem is there's been kind of a revolution since then in electronics, and there wasn't a lot of commercial demand for these things back when they had to be done with discrete phase shifters in an analog fashion. The advent of very, very powerful digital processing elements and software-defined radios has lowered the cost of this so that now it's a viability for civil applications. So you wouldn't have got a lot of comments back in the 2015 from companies that were chomping at the bit to do surface for civil because their perception was probably there's no market, and they were probably right. But I think we're seeing now, evident by the fact that we have at least one U.S. manufacturer that has gone forward and gotten a TSO on a receiver or on a SERPA for aviation applications, that there's interest in civil applications. The problem is that company doesn't know how they're going to deal with ITAR. They built a product, but they can't export it, and I'm not sure they fully appreciate the ramifications of having an ITAR part on an airplane. I mean, when you put an ITAR part on an airplane, the airplane becomes ITAR. And that's not something that the typical operator could deal with. So,
Anybody else have any cathartic statements?
I'm just
Matt?
wondering, in fairness.
Hang on, we have international.
Sorry, I was just going to say, in fairness to Jeff, should we perhaps get the more expert person in state at the next meeting?
Only I can say is they're reluctant to participate.
Okay.
Well, under
okay,
our,
all right, I'll withdraw the question.
But we
under our
did
committee
actually ask.
structure, we can do more fact-finding on this, which is probably where we ought to head. JJ?
Yeah, I know we're wrapping up time-wise, but I just want to personally say thank you to Jeff. This is not his regular area of expertise, and yet he worked with Tim Murphy and actually got the top State Department reps to have a pretty in-depth discussion. And I must have asked 3 times for them to come and brief this group, and we've been successful with the FCC, right? We've gotten commissioners in here, and we've had some others that we may not agree with, but this is the place that we're supposed to lay things out. So I'll continue to work with Jeff and see if for the spring meeting in DC that we could get, some of the reps here. But let's not waste all that time in between now and then. Let's keep pushing and make sure they understand what the interest of the advisory board is.
Yeah, we can continue fact-finding.
Yeah, and maybe there will be some progress too between now and then on this whole process, so.
I did have one last question on your previous slides regarding the, I see, don't worry about it. You were talking about the outreach meetings that are being held.
Yeah.
You don't, yeah, but is FCC there?
They have not been directly involved.
Thank you.
Yep.
Say a law and order, no.
Okay.
Okay, next up, we have Barbara Baker, Deputy Program Executive Officer for MILCON and PNT at Space Systems Command, going to give us an update. Thank you for being here, Barbara.
Yes, sir. Thank you all. Thank you all for letting me come. I was asked to talk a little bit from the Space Force side as we're acquiring some of the PNT capability. What's the latest status on the Enterprise? But some of the conversations we had earlier really resonated me. Honorable Shane, when you were talking about who's the entity, the one entity for PNT that's seen it, because we were just having a sideline conversation. We have so many different departments and organizations that are represented, but who's really the one person that gets to say, like, this is what we're doing for a Department of Defense, or it's not even Department of Defense, see, I'm speaking from a Department of Defense person. Here's what we're doing from a PNT perspective. So when I keep hearing the conversations, it's interesting because in my small little hole that I live in Department of Defense, we look to something that was recently published, which was the National Security Policy. And in that National Security Policy, and while I was like listening to the other conversations, I was scrolling through it because I was like, the thing that's really missing from that, if you want to talk about, especially like in the Department of Defense, when we're trying to prioritize resources, and General Gutlein had shared a little bit of this at our DOT summit, was when you're trying to bring the interests of the civils into the forefront and you're weighing it against warfighter requirements, and we've got a national security policy that isn't loud. It's very loud on some areas. It is not loud on PNT. So when we talk about where resources are getting prioritized, and I sit and I hear this forum and I hear everything everyone's saying, and it's like, I'm resonating with it. And then I go back to my little hole in DOD, and it's like, nuclear deterrence and allied partnerships and missile warning, missile track, missile defense. And I don't hear anything about PNT. That gets silenced in like the rack and stack of priorities against the warfighter. And it's like, I hear you. So I'm gonna just be talking about PNT from the acquirer of what we're building, but I can absolutely resonate with the sort of concerns or comments that have been brought forward, because when we look from a warfighter perspective, the thing we're always looking at is like on the military code side and anti-jam. So if you go to the next slide, what I will be, actually 2 slides, is talking a little bit about the constellation, because we are putting up the constellation for the signal in space that's being projected. And where we're at, we're getting ready to do another GPS-3 launch coming up in the new year. It's like, I can't believe we're almost over 2022 and it's gonna be 2023. So that will get us to 6 GPS-3s. And where our signal in space performance is at today. I mean, we're talking, what is that, 17 inches? I mean, like, it's crazy. I got the opportunity, y'all, and let me speak at the GPS JNC conference. I was down in San Diego. And I was like, look, when, I have family or friends or whatever, and they're like, why did my user equipment take me down, drop me off at a different location? And I'm like, I'm sorry, that's your user equipment. Like, look at our performance in space, our signal performance in space. It's pretty incredible. Next slide. So GPS modernization, like I feel like when I get asked to talk about this, I'm like, I'm not trying to preach to the experts of PNT in the world, but just so we could talk about the capabilities that are coming on with like the different iterations. So we are now finishing up, we're about to finish up the last GPS-3 Vehicle 10 in production. Having been on that program a while ago, it's like heartening to see that production line ending, and we're in the development piece for GPS-3F. So you can see with GPS, so all the 2Fs are launched. We've got vehicles in the barn for GPS-3, but what you're getting from that is higher anti-jam, higher accuracy. You're getting a civil signal, the force civil signal, L1C, that's out there. You're getting longer life on the vehicle. And then with GPS-3F is gonna get you is regional. So we have higher anti-jam at a worldwide level, and at a regional level with GPS-3F, you're gonna get regional military protect. So a more narrowed spot beam for military code. I know for civil community, when we talk about a surety of signal, it's not on our civil signals, it's on our M-code signal, that anti-jam. You're also getting, I saw someone talking earlier about the search and rescue. We're adding a search and rescue payload, we're adding a laser retroflector array, and then something that's always been on this program, the nuclear detonation detection system payload is going through a redesign, and so that redesigned payload will be on. We call it GPS-3F Vehicle 11, not to confuse anyone, but we decided not to restart the numbering, so it goes GPS-3 1 through 10, and then we renamed the numbering system when we started GPS-3F as Vehicle 11. So when you hear that, and we're like, we're at Vehicle 11, you're like, where's the last 1 through 10? So we just decided not to change out the numbering. And then, so part of the enterprise is space, and then you've got ground, and you've got users. So from a ground side, we've got the next generation operational control segment, OCX. It's getting ready through its final deliveries. That one is going to fly all the vehicles because of, for anyone that knows about OCX, the delays we had with OCX, we actually augmented the legacy system, which you see as the Architecture Evolution Plan, AEP. We upgraded that so that it could fly the GPS-3 vehicles in the constellation using the legacy signals. And so that is flying GPS-3s. So although we launched the GPS-3s off with OCX Block 0, yes, OCX is actually launching and checking out the GPS-3s, we fly it operationally using AEP through this thing called contingency operations. But what we also did is we brought online what we called M-code early use. So we again augmented AEP, and so we are monitoring, mission tasking, planning, the M-code signal out there today. So when we talk about the enterprise, part of that needs to be talked about that, we do have that capability from the ground today with the 2 RMs, the 2 Fs, And because of GPS-3 with the 5th vehicle, we have a full constellation of 24 M-code vehicles that we're being able to manage from the ground. And then as part of the user piece of it, we build the user card that goes into user equipments for all the various different users. And that user card, the aviation card, we've got aviation, maritime, and ground. So that's being done with MGE Inc. 1, and then Inc. 2 is doing a handheld one. We've got the ground card that has been certified and is ready to be bought, and vendors out there, and we're finishing up the final testing of the aviation and maritime cards. Next slide. So from an enterprise roadmap, I just assume you all know this roadmap because it really is an eye chart. But what I'm trying to signal in here is when you're trying to synchronize space, user, and ground for capability, what it's really showing is what we just, 24 M-code vehicles up there. We've got, with Vehicle 6 that is coming up on the, in January of 2023, we'll have finally the sort of IOC version of L5, the safety of life signal. So as each vehicle comes online, we're not only bringing on M-code, but we're bringing in the rest of the civil signals that are coming into form. You see where there is, first swim lane is capability, second one is space systems, third one is control systems. If you look a couple lines below, you'll see something that's called M-code early use, OA. We had a chart in here that was circled. Unfortunately, I think we got our configuration control a little off-kiltered. So I was trying to draw the line of between GPS 3, Vehicle 5, between M-code early use, and then you got to get down to the other swim lane for the user equipment. We've now been talking to the various different services about it is time to start building in your user equipment to be able to use M-code. And part of our, so much reliance on PY has been the limited use of being able to do M-code testing because we're still relying on PY, and it's like we're finally getting to the point in the architecture where we can talk about M-code is here, it's now for us to start migrating off of it. Next slide. So I'm going to talk, I get it, military, Department of Defense, sorry, I'm going to talk about civil as well. But this one is really talking about the benefits of military code. So we were talking about anti-jam earlier. And what this is basically trying to do is as we build up more capability for anti-jam in our military signals, how close it allows you to get to a jammer that's out there. And so with our 2 RMs and our 2F vehicles, gets you to a certain level. We've got GPS 3 coming online, especially with Boosted M, and then the Regional Military Protect with GPS 3F. That's where we are today in our architecture. And then I know people in this organization, to include Tom Powell, continues to work on activities of what else can we do? What else can we do for more resiliency in any of our signals, more resiliency and anti-jam capability, that's outside of making an adjustment to the space vehicles. Next slide. And then this one is about the civil signals. And so many of you had already talked about the signals like, L1 that's out there legacy, L2C that's fully employed, what we call, full operating capability. L5 that I had mentioned with the next GPS 3 Vehicle 6 will be the sort of IOC level value, 18 vehicles I believe it is. And then L1C, which needs a number of GPS 3Fs to get you to the initial operating capability for L1C. Next slide. OCX. So previously we were talking about, I was telling people I still wear this, but I feel like although I think we have 100 of these in circulation, OCX 2022, the year of OCX, I'm the only one wearing it, and so really I'm trying to be like an army of one or something. I need more people wearing this so it would actually become true. But we uncovered a couple of issues this summer that set us back a little bit, and so we were earing towards delivery. We call it, system delivery at the ground segment, because then the government needs to take it and do a bunch of testing to integrate it with the space and user, and that series of testing of development and operational testing was going to continue us through 2023. We see that the delay of OCX is going to take us probably until the summer time frame, And then we'll have a better idea once we get through. So first off, all the hardware is deployed on OCX, excluding our classified environment at the alternate master control station. Everything else deployed, 17 worldwide monitoring stations, the master control station, the alternate master control station, the legacy ground antennas have been retrofitted. So we've got that delivered. What we're trying to do is finish up the qualification testing on the software. And once we finish up the software qualification testing, we'll have a better idea of what the back end of the program looks like. But right now, we're targeting for what we would call ready to transition to operations in the fall timeframe of 2023. And that's when we'll turn over the operators for an operational decision to transfer the legacy the constellation from the legacy ground system onto OCX. Next slide. And then OCX 3F, just like we needed OCX to launch and check out GPS 3 vehicles, we need OCX 3F to launch and check out GPS 3F vehicles and also to fly those vehicles operationally. So it's a smaller program. It's like a 20% modification to the OCX baseline. And then they're targeting to be in sync with the GPS 3 vehicle launch. And so operational acceptance needs the ground and the space vehicle to have been launched in order to operationally accept it. Next slide. GPS 3s, we talked about vehicle 6, bunch of vehicles in storage. We're getting ready to finish up vehicle 10. Next slide. 3Fs bring on all that capability we had talked about on the modernization slide. They have gotten forward with their milestone C back in 2020, and then they've been building up their flight boxes for what they call their GPS non-flight satellite test beds, kind of like their Ironbird, and then they'll be doing qualification of all their flight boxes and then starting to integrate that vehicle. Next slide. And then user equipment, we talked about the ground card having been sort of certified in 2022, earlier this year. Time is flying by. I can't even believe we're talking, it's almost December. So in 2022, the ground card's been certified. The Raytheon, who's the contractor who is doing our maritime and aviation card, finally delivered their last software drop that was supposed to resolve a bunch of deficiencies that they had with requirements. They've got 2% of the requirements left to sell off, and then they'll be able to go through final testing onto the platforms that they're doing, the B-2 and the Arleigh destroyer. And then MGE Inc. 2 is the smaller feature size. They have to get a new foundry established. They're going to a 14 nanometer feature size. Can't quite get it that small. And then they're gonna also integrate that into a handheld user equipment to prove that out. And I think that's all I have for an enterprise approach, unless anyone else has a question about the enterprise.
Yeah.
Yes, sir.
Yeah, thank you very much. That was a good rundown here. Connecting to the discussion we had earlier, what exactly is the Joint Program Office's role in addressing antennas to be used with the user equipment overall? Because that's a huge additional factor in providing signal protection overall. Is that something that's in your job jar, or is somebody else expected to worry about the antennas?
Yeah, no, so it's not in our job jar. We are in charge of building up the receiver card that gets integrated into the various different platforms. And so, you know, who that end user is and what platform and what sort of form factor they need is outside of us, and we leave that to the services.
Okay, thank you.
Just a two-part question. One, just as a point of clarification, the enterprise roadmap slide looked like it appeared that FY '24 and '25 did not have a new satellite being launched, but then I thought in the slide after.
Whoever's controlling the slides, if you can go to the roadmap. I believe that one is showing initial launch capability. So that's when the system is available to be launched, but not the actual launch manifest date.
So the second part of the question, obviously we're seeing other nations launch new GNSS satellites at a much more rapid pace. Is there discussion about speeding up that timeline?
So there is discussion. So I'm going to go back to my opening comment that says when you look at it from a Department of Defense and who's doing national security space launches, and we look at PNT as not GPS, not being the only vehicles on the launch manifest, it does get out-prioritized. And so it's through advocacy that potentially they are looking at moving some of the GPS 3 vehicles to the left because they are sitting in storage. but that becomes at a much higher level that at Space Systems Command we do not control. But also, it's about prioritizing the grander mission. So when I cite back to the national security policy, and like one of the things, I had actually like written it down because I just thought, you know, it's like 3 big things that they focus on. And so I think it was this gentleman over here that was talking about, you know, we need to invest in people and we need to invest in education. So one of those that's called out is investing in the underlying sources and tools of American power and influence. But that was all about like education and innovation. And then the second one was building a strong coalition to enhance our collective influence. And at least at Space Systems Command, we have a huge presence of like trying to get international partnerships going on, but like that is a theme across the Space Force. But that third piece is modernize and strengthen our military so that it's equipped for the era of strategic competition with major powers. And so I'm just saying that when we talk within the Department of Defense and we have a Secretary of the Air Force that's like, China, China, China is my threat, missile warning, missile track, missile defense, that's where we see when we're looking at the launch manifest where the priorities shake out, because we have such a robust constellation of GPS vehicles. Although fragile, we have a robust constellation. It tends to not have as much of a voice when prioritizing launches. Yes, sir.
Early on, when you were talking about GPS-3, you talked about increased anti-jam and increased accuracy.
Yes,
so
sir.
that's just for military folks, right?
Yes,
Not
sir.
for civilians.
It is.
Okay.
Any others? Yes, sir.
Thank you, Barbara. So, so just a quick note, I really appreciate you having the LRAs up there and then the search and rescue, and then we take it for granted now, but you know, there are those of us in the room, it took 7 years, right, to get an approval to get retroflectors on, and we had to go to the DepSec PNT Executive Committee 3 times. And then DOD realized, or some in DOD realized, that this is not just a civil request, this is to maintain U.S. technological leadership, right? Because every other PNT service provider was going to be equipping. One thing I'd like to see up here in the future, because I think you agree, is the importance of the space service volume, right? That continues to get more attention. General Thompson, DT, was our champion. I know Dr. Parkinson also you know, worked that issue in some other related organizations. And SPD 7 explicitly calls out NASA to develop requirements for civil space users. And that means taking the space service volume, which now ends at GEO, and taking it into cislunar space. So everything that we do is intended to benefit not just NASA, but our agency partners and the civil sector, the commercial sector. So any updates on any space service volume enhancements?
Nothing that's planned right now, other than what's being provided now. There's no new additional requirements planned. So what's interesting about the modernization architecture, and it's something that we've been doing at Space Systems Command, you may have heard of these force designs, is basically our CSO said, I really like the way that we plan out the architecture that we did for our space control architectures. And so he has directed that organization, and the priority first was on missile warning, missile defense. The second priority was on the space data transport layer, which is with my other hat, Milcom side of the house. And then the third one that's just kicking off right now, unfortunately, is on NAVWAR, force design. So when we talk about GPS, it's like, oh, GPS, force design, let's have our civil partners. And they said, no, the scope of it was very narrowed to be force design. So although we're waiting for that force design to enforce any pivot that we need to do with the GPS modernization to include augmentation, multi-GNSS, it is still focused on NAVWAR. Okay?
Any other comments? Thank you very much, Barbara. Appreciate it.
Yes, you did. Okay, so
The Ohio State University.
that was, what I was about to correct that, but you beat me to it. Well, thank you for the invitation. It's an honor and a pleasure to be here. And I will talk today, hopefully convince you why I'm not afraid of the jammer and how we can navigate from the stars. So here is what I'm not here to talk about. I'm not here to talk about GNSS, RFI, or radio frequency interference threats. You probably know more than I do. I'm also not here to talk about the various reports that have come over the past few years from the International Civil Aviation Organization, several memorandums, the Volpe report, the NIST report, and this past summer, the ITU, the International Telecommunication Union, calling for immediate action for GNSS radio frequency interference. What I'm here to talk about is that the truth is out there. The signals are out there. If you are a fan of the X-Files, maybe that will bring some good memories. So what I mean is that we live in this radio frequency-rich world where we have signals that we can leverage, we can exploit for navigation opportunistically or non-collaboratively, ranging from terrestrial. So we have a bunch of different terrestrial transmitters. The most fruitful, according to our studies, are cellular, 4G and 5G, or they are coming from the stars, from Iridium, Orbcom constellations, or mega constellations, and that's what I will be talking about later, specifically Starlink signals. So first, I will show you some experimental results that we had conducted in NavFest, where we showed, to our knowledge, the first successful demonstration of highly accurate navigation in a GPS intentionally jammed environment simply by listening to cellular towers. So this work just appeared in July of 2022 on the cover of the IEEE Aerospace and Electronic Systems magazine, and I think it would be very informative to show you a video of what we had done. So basically, we were invited by our collaborators at Edwards to NavFest, where we drove a vehicle, and the idea was, can we listen to cellular towers that are within the jammed environment? So that's us, by the way, driving just before sunset to Edwards, and navigate the vehicle with no GPS altogether. So this is the vehicle with all of the hardware that we equipped it with. This is our software that we call Matrix, which is a cognitive software-defined radio. Those are the different cellular towers that we managed to exploit and navigate our vehicle. And what you will see here are the two of the jammers that the Air Force had set up. They were, probably you know about NavFest, transmitting different waveforms. The jamming to signal ratio could be as high as 90 dBs. It's basically enough to knock GPS, and that's the whole point, is these towers supposedly rely on GPS somehow, and the idea is, can we still navigate with them? So far, so good. They didn't start firing up the jammers. We are driving. You see the ground truth from a GNSS IMU system. They were not jamming all GNSS constellations. This is how we get the ground truth. When they fired up that jammers, this is what my iPhone was showing. The blue dot was jumping up and down like it's possessed by the devil. It didn't know where it is. And what you start seeing, a GPS IMU solution starts drifting away. Now it's an unaided IMU, whereas in blue, what you were seeing there is how we can navigate just with LTE. And those are the towers. Pay attention to this guy down here, which is more than 30 kilometers away. And we are still able to listen to its signal and navigate it to an accuracy of about 2.6 meters for about 3.5 kilometers. So the next question that we kind of put to rest, which we've been asked over the years, is can you navigate high-altitude aircraft with terrestrial towers or terrestrial signals of opportunity? So basically, we are not the first to look at LTE, but to date, we achieved the most accurate results. So essentially, I don't know if we can play the video here. Oh, okay, so there was supposed to be a video. The idea is you will see a UAV navigating to a sub-meter level accuracy just by listening to LTE towers. Now, for those of you that are interested in high-altitude aircraft and aviation in particular, well, can we get the signals up there? So we collaborated with the Air Force on a mission that they called SNIFFER, Signals of Opportunity Navigation in Frequency Forbidden Environments. That's what it stands for. And the idea is, well, how high can these signals go? How usable are they? And from how far away towers can we get them? So we conducted the experiments just before COVID hit. Essentially, It was supposed to be over 2 weeks. 1 week was supposed to cover this region in Southern California. The other week was supposed to be over the ocean. When COVID hit, they canceled the second week. But with the data we captured from the first week, we managed to get some phenomenal results. So you can see here several of the aircraft trajectories that were performed, basically revisiting also the same region to see repeatability and so forth. So essentially, we flew in a rural region, that's over Edwards Air Force Base, and a semi-urban, that's in Palmdale, and finally in an urban region, which is over Riverside. So with our previous generation receiver, which, if you believe my word, we can navigate a UAV down to a sub-meter level accuracy with it, we were able to see a bunch of signals. I would say a dozen or so towers. We can listen to them. You are seeing here the carrier-to-noise ratio. This is at an altitude of about 1.7 kilometers above ground level. And then that's the Doppler, that's the pseudo range. So one of the nice things about these kind of studies is it pushes you to look for more. It pushes you to think outside the box and not just be satisfied with what you have, right? So we looked more into the 3GPP protocol. We looked more into different receiver design, improving receiver design for highly dynamic aircraft, which is what we are dealing with now compared to small drones. And I would advise you not to blink, because this is the number of towers that we were able to listen to at that altitude. So unique E-node Bs, they call them E-node Bs, those are the LTE towers, 120. And the stair chart down there, which is as a function of time, which is the trajectory of the aircraft, we are approaching about 100 E-node Bs simultaneously. So this is the maneuver, so we tested our receiver at one point we had even more than 100 E-node Bs simultaneously. No matter what the trajectory is, it's a grid, it's a teardrop, it is climbing, it's descending, it is a repeatable performance. And let me show you a quick video of the experiment. So those are the Air Force pilots that conducted the mission. That's Miss Mabel. They call her Miss Mabel. That's the C-12J that flew the mission. You see some of the antennas that we retrofitted in the aircraft. Those are the cellular antennas that we put at the bottom. This is the RF rack that was built by my students and in the lab. Shipped it to Holloman Air Force Base, put it on the aircraft, and started flying. So this is a snippet of the software-defined radio developed. You see here, images from the control room, and they are making sure they perform the maneuvers that we had requested. So we haven't mapped all 100+ towers in the environment. This is why you are not seeing all of them. We mapped enough to start generating a navigation solution that is pretty accurate. And as you see here, in green, this is the true trajectory of the aircraft. In red, this is the trajectory that we are estimating just from LTE and an altimeter. We are not even starting to use an IMU yet. And you can see here how accurate we are. In fact, I have another video that I will show shortly that shows more of these results. So let me actually play this one, because this one will show more of the navigation solution. That's what I was looking for. Okay. So this is what we are estimating based on these towers. What is fascinating is that we flew all the way up to 23,000 feet above ground level. We didn't fly higher, but all the way up to that altitude, we are still able to reliably acquire and track signals. Some of the towers that we acquired and tracked are more than 100 kilometers away. Now, my student swears that he believes one of those towers are by the beach, which is about 200 kilometers away. I said, until we really verify that, I'm not going to stand in front of the world and tell them that's the case. But he's a pretty smart guy. I think that's the case. So the signals we studied also, we have a whole paper that studied the signals in terms of multipath, in terms of performance, and the signals are beautiful up there. That's the message that I'm trying to get to. So what you are seeing here, this is one trajectory, 51 kilometers in 9 minutes. The position root mean squared error, the 3D position root mean squared error, just with LTE and an altimeter, was about 10.5 meters. So let me show you another region, and that is the semi-urban region. So what we also started doing is we can turn the problem on its head, and we can start mapping those towers as they show in and out from the environment. So we started doing what we call radio SLAM, radio simultaneous localization and mapping. A new tower shows up, we can map it, and we can welcome it to the team, and we can start navigating with it. So you can see here, in this case, we only managed to map 11 towers, but as I said, the signals that we have, the pseudo ranges that our receiver generated, was more than 100. So let me show you this maneuver, because I think it is pretty insightful. So note that the aircraft is going to perform what they call a touch and go, and notice how our estimate in green is following the onboard navigation solution that the Air Force provided us with, all the way as it touched on the runway and took off again. So we are pretty accurate there. And then finally, this is a hold pattern that they performed in Riverside, and in this case, also 55 kilometers, and we are still getting a pretty impressive performance from these terrestrial transmitters. Those are the Air Force pilots to whom we are very appreciative, and my students involved in this. So the next thing I want to talk about is navigation with mega constellation LEO satellites. There is a lot of hype and interest of how they will really blanket the Earth and shower it with signals that we could utilize for navigation. So the idea here is, well, what are the opportunities that these LEO constellations will offer us? Well, first of all, they are much closer to Earth than MEO, where GNSS satellites reside, so we would expect higher carrier-to-noise ratio. They are abundant, so in 2019, it was estimated that there were about 2,200 of them in low Earth orbit, and some predict that by 2029, there will be 57,000. Of course, these numbers keep changing because the new players are entering this new space race, so to speak. They are geometrically diverse, so that's attractive, and they also transmit in a wide swath of the spectrum, which makes jamming or makes the life of a jammer much harder, right? In fact, what I will show you later are results with Orbcomm, which transmit in the VHF band, and Starlink, which transmit all the way up in the KU band, right? So, and the approach that I'm gonna talk about is opportunistic. So in my world, they are free. Just like I exploited terrestrial transmitters, I'm gonna exploit what's coming from space without paying a dime, and in many instances without even the provider knowing what I'm doing with the signal until I reveal it to the world that, oh yeah, I've been using your signal, thank you very much. So of course there is no free lunch though, and the challenges, as an academic, I find them very exciting to tackle, and we've been tackling them systematically one by one. Well, first, they transmit mysterious signals. They don't necessarily tell you. They are not 3G, they don't abide by 3GPP. So we will have to build what we call cognitive receivers that can decipher what we care about and give us some navigation observables. They also don't necessarily transmit to us their ephemeris. So if you rely on TLE and standard propagators, you're talking about several kilometers in error that start building up. So we also have algorithms that track the satellites in space. Their clocks are not as synchronized as GPS, nor they are necessarily atomic. In fact, we conducted a study this past summer where we discovered that Orbcomm has a medium quality OCXO, and we proved that in a contrived way. If you're interested, we can chat offline. And also, they are transmitting in a large swath of the spectrum, so the ionospheric and tropospheric delays are going to be different for different satellites. So we are not the only people who are looking at LEO for PNT. And I can think of it as there are 3 schools of thought or 3 approaches that people are interested in. One is PNT dedicated LEO. So let me design a new constellation in LEO for PNT. Another one is let me augment GNSS with LEO, right? And get the best of both worlds, so to speak. And then there is the fully opportunistic LEO PNT. And that's what we are doing. So the signal, whoever launches a satellite, it starts transmitting, we are going to use their signal. So let me show you some of our results with Starlink now. So essentially, we revealed to the world about a year ago and caught everyone by surprise that we can actually exploit Starlink for positioning. And Science reported our work, IEEE Spectrum. And essentially what we did, we developed two different approaches. They are both opportunistic and cognitive. The first one looks at the carrier phase, and the other one is a blind Doppler estimation. What you are seeing here are the first time that we revealed the pilot tones that are transmitted by Starlink, and then the other one, it looks like, surprisingly, like a GPS acquisition, but this is how we turned it to be. We searched, we can find the Doppler, we can find, now the trick is you need to know the code, which they don't tell you, which we already had decoded. We estimate the code length and all that. So that's the acquisition. This is the tracking in both approaches, the blind Doppler versus the carrier phase. And then this is the moment of truth. In the first approach, our 2D error was about 7.7 meters, whereas in the other approach, it was about 10 meters. Okay, for a stationary receiver that we happen to put on the top of a parking structure in our old campus. So what we did after that, and this work was published in two different papers, is we improved our algorithm, our blind receiver, or we call it cognitive opportunistic navigation receiver. And without going into too many technical details, what we presented this past INGNSS in Denver was that if you, not only we can get pure tones, or which I prefer to call always on, because that's a term from 3GPP, there is what I call on-demand, or OFDM signals, that they beam, not necessarily all the time, but when they beam it, we can detect it, we can estimate the OFDM frame, and we can start navigating with them. So that's what you are seeing on the right and the left of the pure tones. This is the 5G spectrum. So another research direction in my lab is looking at 5G. But if you look at it carefully, you can start seeing the subcarriers. Now, the question is, what is the frame length of Starlink OFDM? They look very similar. What is it? In 5G, it is 10 milliseconds. In Starlink, it's 1.32 milliseconds. So, as I said, we presented this work in INGNSS. If you're interested, happy to talk later. We can get the frame, we can get a pseudo range, and we decoded the signal. Now, I should stress that unlike other approaches that came recently from UT Austin, we didn't reverse engineer the signal. In fact, it is a general theory that we successfully applied to Starlink, Orbcomm, Globalstar, GPS, and 5G, and we are able to reconstruct what different providers are transmitting. So what you are seeing here are 6 Starlink satellites that are flying over us. We were in Southern California at the time. And what we discovered was, of the 6, the first one was transmitting OFDM. The second one was not. It's only pilot. This one was transmitting OFDM. This one was not. And this one was. So it's the same data that we produced the first results with. We just ran them into the new beefed up receiver, if you will. And once we did that, we managed to reduce our error from 10 meters down to 6.5 meters, because now we have larger bandwidth we are dealing with. And if you are curious, our initial estimate was 179 kilometers away, and we zoomed down to about 6.5 meters. So the next thing I want to talk about is, well, how can we do this by, on a mobile platform? So this is something that we also had done. It appeared in on the cover of Inside GNSS last December. And then this work also, for the past 4 months running, has been the most downloaded paper in the history of IEEE transactions on aerospace and electronic systems. I think it's kind of cool to see a ground vehicle. And sorry for the mix-up here with the colors. It's because of the change of technology. But what you are seeing here is the cognitive receiver that I mentioned earlier. We use 2 Orbcomm, 1 Iridium, and 3 Starlink. We cut GPS. The total distance was 4.15 kilometers. We traveled 1.82 kilometers with no GPS. From that point onwards, what you are seeing in red, this is the unaided IMU. It starts drifting away as one would expect. Whereas in green, you are seeing what we can do by, there are several layers of complexity here. One, we are tracking the satellites in space. So we are doing something that we call STAN, simultaneous tracking and navigation. We simultaneously track the satellite in space, aid the IMU with observables we are getting from these satellites, and estimating our vehicle's state. And that's what you are seeing. So, the position RMSE was 18.43 meters with signals that we technically don't know what they are, and with satellites that we have an error on the order of several kilometers of where they are. So you may say, well, this is not enough. I'm not gonna fly in a plane with such an error or drive in a car with such error. So we generated this simulation study conducted a simulation study where I said, okay, when Starlink has all of its constellation up there, so I call it the granddaddy of mega constellations, they will have the most. So at one point, we should be able to see above us in Irvine, California, 74 Starlink satellites. And if you use them through the framework I showed you earlier, what I can promise you is if you are getting Doppler only, then over a trajectory of 12.28 kilometers of an aircraft, your position root mean squared error will be 10.63 meters. So this is just with an altimeter because of the bad vertical geometry and and an IMU and the Doppler that I'm extracting from Starlink. If you get pseudo ranges, which recently we can because of the OFDM I showed you earlier, you bring it down to 7.31 meters. So there is something that I think is pretty fascinating. I'm not the biggest fan of machine learning, but I realize it has its time and space because it is showing some tremendous promise in the form of improving our ephemeris estimation and tracking of satellites. So this is the framework that we started working on recently, where imagine you have a base, a ground station, that listens to a satellite as it passes. So if you do the old SGP4 TLE and then SGP4 type propagation, the errors will accumulate and you will have errors. And those are experimental results. This is for ORBCOMM. The reason I know that this is an error, ORBCOMM is one of the few constellations that actually transmits its ephemeris to you in the downlink signal. So we decoded that and then we compared our estimate versus ORBCOMM's, what it's telling us. So yes, you are seeing here errors hovering around 1 kilometer, okay? So you start tracking the satellite with the measurements that our receiver is producing, kind of closing the loop there, and you're seeing how we are reducing that error to about 50 meters. Now, the satellite leaves, and at that point, your best bet is to do an open loop propagation. So what we did was we took this time history, we designed a neural network, we gave it both time histories, and we said that when the satellite comes back, I want you to tell me where the satellite is instead of doing a TLE plus SGP4 or some sort of a propagator, okay? So let me show you what we were able to achieve here. So we had, I would say, planned the experiment so that the same two satellites that appeared the first time that we tracked, when they appeared the second time, we have a vehicle that will start using the machine learning's estimated ephemeris, plus signals coming from these two LEO satellites to aid its IMU so that when we cut GPS, which is what you will see right about here, we'll see how well we can navigate. So in red, this is the GNSS IMU. Once again, it's unaided IMU, it starts drifting. In green, this is the LEO plus IMU where we are aiding the ephemeris prediction with machine learning. So we go from the final error, 235.5 meters over about 870 meter trajectory down to 8.2 with only 2 LEO satellites. So the last thing I will talk about, I know there is some interest in this community in differential navigation. So this is something that we had done where another way to compensate for the large ephemeris error is to have a differential network. So we set up, and this is with Starlink, those are experimental results. We set up a base and a rover that are 1 kilometer away. They are both listening to the same Starlink satellites. They are getting from the receivers that we designed, getting the observables, and then the base is sending to the rover, it's observable. Well, the rover in this case was stationary, and it's differencing them and trying to, without doing any machine learning, without compensating for doing any fancy error, ephemeris correction. We started the initial estimate 200 kilometers away. I don't know, it looks like Catalina Island somewhere. Maybe that's where my student picked it. Ultimately, we brought this down to 5.6 meters with 3 Starlink satellites. So the question is, well, how about when you have more Starlink satellites? Well, this is a simulation that my students conducted with 44 Starlink LEO. If you fly this aircraft in this figure 8, we can predict sub-meter level accuracy. So with that, I appreciate you giving me the time to share some of our results. Hopefully, it gave us some hope about what we can achieve. And very importantly, I would like to acknowledge the various funding agencies that funded this work. It's been for several years. Most recently, the Department of Transportation through the Carmen University Transportation Center had really propelled our research forward and guided us to go squarely at this problem and offer these concrete solutions. So thank you so much, and I'm happy to take your questions.
Thank you, Zach. Terry first.
Isaac, great work and fantastic presentation as always. I guess it's a two-part question I've got really, and depending on the answer to the first one, I'll modify the second question. Was that data all just recorded and then post-processed? Okay, so the second question is, so what are the, it looks incredibly intensive in terms of the computation, so what would be the reality of trying to move that into real-time processing?
That's a very loaded question. So let me answer it by asking you a question. Are you referring to the LEO or are you referring to the cellular?
Well, I would be interested in both.
Both.
So, yeah.
So the cellular, we were forced, you know, we are into prototyping more than developing a real-time product, right? I was in industry in my previous life, so I know how intense it is to produce a commercial grade product. When we worked with Edwards Air Force Base, we were forced to create something that is multi-channel and real-time. And I give credit to my students that worked hard because, first of all, we were not allowed to fly on these aircraft ourselves. So we had to create something for the pilots so that when they fly, it doesn't fail, right? And if it fails, then we really had wasted a whole flight, a whole day. So they worked very meticulously to creating something so we can get it in real time. That I can tell you about cellular. We haven't attempted this with LEO, but it is doable. Now, of course, it depends on the framework. If you are talking about, well, the machine learning, well, you'll have to have at least one pass, and then you have to go back and process. So that you can't do. You know, it's a neural network, so you need data to. But it is not. We don't have a supercomputer that is doing these things. So with good engineers, it can be turned into a real-time solution. Yeah. And in fact, I have one of my past students here, Dr. Joshua Morales, who had a very big role in the first 2 experiments that you saw. He actually was part of NAFFEST, he was part of Sniffer, and he actually had put a lot of blood and sweat into getting things in as real time as possible.
Thank you, Admiral, for giving me the floor. Fantastic presentation, very attractive and informative. And I would like to follow the thoughts of my colleague, Professor Terry Moore, asking about the computational capacity required. So especially for the perspective of perhaps the mass markets, in a simple question, how this stuff could use your results? Is it possible to distribute the position estimation process in the sense that some essentials will be done on smartphone and the rest on some cloud-based service or some other form of a distributed system?
Well, that would be absolutely fantastic if we have that capability. It will make our lives much easier in the sense that crowdsourcing becomes on the table. It becomes tracking these satellites from different places. It allows us also to start stitching the ephemeris. Now, I mean, it's kind of like taking a kid to the candy store. You know, what you told me, if you can make that reality, then I will be extremely happy. But to answer your question differently, so some of the challenges here, or some of the biggest challenges, if you really want to put it on your phone, are in the form of antennas. That will be one of the biggest bottlenecks. So it's a bit bulky how we do it. You know, we have software-defined radio, we have, you know, COTS that we use, and as I said, we are not in the process, we are really in the process of prototyping. One advantage of the way we started doing things as opposed to how it was done before is that we are taking the approach of utilizing, call it traditional or classic tracking loops. I'm sorry, I'm getting a little technical here, as much as we can, whereas we have a wrapper around because we are doing things, I would say, universally, right? So we don't want to have a different receiver for a different constellation every time they show up, or every time, if they change, right? They could, if tomorrow Starlink changes their code, then whatever is published or released by others will become obsolete. Whereas what we have is, in the feedback, we cognitively decipher whatever is getting transmitted, and we have classic common filter-based tracking loops, delay-locked loops, phase-locked loops, vector loops, and it is really at the core, but at the outside, call it the intelligence, is where we come up with, and this is where the algorithm, I know it's not as intensive computationally. Hardware can become a problem, especially from the antenna point of view.
Thank you very much.
You are very welcome.
Other questions, comments? Thank you very much. Appreciate it.
Thank you.
Next up is Patrick Shannon, founder and CEO of TransPoint. Thanks for being with us, Patrick. You're on.
Awesome. Well, good afternoon, and thank you very much for giving me an opportunity to talk to you guys a little bit today. Patrick Shannon, CEO and one of the founders of TrustPoint, and the title of the presentation is Leveraging LEO Satellites for Accurate and Reliable PNT, but I have a more specific subtitle, which is Less is More, in case we're going aggressively small. And while there's going to be a couple talks today about LEO PNT and LEO GNSS in particular, I think there's a couple of things at the next level down that are worth highlighting. Things that, in particular, TrustPoint is looking at, but not necessarily something that can't be applied to other LEO opportunities as well. So during this, I'll just give you 30 seconds on the company so you guys understand where these thoughts are coming from, a little bit of context for the speaker as well. Some goals. Why should we go off and do new cooperative LEO systems for PNT? And then I'm going to talk about small satellites, small orbits, and small waves. Some conclusions, and finally some recommendations. So first, TrustPoint. We were founded legally in 2020. Really got started late 2021. We are VC-backed with a blue-chip investor out of Silicon Valley. We have facilities both on the East and the West Coast doing slightly different functions, but we do have that bi-coastal presence. Team of about 10 right now. We do have a primarily commercial focus, 80-20, really reserving that last 20% for DoD, IC, and allied partners. And from a technology-focused standpoint, very much the satellite payloads, signal structures, and then the receiving side of that link, not necessarily the hardware, but definitely the firmware and software. And then a little bit on the applications there that we're going to be pursuing that we're trying to optimize for. The problems of GPS that TrustPoint's trying to solve, these are going to be familiar to everyone in the room. And in particular, what is the solution? And in our opinion, it's innovating on that space infrastructure layer with commercial satellites, specifically microsats, and on the signal layer, both the RF physical layer as well as the data within those messages. And we think if you do this correctly, you're going to be able to come out with something that is incredibly low cost, high performance, and inherently secure. All right, so what is the goal? Why should we go off and do something that we haven't already done, right? What's the purpose of providing all the effort necessary to go off and have a new infrastructure, new signal sets, right? And I think it comes down to 4 primary things. And there's a bunch of different ways you can cut the cake. But if I were to talk about 4 of them in particular, the first one is performance. And that can be accuracy, that can be availability, and that can be security and other things. There's probably a bunch of dimensions that can be grouped in there, but it's the general performance of the service. From the infrastructure side, it also needs to be scalable. And a lot of people like to attack scalable by going commercial, because you get to share in the investment and get to bank on that commercial market in the future. But that's only accessible as a feature for a commercial system if what you're proposing is scalable. And scalable means a first small bite, right? Something that is manageable, quick, and easy, so you can start learning and building momentum. They need to be logically extensible, right? It's not about going from 0 to 1 to 100. You need to have some plateaus in between. So you got to build a system and an architecture that can support that. And finally, when you get to your end state, it's got to be affordable. It can't be something that you bank on winning 80% of the market and being able to sustain a multi-billion-dollar annual OpEx or CapEx requirement. 2 other things, resilience and future-proofing. 2 other things that I think LEO is particularly in a fantastic place to support. On the resilience side, at least at TrustPoint, we break it into 3 parts: graceful degradation, flexibility, and responsiveness. Future-proofing, we don't know what the future holds, right? There are things we can't predict a couple years out, maybe 10 years out. Beyond that, we're not sure. We have to be able to build in kind of baked-in ability to be flexible. Best way to do that is with quick refresh and building an architecture that supports that. So with that said, if those are the goals, how do we get there, right? And this is where a potent trifecta comes in, right? And I'm not necessarily trying to be cute here. I'm trying to be memorable. Small satellites, small orbits, and small waves. And I'm going to go through each of these relatively quickly and talk about the features and benefits that come from that, but it's important to note they work really well together. It's not one of these providing incremental value with the others. There's actually a fantastic synergy between these 3. So first, on small satellites. And small satellites, a class of small satellites actually kind of starts somewhere maybe around 100 kilograms or 150 kilograms. I'm actually going to take it a lot smaller than that, right? What SDA is doing is actually a fairly large spacecraft. It's proliferated LEO. It's significantly more cost-effective and smaller than heritage systems in LEO. However, it's still relatively large, right? And so I'm talking 10-kilogram spacecraft, things on the order of a 6U CubeSat, if you're familiar with that particular form factor. It can be a little bit smaller, it can be a little bit bigger, but these are things that a single person could pick up and carry across a lab, individually integrate into a launch vehicle with one observer and one individual, very simple processes. The other thing is, when we start talking about the smallness, you still need a decent amount of power to do an RF broadcast mission, right? And so I'm saying classes of spacecraft at this size, but have up to 50 watts of orbital average power available to the payload. Now, if you can do something like this, what does it get you? Well, the first thing is it's just generally low cost, right? It's simple to integrate. It's quick to integrate. When you start talking about labor, there's a little bit of material, not a ton of material. And it is low cost, but how low cost? So one thing that TrustPoint has done recently is gone out and engaged kind of the known platform providers and a couple of new ones out there. We looked at 16 different platforms and racked and stacked them based on cost as well as orbital average power that they can provide to the payload. And you'll see some groupings on the right. Obviously, we have the pack leaders, and that's a really interesting one. In addition to identifying these, it's worth noting that these are relatively new platforms. In the last 3 years, there's been a lot more new companies come on board with new technologies in this class, but also the advancement of the technology just in general. The middle majority has kind of been where CubeSats have been for the past decade, maybe even the last 15 years. It's only been in the last 3 that we've been able to cut that cost on the order of 50% and increase the power available to the payload by 2 to 3x. And so the main takeaway here is we now have high-performing, precision-pointing CubeSats on the order of $200,000, potentially less than that at scale. When you start talking about proliferated LEO architecture, it becomes very affordable. Now, that low cost lets you do that scalable. That first satellite's pretty cheap. The next block of 10 is pretty cheap. In fact, if you want to deploy 100 of them, that's still relatively affordable. And so that's very, very interesting, very valuable to this play. It also allows you to have a lot of nodes, right? When we start talking about resilience, right, the number of targets you have to take down, losing 1 or 2 satellites, either due to your own fault, just end-of-life issues, or adversarial attacks, losing a few satellites is a small percentage of the overall system, small percentage of the overall service level. Also, we had some conversation earlier about GDOP, geometric dilution of precision. With a lot of nodes on orbit, you have a lot of satellites to choose from to optimize that particular factor in your solution. You also have plentiful supplier base, right? There's a lot more companies that can get started building these than can get started building 100-kilogram class spacecraft or 1,000-kilogram class spacecraft, right? That diverse supplier base, both here in the US and in allied nations, provides a great resilience to our supply chain. And the short build time is super important. And it's important for evolutionary design and development, right? Everyone's familiar with Moore's Law. Everyone likes to talk about iterative design and how fast you can progress technology when you build it, deploy it, test it, learn, and go back and start right over, right? It's that virtuous cycle of technology. If we look at a few quick case studies, cell phones in the last 20 years have improved dramatically. 15,000 times data rates, 16,000 times data storage, right? Now that all relates back to Moore's Law and the chip scale technologies, but it's a great example because these companies that were building these phones put out a new device every year or every other year, and the learning they're able to incorporate the new technologies, the tech refresh lends to that. Now we've also seen this quite a bit at the GNSS receiver level. Obviously, back in the 70s, they were pretty big and bulky. Early 90s, we started getting the first commercial receivers, still relatively expensive and short battery life. But today, we have some pretty high fidelity capabilities. Leading edge chips down to 7 nanometer silicon size, feature size, less than 10 milliwatts of power, over 100 tracking channels, pretty substantial in a tiny, very low cost package. It's not necessarily going to get you the type of precision you might need for some of the autonomous navigation applications that are out there, but it's really good for a lot of other things. And the thing to take away from this slide is these dynamics exist in phones and in user equipment, but they have not yet been applied to the infrastructure layer. And that's where LEO and CubeSats in particular allow us to take that dynamic and apply it to the space segment. Transitioning over to small orbits real quick. When I talk small orbits, I'm talking LEO. But I'm even talking a subset of LEO. If LEO generally is supposed to go up to about 2,000 kilometers altitude, I'm really interested in what I'd call moderate LEO, 500 to 800. And that's good for two reasons. It's easy to access, right? Low energy compared to trying to get to something higher. It's also got a pretty mild environment, and that's both for radiation as well as thermal. And so that's super important. Now what that set of orbits allows you to do is it allows you to get there pretty affordably, right? There's a lot of low-cost launch, a lot of rideshare opportunities to these orbits, and that becomes super important. It also allows you to use pretty simple spacecraft. The radiation tolerance requirements are pretty minimal. Your requirements for things like ACS thrusters to desaturate reaction wheels is no longer a thing. You can use magnetorquers. And so it keeps the cost of the satellite down by going to those orbits. And then, of course, you have low-cost deorbit. And this is super important, too, and this is relatively new. With the FCC's new guidance on having to dispose of your spacecraft in LEO 5 years after your mission completion, we now need to make sustainable orbits. And that's a big part of sustaining a system is keeping your own space clean. Now, to illustrate this a little bit better, I want to give a comparison between a satellite system that might be operating at about 700 kilometers and a system that might be operating closer to 1,000. And this is a set of back envelope calculations. We've done a lot more of this at Trust Point to find an ideal solution for some of our customers and some of our plans. But there's a lot of things that weigh in, right? We're talking higher radiation, 3 times as much radiation at that 1,000-kilometer altitude rather than down at the 600 to 700 range. You're going to need a larger power subsystem, generation as well as distribution and storage. If you're presuming that 1,000-kilometer system is going to provide a service out to the same elevation mask as that lower system, you're illuminating more of the Earth per spacecraft. You're also going to need more delta V, right? Whether that's delta V to get to where you're going after getting dropped off at a lower altitude or bringing the spacecraft back. And there's a big breakpoint right now in EP systems for CubeSats. There's small ones that can deliver 100, 125 meters per second of delta V, which is good for some station keeping, getting to your station initially, and then a deorbit from moderate LEO. There's far fewer propulsion systems in any sort of reasonable cost point for systems that can apply more than 150 meters per second, which is what you would need to do to lower a perigee from 1,000 kilometers down to about 400. Two last things here. You have to reserve, with this new FCC guidance, and I think this is the way sustainability is going to be going, you have to reserve some of your operational life to dispose of your spacecraft, right? And to that extent, that eats into the operational, or I guess the service life of the spacecraft. And it can be pretty material. Part of that is you're not necessarily going to be able to operate your payload while you're doing a deorbit burn with an EP system. They both share the power subsystem pretty substantially. And on top of that, if you're not in your orbit, you really shouldn't be operating your primary payload anyway. When you're down in moderate LEO, you can bring your perigee down to 400, maybe 350 relatively quickly, and then use drag to do the rest. And you don't need to spend a lot of time burning. Dropping a perigee from 1,000 down to maybe 400 kilometers with standard EP systems today takes months. And that's months off the service life of your spacecraft, which increases its effective cost because now you have to replenish it faster. And then finally, of course, higher launch cost if you're looking at going in and doing a direct inject. If you start stacking all those things together, you have a pretty big impact on your launch cost per satellite and your overall satellite cost by our calculus and the research we've done in the market to date. If you group those together, you're looking at a deployed satellite cost about 83% greater than what would have been in a more moderate LEO. Now, we can also compare this from a standpoint of the number of spacecraft you need. At a higher LEO, you don't need as many spacecraft, and that's why there's been quite a few papers to start looking at optimal orbits, and you start getting to that high LEO, 1,000-kilometer range pretty quickly mathematically before you take into account a lot of these other factors. And you do need about a third less spacecraft when you go up to about 1,000 kilometers versus a 700 or something thereabouts. However, it doesn't make up for it. There's still, by our calculus, a more expensive system when you go higher, and more importantly, it's going to take you longer to get there. Now, if you compare both of those to GPS, and it's not apples to apples, they're very different services. There's a lot different requirements on GPS that a commercial LEO system doesn't have to take into account or implement. But from a standpoint of an annualized system cost, you're looking at something that's about 40 times less. Right? Now, if you were just going to compare that to the civil services, maybe that's a better way of doing it. Maybe the civil services account for a third of the GPS system. You get a little closer, but it's still a quite drastic difference. And so your final result between the two LEOs is about a 20% difference, and with GPS, it's still an order of magnitude or more. Now, it's another thing worth noting, the 1,000 kilometers still looks pretty interesting, because building a lot of spacecraft is not easy. So if you can build a third less, maybe that helps you. But the reality is we don't quite yet have those technologies, and the few systems that are out there are not anywhere near production rate. So you're going to have a delay for R&D and a delay in schedule, and for a commercial company, that's lost opportunity cost. It sounds like, oh, another year of R&D, maybe that's a couple $1 million, but it's a year lost getting to market, which could be worth tens of millions or hundreds of millions over a period of a few years. Right? So that's a material cost that to some extent could dwarf the system cost when it comes down to it. So small orbits, those low costs, they help scalability. It's easy to have a lot of them. They help future-proofing. It's easy to take a new bite, refresh. You also have diverse launch opportunities. The recent market studies on the launch market, there's something like 150 funded suppliers or something today. About 2/3 of those are for LEO launching, small launch. We'll probably see 80% of those dry up or merge. However, that leaves quite a few companies to do that. So if you're looking for diversity in your launch services to support an architecture, this is a pretty interesting one. And there's also a geometry aspect that's super interesting. And on the next slide I'll show you, but the geometry in LEO allows for some higher performance characteristics, and it also supports some scalability. And how do we do that? So real quick here, when you're out in MEO and you're looking down at the Earth, you're going to see about 40% of the Earth, right? And when you have those higher, higher gain beams on the later Block 3 spacecraft for GPS, we're going to be able to decrease that effective service area for some of those signal sets. Being down LEO, you're not looking at 40% of the Earth. You're looking at a few percentage of the Earth, somewhere between 1 and maybe 6% of the Earth. What that allows you to do is cellularize the planets. The service you provide over North America does not have to be what you provide over Europe or what you provide over the maritime regions. It does not have to be what you provide over eastern Ukraine, the South China Sea, or the Taiwanese Straits. You can change the modulation schemes, the encryption keys, the frequencies, the transmit power to allow you to serve the needs of the customers in every geographic region in the way in which they can best be served. And it's a pretty low mod to the spacecraft to add that level of flexibility in a lot of cases. The other cool part about that, and this also comes into duty cycling of the spacecraft, is you don't need to roll out a global system to start. You can start with North America, maybe Europe. And if you run the math and do the STK simulations, you can actually support North America and Europe with a persistent coverage with only about a 25% duty cycle on your spacecraft primary payload, which means your requirements from a power standpoint are significantly less than a global service, but that's a material business. That's a scalable point in your business model that makes things like this a reality. Okay, so now small waves. Last category here. I'm really talking about higher frequencies. In particular, above L-band and not too high into X-band, right? And of course, there's some detractors in going higher. There's different atmospheric effects, ionospheric effects you have to account for. But there's also a lot of really good things. And those good things, in my opinion, make up for it. So first, you have compact user antennas. And this is super important. And if I can harken back real quick to Brad's talk earlier this morning about antennas, the size of an antenna is directly proportional to the wavelength of the frequency it's been designed to receive, right? SERPA antennas, which are a fantastic technology, and we should relax ITAR, and we should get those out into the markets, are great, but they're still pretty big and still pretty heavy. You're not going to put those in a cell phone. You're not going to put those in a small drone. You're pretty limited. I got 2 on here from our friends at Antcom, fantastic technology, 7-element. It's about 6 inches across and about a pound and a quarter or so. Smaller ones, 4 elements. It's down at about a half pound, still 3-4 inches wide. Again, you're not going to be incorporating that into a small IoT device or a small mobile phone. However, if you were to move from, say, L-band up to C-band, and there's been some foreign countries looking at building C-band systems. There's C-band allocations at the ITU for these types of services. So it's a good case study to look at. Your wavelength shrinks by about 2/3, right, down to about 6 centimeters. Now what that actually means is your size is reduced by 70% and your mass is reduced by 90%, because one of those relates primarily to an aerial ratio and the other one's overall to a density ratio, right? So now something that maybe could only really be incorporated in a car or a tank or a large aircraft can now be put in much smaller vehicles and much smaller devices. The other thing here, and I'm not quite sure what's going on there, it's a little hard to read, but the important fact is these types of antennas are important to the commercial sector, probably more so than the defense and intel sector. Your ability to handle jamming is important, but so is multipath. And there's way more users in Manhattan dealing with multipath than they are dealing with jamming today. The other thing is that they have some great opportunities to also allow for spectrum sharing. When you add controllability to the beams, your ability to not interfere with others in either adjacent beams or co-users within your own allocation goes up. And so there's some interesting things on the regulatory front that should be investigated at higher frequencies for that purpose. So compact user antennas. There's a corollary here with the spacecraft as well. Higher frequencies, smaller antennas on the spacecraft. And to that extent, that's what allows those small satellites to work so well. If you go up in higher frequencies, those satellites are cheaper and easier to build. There's also an absolute frequency agility that should be mentioned here. So folks with an RF background in the room are probably familiar with the 10% rule. Your standard antenna, and this doesn't apply to all form factors, but your standard antenna has roughly a 10% bandwidth off of its center frequency, right? So if you look at absolute frequency agility, down at L-band, you might have 150 megahertz of frequency agility in a simple antenna. Up at C-band, you're going to have 500 megahertz of frequency agility in that same RF front end, depending what you want to do with the filters and the amps. And so what you end up having here is greater flexibility. And so deploying an antenna gives you a wider range of potential channelization. Maybe this applies most when it comes to military applications, because you can go out in the field and kind of say, okay, we're in a war zone, we'll use whatever information or whatever frequency we want to get the mission done, and you have more options at that higher frequency. Also, it's just different from L-band, right? We have a fantastic L-band service with GPS. Let's pursue diversity through commercial and through LEO and provide that other opportunity. And I guess that brings me to some key takeaways. And just summarizing what I've been talking about here. You have high-performance CubeSats that have hit the market, and they're very affordable. You also have a material difference between moderate LEOs and higher LEOs that needs to be accounted for. Those moderate LEOs have a lot of benefits. And finally, your performance opportunities are quite big when it comes to higher frequencies at the antenna level. And so with that, I'll just end quickly with some recommendations that flow out of those key takeaways. At least as a commercial company, I'd love to see continuing growth of USG sponsorship and field test and demo days, whether that's Pentax, NavFest, you name it. Those type of activities are fantastic to participate in. You learn a lot. Third parties trust the results coming out of that because there's a strong government role in the generation of them. I'd also like to encourage folks to look beyond L-band. There's been a lot of talk and a lot of consideration of additional L-band services, additional L-band transmitters, higher power in L-band, but let's not forget we got a lot of other spectrum we can go use for a cooperative system. And it's not easy. If anyone spent time at the ITU or at the FCC, it is very difficult. But when you start looking at antennas and some of these other factors, you have some really nice technologies to bring to those conversations to ensure you're not interfering with other services. And then, relaxing ITAR, I'll add my little bit of weight to that argument. And happy to support any white paper drafting on that front because it's very important, especially for those higher frequencies. And last, of course, invest in and buy commercial, but that's just the shameless plug at the end. So anyway, went through that, and I'm happy if there's a little bit of time here to answer questions if any have arisen.
Thank you. Tom?
So you mentioned the ITU. Are there any RNSS allocations in 2 to 10 gigahertz?
Yes, there are. So there's a co-allocation in S-band at 2.483 to 2.5. There's also an allocation up at 5 gig between 5 and 5.03. And there's a good reason to look at a few of the other space operation bands as well that might have some valuable regulatory justification for use.
Renato?
Thank you, Admiral, for giving me the floor, and appreciate very much your very interesting presentation. My question will target your ability to have the freedom to operate.
Mm-hmm.
Have you considered any IPR issues, any potential drawbacks in the current regulatory and standardization environment for the application of your idea?
Yeah, absolutely. I think the big one is there's a 800-pound gorilla in the corner called 5G that are looking up to gobble some heritage systems and some underused spectrum. I think we need to reserve some of that spectrum for non-5G purposes. As economically beneficial as it is, there are other things that are as valuable or more critical than it. And I think there's some pressure that needs to be put kind of as a coalition against the 5G for that purpose. The process itself, at least at the ITU, it's very descriptive. It's very understandable. People have been going through it. Satellite telecom operators have been navigating that process for decades. At the national level, it can be very difficult. The FCC in particular is pretty expensive. When they set up a lot of their regulations, they set it up for larger, more established telecom players. If you guys are familiar, there's something called a bond. When you apply for an FCC approval and you want to deploy a system, you got to come up with a chunk of change to prove you're going to do it. And that money can get as high as $5 million. For a startup, that's almost intractable until you get to later rounds of funding. And so it slows down your progress because you can't push forward. Other countries aren't as bad. Europe in particular is pretty cost effective. Comes with pros and cons when you start bringing your service across the ocean there. I think generally, I don't think I necessarily have anything against the process. It's just something that takes time. Maybe folks in the PNT community, which have fortunately benefited from the NTIA, taking care of that in the background and making sure that we have good spectrum and that it's really well protected, we'll need to recognize that if we go off and provide commercial services, there's now going to need to be that same function that occurs. And that's going to have to be shared by a lot of different stakeholders that use it, customers, the provider themselves, regulators on that front.
And apologies for not introducing myself, Renato Filjer from Croatia, and very meticulous survey of yours. Thank you so much for this.
Of course.
Matt?
Yeah, thanks. Great presentation. We've been thinking in developing the Australian roadmap around what are the possibilities for LEO, obviously. And a few of the things that came out, I guess, to follow on from Tom's question is you go to other bands, you have diversity, which is good, but you also got an equipage problem because there's lots of equipment available in L-band. Do you have a feel for whether that's an issue or not, or am I imagining it's more of an issue than it is? And the second part of the question is, I was joking, I wasn't cheeky enough before to answer the question, but ask the question, but I was actually disappointed that GPS-3 has a 15-year lifetime. So could you comment on the fact that these 5-year turnarounds means you're much more agile in terms of next generations of technology? You can do Moore's law in space,
yeah,
if you like. So they're kind of my two.
Sure. So to take the first question first, how do you get around the fact that it's actually nice that there's a lot of capability from the user segment today on L-band? I think it comes down to looking at frequency bands where the piece part selection that you're using for your user equipment for a new service is actually coming from another sector, right? So the 5G community is working on mid-band spectrum. You've got folks in the ISM sector that's been working at 5.8 gig and 2.4 gig pretty proficiently over the last 30 years. A lot of piece part selection under 10 gig that's available to folks at low cost, right? These are still cents type components, tens of cents, a couple of dollars. So I don't think that's as big of an issue. In this day and age, we still have the chip shortage problem, which is material to everyone in space segment, user segment, ground segment on this front. And I think in particular FPGAs, which are used, of course, for development, but also early product, are particularly difficult. So kind of maybe to answer that, the harder part of the user equipment piece part selection is actually just in the first couple of years due to the chip shortage this year, as opposed to there being technologies we'll be able to use down the line once supply becomes available. And remind me of the second question.
The agility.
Yeah.
Yeah.
I guess I might want to think on that a little bit more to give you a concise answer.
Yeah, it's, some of the discussion is around, well, we're doing this on this constellation. Well, why don't you do this? Well, we can do that next constellation.
Oh, yeah.
It's kind of an iterative.
Yeah, the leapfrog. So I think it comes down to how quick you can deploy technology as it becomes available.
Yeah.
We have SERPA antennas. We understand how to use 7 and 4 element antennas. 5G, second phase 5G, and the higher frequency 5G are going to be using 48, 64 element antennas for pencil beams to users that are mobile, right? They're going to be having chip scale solutions for significant capability on the beam steering front that'll become very, very cheap because they're going to put it on base stations, they're going to put it in phones, right? I'm pretty sure the boat's already left on GPS.
That you can then put in space, you're saying?
Yeah, exactly.
Yeah,
you
right.
take that and you fly it, and you see what works. Not everything works.
Yeah.
And so you got to find the things that do work, and you got to leverage around them.
Thank you.
You might have mentioned this, and I just wasn't listening, but why not above 10 gigs?
Yeah, two primary concerns there. Your efficiency on power amps becomes a little more material. You also start to have some issues in small form factors, high powers with multi-pactions. The spacecraft becomes a little more difficult to design and develop. You also start to have atmospheric effects that could be material for a signal like PNT. So obviously L-band's great, right? Because it goes through clouds, it goes through storms, it goes through a lot of foliage. You start getting above 3, 4 gig, and you start having material effects due to weather and obfuscation and things due to foliage. If you start getting really high, it's not going to go through it at all. So you'll have opacity in a lot of areas.
Thank you very much, Patrick. Appreciate it.
Awesome. Thank you very much.
I don't know. I was going to ask that. Oops. Can we take our seats, please?
Mr. Chairman, just sorry, as we're beginning to reconvene here, I just want to get into the notes that I do need to recuse myself for this following talk. So, JJ, if you can.
Yeah, folks, if we could have a seat, could you please go ahead and restate your recusal there, just so everybody heard it? Thanks.
Yes, I just wanted to announce that I do need to recuse myself for this following presentation.
Thank you very much. Okay, Brian, I saw you earlier. There you go. Thanks for your patience. Brian Chan, co-founder and vice president of business development and strategy, Zona Space Systems. Thanks, Brian.
All right. Thank you, Thad. Can you guys hear me okay? Good, thank you. Yep, so good afternoon, all. My name is Brian Chan. I'm the co-founder and VP of Business Development and Strategy at Zona Space Systems. Really appreciative of the opportunity to speak to the advisory board. I'm happy to share some of our thoughts and perspectives and observations about LEO PNT and the general landscape. Next chart, please. So, quick outline. So first, I'll kind of set the stage here, how we see PNT needs and the motivations behind them, how commercial SatNav feeds into meeting some of these requirements. Then I'll go into Zona and what we're doing and the Pulsar service that we're providing. And then finally, I'll conclude with kind of the progress, where we are, and where we're going. Next chart. So yeah, the need for PNT resilience. I'm sure this is not a new topic or theme for you all, but I just want to point out that obviously GPS has tremendous value to not only DoD, to civilians in the United States, but of course the world. And it's a little bit kind of paradoxical, right, where the more value that GPS can provide to the world, the louder the calls are for alternatives, right? Because the inevitable question always comes up: what happens when GPS is unavailable for some reason or other? What happens next? And there really has not been a single kind of comprehensive response to address all users everywhere. And so really this is kind of where this is coming from. Clearly, the topic of resilience has been heightened in recent years and recent events, of course, and that's been highlighted in previous talks today. And it's pretty interesting, recently there's been some government LEO PNT efforts that have been underway, actually. At least I'll point out some of the non-US efforts. I mean, China, we know that there's a couple LEO PNT demos going up, but more recently, even in Europe and in the United Arab Emirates, they're looking into doing demos. So that's a pretty recent development there. I'll say that from my perspective, resilience alone does not justify a commercial approach. It really is one of several other factors, which is a good segue to my next chart. The drivers for high-performance navigation. And so, the better part of 3 years now, I'd say, part of my job has been engaging with end users that currently use GPS. And my very basic questions I've asked, which are, how are you using GPS? How do you like it? Are you looking for better PNT than what's available today? And are you willing to pay for it? This is a very high-level summary chart of what people are looking for. I'll say, depending on the industry, there's different priorities, there's different price points, there's different features that people are looking for. But, at a high level, I would say the automotive users and the autonomy users are really the ones that have the most stringent requirements in the form of, they want higher accuracy, they want that accuracy to converge very quickly, they want their accuracy in very challenging environments like urban canyons and downtown centers, and they want all these features to be rolled up into very low-cost devices that are produced at very high volumes, and they want that extremely cheaply. So if that sounds like a challenge, it is. It definitely is. But we definitely see a kind of unmet need there, or unmet needs. And so these needs for complementary PNT, for augmentations to what's available, ultimately driving to high performance and resilient sat-nav, that really lends itself to these commercial PNT business models. So I'll talk a little bit now about commercial sat-nav and how I think this might play in. Next chart. So I kind of start with 2 steps back here and showcase kind of a comparison of PNT requirements. So with GPS, by the way, this is the requirement set as we understand it back in the 1970s or so. Obviously the GPS user group was for government. It's been since opened up to commercial, of course. The famous tagline was, to drop 5 bombs in the same hole, and it had global availability. Those were the general requirements. When you look at the high-level requirements for sat-nav for today, with the user group, there's well over 90% and more are commercial users. So clearly, to address those users, we really need to prioritize these end users. When it comes to accuracy, for maybe even several years ago now, being able to pinpoint where your vehicle was on what road was important, but now it's tightened to not only what road you're on, but where in the lane in the road you are. So we see these kind of accuracy requirements tightening even further. When it comes to availability, global, of course, is required, but really people are looking for even more enhancements in population centers, like in downtown centers, and oftentimes, at least for sat-nav, that there's some kind of additional obstacles and some challenging environments to consider. Interference, clearly the world is very different than what it was 50 years ago. Good. When it comes to cyber attacks, we've been hearing a lot about not only those increasing in frequency, but increasing in sophistication. There's a lot of RF environments. There's things broadcasting both terrestrially as well as from space. To be a commercial system, of course, we have to be commercially viable. And then when it comes to user equipment, we're really talking about the millions to billions of users that are looking for higher performance PNT. And then lastly, when it comes to independence, it's resilience. A big part of this is resilience, and at least one way we see it is just having being an alternative, right, or being a GPS backup. And so I think this is really important when considering sat-nav for today. And so the real takeaway for all this is, given these very different set of PNT requirements, this results in, different PNT system architectures. So if you go to the next chart, this is GPS. I'm not gonna go through this. I think many more people in this room can lecture me about how GPS works, but this is really here for reference, right? It's about 30 satellites in MEO with atomic clocks on board and broadcasting one-way data down. So this is, given those set of requirements in the last chart, we see, a LEO-based architecture kind of meeting them. And so there's a couple of kind of key factors with a LEO architecture. And the first is obviously because it's so much closer, the satellites move faster across the sky. That results in faster convergence times for the end user. Also, there's higher receive power for the end user, which is pretty important for interference, whether that's mitigating against active or passive. And there are disadvantages, or there are things to overcome. So when it comes to commercial viability, a big part of this is, as you'll notice, there are no atomic clocks on the LEO satellites. Just by nature of atomic clocks today are very high swap, they're very heavy, they're very expensive, and considering the just sheer amount of LEO satellites we need to put up, it just does not make too much commercial sense to put them on. And the way around this is by offloading this kind of long-term stability to the network. And by the network, I really mean across the satellite constellation and then ultimately back down to the ground. There's a couple knobs you can turn here, but basically, with say a cross-linked architecture or say more antennas on the ground, by reducing the time between communications, you can continue to have a very stable clock or synchronized clocks across the entire LEO network. And so this is, I think, a key distinction between, say, a LEO architecture and a MEO one. So this leads into Zona Space Systems and what we're developing. So next chart, please. So our mission at Zona is to enable modern technologies to operate safely anywhere. We believe we have a really great team behind us, certainly our technical staff, but also we recently announced a funding round. Some of the key backers are Lockheed Martin, so that's a pretty big signal of support across a couple aspects, I guess, and Toyota Ventures is really a kind of a representative of some of the end users that we're targeting and that we're serving. So, given that system architecture I laid out, like what does this actually mean to the end user, right? What kind of PNT features are provided? So, with the Zona Pulsar system, there are a handful of kind of key aspects. One is providing complementary GPS data effectively. So, with this one-way data broadcast, similar to GPS, there's a fair amount of bandwidth that we can provide support with. So one of those is, GPS acquisition aids. So for example, if a receiver were to pick up a Zona Pulsar signal and get that data, the search space for GPS to acquire and track goes down. And so that improves acquiring GPS, for example. GPS corrections is something in the form of PPP that people are used to today, and integrity monitoring of constellations. So that includes Pulsar, it includes GPS, and potentially other GNSS also. The signal down is resilient and accurate, and by that I mean the signals, because by nature of being closer, the receive power is over 100 times more powerful than GPS L1CA. And can provide, decimeter level accuracy or potentially even better is what our studies are showing. The signal itself also has a couple layers of security, so encryption and authentication. It's sort of a killing two birds with one stone, where we can control access to the service, but also it provides protection against certain attacks such as spoofing. And then lastly, just serving as a GPS backup. So it really helps to have this tenet from the ground up, where it's hard to extract or take out GPS dependence when you have it already. And so the system is kind of designed from the ground up to be fully independent, to provide that backup and alternative. I will say a key point here though is when I talk about this sub 10 centimeter accuracy, our satellites do use GPS as an input to get down to that accuracy, but if GPS were, say, unavailable to the space layer, the Pulsar system would be able to provide position, but just at a more degraded state. So we're talking about the meter or 2 meter type level. So how does this actually work as a business? So the way I guess I would think about this is Zona is developing the ground and space segment, delivering a signal down, and that signal and service is ultimately the product. That product then goes off, and we work with receiver manufacturers who are integrating that service and that signal such that they can then produce kind of higher performing equipment and then deliver that higher performing equipment to end users across, automotive, mass mobile, and really kind of all the folks that I touched on earlier. So here's a chart of the Pulsar phase rollout plan. We're not going to do this overnight. It's going to take some time, and we've broken it down in 3 phases. The first phase is 40 satellites. So 40 satellites allows for at least 1 satellite in view across the mid-latitudes. That can provide precision timing. That can provide GNSS enhancements like the aids and corrections I was talking about, and that IOC in the mid-latitude region begins in 2025. As we populate the constellation, effectively, the service features improve, the coverage map expands to global, and then when we get to the full 300 satellites, then this is really when we can offer all the kind of bells and whistles and all the features that I talked about earlier. Okay, lastly, the kind of where we are and where we're going. So next chart here. So yeah, I mean, all what I talked about is well and good, all in PowerPoint land, but what have we done to date? And so enter Hugin. So to provide a little bit of kind of Norse mythology trivia, Hugin was one of Odin's ravens, which flew around the earth, gathering information and delivering information back to Odin. And so that's kind of what Hugin is doing for us today. So Hugin was launched in May of this year, and with that launch, Zona became the first privately funded company to launch a dedicated satellite navigation mission. And so to the left there is a picture of the satellite, the sat-nav payload itself. In gold is what you're seeing there is the antenna array elements. So it's designed to broadcast in L-band and in C-band. The middle is a shot of the SpaceX Falcon 9 rocket there going up, and then to the right is a picture of it in space just prior to separation from the launch vehicle. So we've been moving quickly, and we're starting to already move towards production. So, in 2019, we filed for our LEO PNT patents. I know that wasn't so long ago, but I think LEO PNT at the time was seen as a pretty outlandish idea. I think one of our objectives is really to bring this down to more of a grounded kind of project. About a year later, we took that plan in patents and took that into the lab and showed that it actually worked. A year later, we improved that lab prototype, and then we tested that in the form of pseudolights at Camp Roberts down in kind of by Monterey area, California. And then a year later, we improved that, and we launched into space. And that's really what you see there. A couple, kind of the status of Hugin right now. So it's operational. We've been checking out the systems. Everything looks good. We've already completed some successful firmware uploads. We're doing internal testing right now, and we expect to open it up to doing end-to-end tests with our third party or our receiver manufacturers next year. Speaking of user equipment manufacturers, so we're working with about a dozen or so user equipment vendors. So they're currently integrating Zona's LEO PNT signals into their existing products or future products, and demand for kind of GPS plus Zona devices are in the millions right now. I think a really interesting aspect of this also is because user equipment folks are really investigating the firmware change only kind of capability, right, where you have existing hardware that picks up GPS, picks up GNSS, and with the firmware change only, can pick up Zona. And so we're seeing some very promising results in that realm. I know spectrum and spectrum management is a very big deal here. So what I'll say is from this mission, we've gathered some very good feedback from some of the results themselves, but also from stakeholders. And stakeholders include regulators, government folks, and also user equipment vendors that we know that they have, say, limitations or they have existing hardware. And again, we want to make it as easy as possible for that integration. I'll also say that, we take spectrum management very seriously. As a kind of GPS augmentation service, it's not only important for Zona to be compatible, but really to be interoperable with GPS and with GNSS. And, I think that it's certainly in our interest that GPS operates at the highest level, and there's really no, concerns when it comes to compatibility. So I think that, our company is pretty aligned with, hopefully, with what the advisory board feels, as well as the national interest in terms of, keeping GPS, operating at the highest level. And the last point I'll mention here is, we're moving to production. So as we are getting results back from the demo mission, we actually have a second demonstration mission coming up next year, and we're already evaluating suppliers to help with the ground and space segment and the production systems required to make that all function. And so this really leads into the Pulsar ecosystem. It's kind of a trite phrase, but it's true where we really couldn't do it with the support of folks on the supply side, on the user equipment side, and the simulator side. And there's others as well, such as antennas and everywhere in between. I'll say that, I guess I did mention a little bit about the ground and space segment partners, but a couple kind of highlights when it comes to simulators. So we announced a partnership earlier with Spirent Federal. So they're looking at delivering effectively a Zona plus GPS simulator. There's a company called Syntony. They actually demonstrated at ION GNSS earlier this year. They demonstrated a Zona simulator at the exhibit hall. So that's a screenshot of some of the outputs of that simulator. And on the user equipment side and the receiver side, there's a number of advancements there. We signed an MOU with Hexagon Novotel, and so they're looking at picking up the Zona signal in addition to GNSS. We've done the same and reached an agreement with a company called StarNav, and there are others. And so you can see a few photos of real hardware that's ready to go, ready to pick up the signal. And yeah, we kind of welcome more and more user equipment. Clearly, going back to the early charts of, it really depends on what the application is. We intend to test these user equipment at, in different scenarios, different use cases, different requirement sets, because there's never really a one-size-fits-all kind of user equipment when it comes to GPS or PNT in general. And yeah, I'd like to just conclude with the Zona team. We believe we have some really strong technical staff on board, very well steeped in GPS, in autonomy, in kind of civil aviation, as well as space systems. And so we grew from a co-founding team of 8 to now 45 full-time employees. We're based in the San Francisco Bay Area. We just outgrew our original headquarters, and so we're moving to a new facility in Burlingame, so just right by SFO, so you can kind of see the airplanes take off and land. We're moving in January, so a couple months from now. And so once we kind of put new paint on the walls and add office plans and things, we definitely welcome everybody here for an office visit sometime. So with that, I appreciate your time and open up to questions.
Thanks, Brian. Questions, comments? Terry?
Just a very simple one. On slide 17, where you've got the picture of Hugin, there's an antenna on the side. Is that for reception of GNSS? Is that for satellite tracking?
Yeah, so that's a great question. So this is based on, I mentioned that we're launching a second demonstration satellite. And so we'll be doing some tests where we're doing satellite to satellite. Yeah.
Thank you, Brian.
Thank you.
Yeah, Admiral, this is Russ Shields. I have hand raised. Can you hear me that I can ask a question?
Yeah, I'm sorry.
Yeah.
I'm sorry we missed you. Go ahead.
I know this is hard to do it. I thought this was an interesting presentation, and looking at a lot of the emphasis on cars and wondering what kind of pricing you think you're going to have for the cars. And let me give you some background on this. The car companies are always looking for multiple things. So the fact that you've got investments from Toyota Ventures, I know of at least 5 different things that Toyota has been working on different kinds of positioning. And many of the senior people who are working on true automated driving and 10 centimeter accuracy within the lane, and that's relative accuracy, not absolute accuracy. They need relative accuracy in the lane, are strongly working on using the multiple cameras that they're putting in cars, a multi-stereo approach to be able to do the precise positioning where they think they can get themselves within the lane in the 3 to 4 centimeter. But that cost is only adding some software. How do you have a cost that would be comparable to adding some software in a car to do the job?
Yep, great question. So, we're based in the Bay Area, so, we see, you can kind of throw a rock and you'll hit 5 different self-driving car companies. We see them all the time. And you're right, I think relative nav is a really big deal for them, and absolute nav, at least historically now, has kind of taken a backseat. Our whole position is, so, not going to name any names here, but for example, self-driving cars are a thing, and they can really drive themselves. A kind of big asterisk behind this, though, is to really get to those 5 nines of safety, you really need some very high-end, expensive equipment. It can be tens of to ultimately hundreds of thousands of dollars, and it's simply just not scalable. So, if we look at GPS, right, it's an incredible system. With a $5 GPS chip, you can do pretty good. And so the whole point of our approach is kind of offloading the need for very expensive equipment, such as LiDAR, such as cameras, such as things like this, and you're left with a fairly kind of low-cost chipset that can pick up, say, GPS as well as Zona. And so that's really the approach that we're taking, and so you offload that cost from every single car, and you offload that to the space infrastructure.
Yeah, good luck. Don't believe all you see in Silicon Valley. Mainstream car companies will have automated driving out in regular cars for consumer costs of under $5,000 in the next 6 or 7 years, different from Silicon Valley. So good luck. I wish you luck on those things, and the evolution will be interesting as we watch it. Thank you.
Yep, thank you.
Thanks, Russ. Any other comments here or virtual? Thank you very much. Welcome to Dr. Ramsey Farragher. Did I get that right?
Perfect, thank you. Okay, great. So good afternoon, ladies and gentlemen. It's a pleasure to be out here speaking to such a prestigious audience on hopefully a topic that you'll find quite interesting.
Could you move closer to the mic, please?
Certainly. Is that better? Perfect, thank you. So I'm going to be talking about supercorrelation, which is a software upgrade to go inside GPS receivers to improve their resilience against spoofing and jamming. The problem we're solving is this one. The signals bounce around inside cities, as I'm sure we all know. And one of the biggest challenges we have with GPS in our cities is that that signal is highly reflective. So those reflections look just as loud as the line of sight signal does itself. And so traditional processing really struggles in this environment. We have what's called multipath interference, where the line of sight is interfered with by the reflections, and this distorts the signal. And you also have issues when the line of sight isn't available at all, and you're only picking up a non-line of sight signal. And both of these can contribute to really significant positioning errors. Traditionally, it's been a real struggle for a GPS receiver to understand the differences between the line of sight signals and the non-line of sight signals, and this is the problem that supercorrelation fixes. So the hint is in the name. We're right down there at the correlation level, and we're effectively changing how correlation works. So for those of you who are not familiar with this, it's the heart of the measurement of a GPS receiver. The satellites all transmit a unique code word. You have a correlator bank inside the receiver that has copies of those unique code words, and it matches them, finds the time of arrival, and you get this pulse in time inside the receiver, and you use that to work out how far you are from the satellite. That pulse can get distorted by the interference I've just described, and what we do is we solve that distortion and remove it completely. So I'll explain how we managed to do that. So the correlation code words repeat over and over again. That's represented by these dots at the top image. That's the code word just repeating from the satellite. And the satellite transmits those code words on its carrier frequency. And so the textbooks say, here's the code word, aim for the right sort of frequency, and begin correlating. And that would work brilliantly if you were static and had a perfectly good clock. But in reality, you're moving if you're navigating. And when you're using smartphones and smartwatches, which is where we concentrate incredibly low-cost devices, the oscillator inside those devices is incredibly low quality. And what that means is the receiver, when it samples the electromagnetic radiation, that sampling pattern does not look like what was transmitted. But that's what you have to work with. So instead of getting a beautiful set of correlation code words all in a row on a fixed frequency, you actually get a distorted view of both. Both the code words and the carrier frequency are squished and stretched through your motion through space and through the oscillator inside the device being very, very low quality compared to the oscillator that transmitted the signal. So the receiver actually receives something like the cartoon on the bottom, but you're trying to match it to what's in the middle, what it says in the textbooks. And so what Focal Point do is we do all the hard work on making the match. So we reconstruct the motion of the antenna through space to a centimeter level and use that to motion compensate the correlation sequence. And we also have a lot of clever technology to model what the oscillator is doing, even very, very low quality oscillators that are being heavily distorted by 5G modems getting hot and other problems inside smartphones. And we reproduce the true, rather complicated supercorrelator pattern. And we do this over long timescales, like a second or longer. The longest real supercorrelator we've done on a freeway with a smartphone was over 5 seconds long, and that gave us about 10 dB of gain. So when you're matching a true supercorrelation sequence like this, you get another fantastic benefit. So you're not just getting over a second of coherent integration and all that gain, you're getting true discrimination between the line of sight signals and the reflected signals. Because when a signal bounces off a building, those very subtle Doppler shifts I just described due to your motion are different for the reflected signal as they are for the line of sight signal. So a reflected signal has a different supercorrelator pattern. And if we look back for a moment at what a traditional receiver is doing today, the middle, normal receivers are basically just as bad at looking for the line of sight as they are as looking for the other signals. They're not perfectly matched to either. And so this is where multipath interference occurs. They equally correlate the stuff you don't want and the stuff you do want and make a mess. When you're supercorrelating instead, you tailor your correlation sequence to the direction you're interested in, and you get angle of arrival in software. In effect, we've solved the problem of synthetic aperture processing on a smartphone at incredibly low cost, for those of you who are familiar with synthetic aperture processing. My building just turned into a spoofer, so that's the other handy thing. So in the same way as the reflections not being a true pattern of what your motion and your oscillator is causing the signals to look like when you sample them, a spoofer cannot do this either. And so spoofing signals are separated out too and detectable by angle of arrival, as you'll see in a few slides' time. So here's some actual correlation peaks, starting with some GPS L1. So yellow here is incoherent integration of the correlation peak. So in other words, the traditional stuff, for those who aren't familiar with what I've just said. There's a blue line here as well. That's the supercorrelator correlation peak, but you can barely see it because it's underneath a red shape. And that red shape is a template of a perfectly clean signal. So it fits on the blue function nicely, showing that there is no multipath interference on any of the supercorrelation peaks. So on the left is an example where we gathered some data in a completely open environment, and the normal processing is nice and clean, as is the supercorrelator, as is the template. In the middle, that's data from an urban canyon. The yellow plot that you can see is highly distorted by multipath interference. The line of sight's there, but it's been mixed with lots of non-line of sight signals that have distorted that peak. But the blue supercorrelation peak is clean, and it is just representing the line of sight component. Then on the right-hand side, you've got what looks like a nice clean signal from traditional processing. The yellow peak looks beautiful, and a simple algorithm running inside the receiver might go, hey, this looks really clean, I'll trust this. But supercorrelation revealed a much weaker earlier signal, the line of sight. And in that instance, it was actually coming through a building, and we effectively stared through the building in the correct direction and picked up the non-line of sight component and destroyed the non-line of sight component because it didn't have the right supercorrelation pattern. Here's some L5, we make that better too. So left example again, multipath interference. You still get that on 60-meter wide correlation peaks, just like you do on 600-meter wide ones. Difference between L1 and L5. In the middle, the trackers were being held in place by the navigation engine, but traditional L5 processing couldn't see anything. The yellow line is just noise. But we can dig out the actual line of sight component buried in the noise. Again, that was a signal coming through a building. Because we're doing over a second of coherent integration, we push the correlation peak up and we push the noise down. So you get this beautiful boosting in signal-to-noise ratio. On the far right-hand side is another example again of what looks like a beautifully clean correlation peak to traditional processing, the yellow one, but we dug around in the noise and found the line of sight component. Again, it had been blocked by a building that we could see through and extract the line of sight signal. Here's some trials from Canary Wharf. This is a GPS L1 only trial. And what we were doing here was using supercorrelation to clean up the observables, the pseudorange and the Doppler, but then just passing the radio observables into a radio-only Kalman filter. So that there's no inertials in use here in the navigation domain, which is why traditional processing, the red line, is so bad. Of course, some of this is hidden by strap-down processing normally, but this is revealing what the observables are really telling your Kalman filter is going on when in a strap-down mode in a city. And what's effectively happening here, if you look in the middle of the plot, where the blue lines are still giving you nice straight lines in the urban canyon and the reds are all over the place, what's really happened there is we're in the middle of a nasty urban canyon. Normal GPS processing can see maybe 10, 11 GPS satellites and is shoving them into a sensor fusion algorithm. But the supercorrelation results are going, hey, look, only these 5 are line of sight. You can't use the others. And so it's only limiting you to the line of sight signals and effectively keeping you on the straight and narrow in those urban canyons. So the plot on the left is then showing the error histograms for that journey. And we improved the 95% confidence bound by a factor of 10. I realize this is a slightly confusing plot. The red 95% confidence bound, the dotted line should actually be off the side at 108.7, but it's actually come back into the plot on 80. But we improved the 95% confidence interval there by about a factor of 10. So this is a summary of the typical improvements. This is actually a summary across a whole range of trials with various smartphone manufacturers and others, a combination of the performance we're getting with different people. So a sensitivity boost of 5 to 10 dB, depending on whether we're doing 1 or up to 5 seconds of coherent integration. The accuracy boost for pseudoranges and Dopplers can be anywhere between 2 times to 12 times. That basically depends on the environment. The nastier the environment we're in, the more we're rescuing the problem. So up on a mountaintop, you're just benefiting from some sensitivity boost, but in an urban canyon, we can drive some really big, significant changes in the performance of the accuracies of things like pseudorange and Doppler. Integrity is a measure of how often the device is lying to you, for those who aren't familiar with it. So if you've ever had a situation with your own smartphone where you're kind of looking at that blue dot on Google Maps or another service, and you've got the error circle around it, but you know you're not actually even inside that error circle, regardless of how big or small it is, that's a low integrity fix. And so that is caused by the non-line of sight signals collapsing the error ellipse, but putting you in the wrong place. But by discarding the non-line of sight signals, you keep a sensible size error ellipse that you're always inside. And so we can improve the integrity by up to a factor of 10 again in real trials. Integrity is a very important measure for things like autonomous vehicles, safety of life, things like that. And the bottom is mentioning a bill of materials saving. So there's a spectrum of things you can do with supercorrelation. It's kind of like a bit of a lever that the GPS receiver manufacturer is choosing to set. You can either keep everything as it is and improve the performance of your system, have a higher sensitivity, improve the accuracy metrics like I've just described, or you could actually choose to set the lever in a different place so that you keep your current level of performance, but make your antenna worse, make your oscillator worse, these sorts of things. We find that different people we work with are in different places on that spectrum. Some people are just wanting to reduce BOM costs where they can. One of the nice things we can do is give you L5 type performance just with L1. And so that's a BOM cost saving on antennas and silicon area and things like that. So I'll get on to the resilience bit and show you some results from some spoofing trials, but I need to show you a brand new thing that you can't get with normal GPS processing. So this is what we call SkyScan. You're used to seeing a circle like this when you look on your smartphone at the picture that shows you where the satellites are in the sky. So that circle represents the sky above your head, and you are normally looking at all of the satellites at different azimuths and elevations. What we're showing here is one satellite, PRN-23, the red circle there, and all of the colors are the energy that we're picking up from all of the different directions. So normally you effectively set your supercorrelator in the direction of the satellite where you're interested in and just focus a beam over there. But you can actually have a little bank of supercorrelators and scan the whole sky all the time and map out all the energy coming from all the different directions. And that's what you're seeing here. So this is, for those of you who've never seen multipath interference before, here it is. This is the energy arriving from all sorts of different directions inside an urban canyon. And it's a nice little example of the problem. So the red dot, as I mentioned, is the true location of the satellite. So low on the horizon in the west. Black is no power. White is a lot of power. In fact, line of sight level of power. And then you've got this gradation running through dark green, pale green, pink to white of power. And as you can see, there's this band of energy around the red dot. So there was some power coming from the line of sight direction, but about 100 times less power than you expect for line of sight. And there was line of sight amount of power coming from the northish of us. That's the big white stripe across the top of the SkyScan plot. And what's happened here is this is a moment inside an urban canyon where satellite 23 was just eclipsing behind a building. And the signals from GPS satellites have kind of a size to them like a torch beam does. And so they literally eclipse behind the building. So as the last glimpse of the edge of the satellite's beam was disappearing behind that building, we were still picking it up when we were looking in the right direction in the sky, but there was only 1/100th of it for us to play with. But there was a bus or a building or something north of us that was bouncing the signal with almost perfect reflection down from the north area. And that's the big white band across the top. And so the SkyScan plots are kind of giving you a passive radar, if you like. So here's a cartoon representation. So for this scenario, this car driving along with a signal bouncing off the van at position 1, the building at position 2, and the building at position 3, you get these bands in your SkyScan plot. When you're taking a very nonlinear path, these are spots. But if you're moving in a straight line, they're bands of power. It's just a kind of symmetry issue with how synthetic aperture processing works. But I wanted to explain this thoroughly before I show you the next bits. So there's a set of SkyScan plots for 7 satellites from a moment inside an urban canyon. And as you can see, you get vastly different patterns from the different satellites coming from different directions. So for normal reflections, non-spoofing stuff, Skyscan plots all look quite different. So this is the results of some real-world trialing we did with an entity that is allowed to do such things. And I can't show you the satellite imagery of where we were, unfortunately. I didn't get permission for that for this. But the data and the results I'm showing you, I have got permission to show you all of the real data. So here it comes. The route we drove, as you can see, was about 200 meters. We drove past a spoofer, turned around and came back up. And the spoofer was effectively meakening, so it was rebroadcasting the sky. And it was delaying the signal such that it was set to give an offset just a little bit north of us. And a meakening attack is the worst kind of attack because all of the encryption is in the rebroadcast. And so M-code can't prevent you from being disrupted by a meakener. You need a CRPA or this sort of technology to give you angle of arrival. So what you've got here is the red line is normal GPS processing, the blue line is the supercorrelation processing, and the black line is ground truth. So you can see as we drove down and then back up again past the spoofer, both times that normal processing was ripped off to the side. And the plots you can see on the right-hand side, that's the north, east, and up errors. So I'm afraid the font size is quite small, but it dragged the position off by about 100 meters on both passes. And here's some moments from the drive from the Skyscan point of view. So we are at the position marked by the pale blue circle in the top corner. And as you can see from the Skyscan plots, which you're all now expert in, it's a beautifully open environment, and there's just power cutting through every satellite. No problems. And we get to here, and you can see that the normal positioning is being dragged off towards the spoof location. And sure enough, if you look at the Skyscan plots, we've got the band of power cutting through every red dot from the satellite in the sky, and we've also got common power south of us on every single Skyscan plot. Not normal, not something you get from reflections in buildings. This is a common reflector or common source of power south of us that we can pick up. Driving right past the spoofer, and there's huge amounts of power right there, and you can see there's this sort of general gist that there's power coming from the west of us. This is then that we've driven past the spoofer, and traditional processing is now caught back up and is not being spoofed anymore, but we are still detecting that there is a spoofer now on the north of us. You can see the power on the north side of each of these Skyscan plots. And of course, by the fact that Skyscan is a directional technology, you can effectively take an azimuth at each of those locations and locate where the spoofer is. Taking transects like this would be a very rough and ready, lazy way of locating the spoofer. In reality, you'd build up a Bayesian estimator to have a probabilistic estimate as to where it was, but I think this proves the point that it can be used to locate spoofers. So in summary, supercorrelation is motion compensating very long current integrations. I've talked about GNSS, but it's actually a radio technology that's applicable to anything that has a digital code word that repeats. So the things we've heard about already using television signals is next, I believe. Mobile phone signals, TV signals, LEO satellites, etc. All of these signals can be used with supercorrelation. And it's a way of getting angular arrival without hardware changes, without expensive antennas, doing it entirely in software. So we focus on smartphone and smartwatch devices. We're working with all of the major names that you'd expect there. We've licensed our technology to U-Blocks. That's the only one we can name publicly at the moment. But Focal Point just closed a £23 million funding round with a major automotive strategic that we're hoping we can announce publicly in a few weeks' time. And as I've just shown, we can use this technology to detect the source of spoofers as well as ignore them. So an important step, I think, for improving the resilience of GNSS receivers in the future. I'll take any questions if you have them. Thank you.
Thank you. Brad?
Very fascinating. Now, I don't exactly understand. Are you using sort of a running fix concept to get the as and L? I don't see how you get from a cell phone an as-L plot of the sky, although I can conceive of it as a running fix if I can run correlations. Maybe, yeah, but I still think there would be a dot problem that I could get one of the directions wouldn't be very, very good.
So what we're effectively doing is we rely on motion. If you're stationary, you can't do this. And so we're synthesizing an aperture. So over a second, a human moves about a meter. A car will move much further. So if you imagine, instead of waiting a second to process a supercorrelation, if instead you dragged behind you a 1 meter long antenna full of elements, you could steer a beam with that array.
Yeah, so to my old 1950s navigation, we would call that the inverse of a running fix.
Okay.
But it's still, to get it in as and L, when I'm driving a straight line, it seems like...
Yes, sorry, so that's the symmetry problem. So when you're in a straight line, it's a surface of a cone of sensitivity.
Aha.
And the surface of that cone is the bands.
Say no more, I got it.
Yeah. So
Thank you.
it's the residual issue. So for cars, it's more of an issue than it is for humans.
You don't have, I've got it.
Okay.
Thank you.
Pat?
That's really, really cool. My question is, what is the impact on the system processor that the load of your software would add?
So it's a few MIPS. It depends on the receiver design and how bad their oscillator is and things like that. We have a calculator that we provide to the manufacturer or the OEM, whoever's implementing the IP, so they can work out what the impact is. It's tens of kilobytes of extra memory, which is meaningful if you've designed a discrete, but meaningless if you're a smartphone, where they can touch the main host memory. And then it's a few MIPS of extra processing.
One other question, thank you, that's good. Is your software, does it become an app, or is it actually integrated into the operating system?
So the key thing that we require is those samples from the correlation peak, and they need to still be complex. And so just about everything else we need is at the Android standard calls. You could write an app to get just about everything else we use, apart from those bits. And so we were the first people to go around asking all of the receiver manufacturers to go one notch lower now than pseudoranges and Dopplers and give us the early, prompt, and late in complex form, please. And thankfully, they all started handing it over to us, which was lovely. And so that's how we've been able to do trialing with them all. And so wherever that is available, our IP can sit. And so traditionally, that would have been inside the chip. But the relationships are changing between the chipset manufacturers and the operating systems and the handset manufacturers, and more data is available than ever before in that relationship. So, pseudoranges and Dopplers didn't used to be available at the OEM level, but now they are. And so we're going through a transition where the OEMs have access to this data too. And so we can either sit inside the chip or we can sit inside the operating system.
One more. Does your software have to go through a discovery process to understand the antenna and what the chipsets are that you're interacting with, or is there some kind of a menu that you select a variety of things?
That's a great question. So it's certainly the case that every receiver manufacturer we've worked with are all subtly different in some way. And so while there is what we call our reference design, which we provide along with the licenses, when we go through a trialing phase, before they'll stump up any cash, they want to check it works. During the trialing phases we go through, we learn if there's any particular interesting thing about their receiver that we have to compensate for. And so it looks at the moment like everyone will get a slightly tailored reference design from us. So there's some small differences that we account for. So there's that aspect. And then I think you're also kind of asking, is there like a set of features you can kind of enable and turn on and off and stuff like that? And that's the case as well. And because it's software, it's just a matter of which functions are provided. So Skyscan, for example, doesn't need to be a default thing. That's something they can pay extra for and things like that. So I think there's a mixture there, I think, to answer your question. There's some stuff that we have to tailor for each receiver because they're not all the same, but there is also a set of features that people could choose what they want from us.
Terry?
Hi, Ramsey. Just one quick one, because I don't think you've said it. You've explained that you've licensed now to various OEMs or chip manufacturers. Without giving anything away, how long do you think it would be till it's appearing in consumer electronics? I mean, is it going to be next year's products? Is it 5 years away? Just to give an indication.
It's a good question. My conservative statement would be within a couple of years. There's an integration roadmap we're involved with us and two other companies that is looking at deploying it in vehicles in a couple of years, and I'm hoping this will actually be part of a press release in the coming weeks. And on the smartphone side, we're at a negotiation phase with entities, and you have to hit in their cycles then. And so it's this kind of horrible thing where you can close a deal one day too late, and you have to wait a year now to be in, the next release and things like that. So it's hard to predict because of that aspect, but I'm hoping that in a couple of years' time, we'll be driving around with them and maybe have one in our pockets if we're buying the right phone as well.
Do you have a?
I do, if it's not. Back to your supercorrelation replica. You had the picture up a second ago.
This one?
What is the source of that? Where does that come from?
So we take the early, prompt, and late from the correlation peaks. So what normally happens in a receiver is that they'll have some pre-integration amount they do at the moment, say 5 milliseconds. And so they're creating a correlation peak every 5 milliseconds that has a complex early, prompt, and late. So over the course of 1 second, we'll collect 200 of those. So we've got 200 complex correlation peaks. Over that same second, we've monitored the inertials to see how the platform's moved, and we also do some very clever stuff to do some clock modeling. Once we've done the clever motion stuff and the clever clock stuff, we build up a set of complex corrections called the supercorrelation phaser, unique to each satellite, unique to each moment, unique to each motion pattern, and unique to what the hell the oscillator's just done. We multiply the correlation peaks by this phaser correction, and crunch, 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 crunch. When we coherently integrate them, we've only coherently integrated the energy from either a cone of surface cone or a direction, depending on how nonlinear our motion was. Hopefully that incredibly complicated answered your question.
Thank you, that helped, I'll follow up later.
That was the non-cartoon answer.
Thank you very much. Next, we have Sam Matheny and Tariq Mandal, National Association of Broadcasters and
fixed, reliable, and high-power service based on terrestrial broadcasting that can be used for both timing and positioning. So Tariq is going to talk about the Broadcast Positioning System, or BPS as we call it, and describe how it works and what it does. And then I'm going to come back and try to describe how it could fit into a system of systems, what its key advantages are, and then what the next steps for BPS are. So with that, Tariq.
Thanks, Sam. So BPS is actually a system and method of estimating both time and position of a receiver using only over-the-air television signal, nothing else, over-the-air television signal. And it's 100% compliant with the next generation television technology that's being rolled out now. And the technical standard that drives the next-gen TV is called ATSC3. More on that later. And GPS is independent and standalone in the sense that it continues to operate when GPS, cellular service, and internet are simultaneously unavailable. I repeat, it continues to operate when GPS, cellular service, or internet are unavailable. The concept is really simple. From a tower, we transmit a known waveform, and right after that, we transmit that waveform's emission time and the position. Think about it. If you just have one tower and the receiver position is known, then the receiver will correlate, find the time of arrival using the known waveform, then it will demodulate the signal, find the timestamp, compute the propagation path using the location coordinates, add it, and voila, you have a stable timing source. If the position is unknown, you can still get a stable time, but it will have a clock offset. And if there are 4 or more of the signals coming from 4 or more towers, geographically diverse towers, then you can compute the pseudo ranges, and from there, you can do the joint estimation of position and clock offset. People with brains have already developed this 50 years ago. They figured it out, they employed it. We just took the essence of that idea and applied it to the broadcast system. We think, even if we have just one tower, if we have a good timing reference and the unresolved multipath is not too bad, we should get 100 nanosecond accuracy 95% of the time. And for multilateral technique, where we have 4 or more towers, actually you could get 8, 9, a lot of television towers. I'll come to that later. We think on the average we can get 100-meter accuracy. And this is not line of sight, this is terrestrial signal propagation. A little bit about ATSC standard. The standard actually we started talking about in 2010, and then most of it was developed between 2012 and 2016. A lot of big companies like Sony, Samsung, LG, Qualcomm, and also some of the research institutions like ETRI of South Korea, CRC Canada. They were some of the leading contributors. There are also many other small companies and some universities. The standard finished, the standard was totally developed by 2018. The standard is fairly new, and all those researchers and engineers, they incorporated the latest developments of communication technology into the standard. It was going along with 5G. The standard was deployed first in South Korea in 2018, just before the Winter Olympics. In the US, we started deploying it in 2019, and it has been being developed. The ATSC system, the physical layer, the whole system, is actually a low latency, high capacity data pipe. It transmits UDP IP packets. Some call it data casting broadcast IP. So most of the data is used for television services. Yeah, stunning pictures, captivating sound, everything, all that. And there's still some bits left. And the remaining bits, we can have some data casting use cases. Some of the things Dr. Axelrod talked about, GPS assistance data, correction data. Those could be all transmitted easily in a fraction of a second. Finally, because of this superb engineering, the reception of this ATSC3 is much better than the previous generation television signal. It's actually 20 dB better. It requires 20 dB less signal-to-noise ratio. Because of that, it works indoors, and it is also received by mobile devices. Television signal. Television operates on 35 channels, each of them 6 megahertz wide. And it's also it's from VHF to UHF frequency. It's a lot of frequency diversity in there. More than 500 channels operate up to 10 kilowatt in VHF band, and more than 1,500 channels operate with up to 1 megawatt power in UHF band. So because of the frequency diversity and the high power, this signal is probably a little bit difficult to jam the entire system. And yeah, if you want to jam the signal, build a power plant, build a tall antenna, and Karen Van Dyke would come with a bludgeon to catch you because you're doing interference. It's very easy to actually detect if someone is trying to interfere. The system has been deployed, I told you, in the US. Right now, in 65 markets in the US, it has been deployed. The orange area in the map, if you have a receiver over there, you can get 1 to 2 stations. Signals from 1 to 2 stations is receivable. 15 more are coming. They are shown in blue. Broadcasters actually want to cover the entire US with at least 1 tower before they deploy multiple towers in a market. This is the coverage of just the UHF deployment. There are more than 1,500 channels, but we considered only 696 of those towers because they are geographically separated for at least more than 1 kilometer. And if you look at the orange area, the coverage 1.5 meter above ground, you could see you can have more than 10 stations. The receiver can pick up more than 10 stations. Most of the east half of the US. There are some yellow spots. There are 1 to 3 stations on the western half. This is because we did not consider VHF channels. Those areas actually have a lot of VHF channels. So if we consider all the channels, 2,042 channels, then the coverage numbers will be roughly 3 times higher. So on the East Coast, could be more than 30 stations. We also recommend redundant timing. GPS, PTP over fiber, and atomic clock should be available to all the towers. Yeah, and ELORAN, when it is available, could also be used. And on top of those, the ATSC stations would be all locked to time, so we could listen to neighbor stations and get additional timing reference. And to increase resiliency, accuracy, and fixed yield, we recommend 2 things. First, all the stations should listen to each other and report the emission time and position of all the neighboring stations. This is something Mr. Higgins was talking about when he talked inter-satellite communications earlier today. Same concept. It looks like GPS assistance data. With that, a receiver can easily detect if a television signal, one of the 30 signals is spoofed or not, and it could exclude that. Moreover, if there are signals that are good enough for time of arrival detection for the correlation to the known part, but the signal is not strong enough to demodulate and get the emission time and position of the tower, it can actually get the assistance data and compute the fix. So that's the way it increases yield. And the second one is we will also be reporting the timestamping error of the previous frames. This is broadcasting layer. This is, I mean, there will be some errors in there, few nanoseconds, but we'll report that. So one can actually take that measurement error and apply it to past fixes to get a more accurate location estimate, on timing estimate, both. And so, in the use cases, if you want the fix right now, you could get it really quickly. I mean, maybe within, for deployment within half a second or so, but with some accuracy. But if you want more accuracy, then you have to wait a second, then the accuracy will go high. So it's a choice, and there's a use case that will determine what we'll do. I now pass over to Sam Matheny.
Thank you, Tariq. So I think you can see that there are a lot of important and inherent advantages to a BPS type system. It's low cost, reliable, diverse frequencies, and can be received indoors. It's based on existing broadcast infrastructure. So the towers are already there, and these are facilities that are designed to stay on the air 24/7 and operate even during and following times of disaster or emergency. And many in our industry would say that that's especially when we're designed to operate. That infrastructure is already there, and it is already offering free-to-use signals, right? The receivers are being mass-produced. CTA estimates are that 5 million next-gen TV sets will be sold this year, and that's going to grow to 27 million sets sold in 2025. So there is a large adoption rate on the receiver side. And as Tariq said, this can be operated completely independent of the GPS system and provide some really good augmentation. And I would note Karen was talking earlier about Denver and Dallas. So, you know, if you go back and look at that map, there are 10 plus signals that are going to be received in those markets where GPS spoofing took place. 10 plus of these television signals are going to be available there. So what are the use cases that we see for this? And there's, you know, we have these 4 basic ones in mind. You may have others, of course, you know, they've learned a lot throughout today, but number 1 is just we can deliver independent time source. And we can do that, as Tariq said, with a single tower. The second one is we can deliver independent position and time, and that comes with the deployment of multiple towers. When you integrate this with GPS and make it part of a system of systems and you monitor it, you can detect GPS spoofing. And then, of course, you can add AGPS or real-time kinematic data, and you can both enhance the resiliency as well as the accuracy of a GPS system. And I'll pause here just to say that earlier this year at our trade show that we do in Las Vegas, NAB show, we actually had a demonstration where there was an ATSC-3 transmission of RTK data that was received by an unmanned aerial vehicle, a drone, using a little antenna. It was combined with GPS signals, and the drone flew a very accurate and precise course using that RTK data. So that type of application is already taking place today. So this is not a fully built system. It's not fully built by any stretch of the imagination, and these are the development phases that we've laid out. And phase 1 is really where we are today, and that is that we're focused on the transmission side of things. We've detailed the data schema that we need, and we're beginning to work with commercial vendors to get it integrated. Our plan is to bring that back into our lab at NAB, where we will further finish that phase of things out. Phases 2 and 3 are really about let's take what we learned from phase one. Where are the gaps? How can we address those gaps? And what can we do to develop a prototype receiver and move towards deployment in a live market? Phase three would be really, okay, we're going to add a real legitimate backup timing source, and we want to do a live market trial. Going into phase four is where we think that we can begin to deploy a timing-only service. And then 5 and 6 are really about building out multiple towers and adding that positioning use case. So looking at phase one just a little bit closer, this is where we are. This is what we are working on today and what we're funding. Again, we've got the transmission schema. We're working with commercial providers. This work is taking place now, and we believe will be complete next year, end of this year, early next year, and we hope to have some sort of demonstration at our April trade show where we can talk about this as sort of another use case in addition to the RTK demo that was done at last year's show. And we believe there's precedent for this. Primary entry point stations, and for this, what I mean is government and broadcaster partnership. Primary entry point stations are part of the emergency alert system. Before that, the emergency broadcast system. These are stations that have additional hardening that's provided by government support so that these stations can stay on the air and fully operational, not just for the week or so that most stations have with their generator backups, but for really extended periods of time. And these are the stations where they receive, the presidential alert or the other emergency alerts, and that start the daisy chain of alerting for the entire country. So we believe there's precedent for this sort of, government and broadcasters working together, and that BPS would be another part of that. What we need help doing is really working on, phases 2 and 3. What we don't want to do is to pursue this in a broadcaster vacuum. We're broadcasters, we know what we're good at. What we don't necessarily know is what are all the use cases, what are all the requirements, be it accuracy or otherwise, that would be needed, and then how can we develop this such that it would be truly useful to the end user, because we want to develop it with the end user in mind. So at the DOT Roundtable, this was the first event that we attended back in August. One of the themes that we heard is that government support is needed if you really want a resilient system. And I would say that that is true for a BPS system. We need support to both help design it correctly and then also to operate it. So that's really what we're here to talk about is, where we are, how far we've come at this point, and what we think the next steps are. We want to be partner-oriented. In conclusion, I'll just reiterate that we think that BPS can be a valuable and cost-effective way to augment and complement GPS. And with that, I will say thank you, and we'll welcome any questions you may have.
Thank you very much. Tom?
You mentioned the antenna, and that was one of my first questions, is what kind of antenna does this require, and at what distance can you close the link for the purposes of navigation?
For the UHF frequencies, antennas right now is this big as a loop, but it could also, this system is designed to be signal to receive a cell phone. You have a small antenna by physics, you have like a -7 dB loss in there, but it works. So that.
And does it work beyond the range of where you could receive the TV signals?
Yes, it does. This is a highly configurable system, and the physical, on the physical layer, we call it physical layer pipes, and they have different FEC and different robustness built into it. For television signal, the coverage is defined by about 15 dB SNR, and then you get this. For data, you can make the data as robust so that they can be received at -5 dB SNR. So it takes a little bit of the resource, but you could change the robustness. Like, not all data bits are the same. Some of them are television, and these are the precious data bits.
Could you calibrate your two numbers? Could you calibrate your two numbers in terms of range from the typical power in a typical radio station?
I don't have the data, but television signals goes at like 50 miles or so. You could. Some of the towers are like 2,000.
So towers can be up to 2,000 feet and operated up to a megawatt. And just by example, I'm sorry I didn't have a picture of it, but the drone that we flew had a little stick antenna that was just next to the flat GPS antenna. So it was about that big.
And then, do you have to consider the equivalent of DOP? Because like here in LA, everything's on Mount Wilson. All the transmitters are there, so you're not going to really get good geometric diversity if you're navigating off of those.
Yeah, that was part of what Tariq was talking about when he said for those, I think it was 696 towers, we took out any tower that were within a kilometer of each other. We chose the tower with the best strength, but we eliminated the others that were within a kilometer of that tower for the exact reason you mentioned. And in addition to the VHF towers that were not included, there are also thousands of low power stations that are out there as well. Those were not considered in our modeling either.
Yeah, there are actually about 2,500 low power television stations, which we haven't considered. They usually fill the gaps. Right. And the standard also supports SFN. It's a distributed antenna system. So you have a big antenna, and some of the gaps you could have small antennas, and they will have their own TXID, and this thing could be transmitted from there with their own ID. So that's the way the coverage is designed.
Very innovative. The comment I would first of all make is that the way you're tying it all together in terms of navigation position, not time, in terms of position, it is very similar to what Loran has always historically done, except you have, there are no masters and slaves. They're all masters, I guess, at the end. But the other comment is relative timing, sure enough. But unless you somewhere have an external reference, you cannot get absolute time. And hence, there's a greater problem, a greater system problem across the whole United States, because each of these is sort of leapfrogging onto all the others. I assume you've thought about this. And it's a very interesting problem from the standpoint of synchronizing the time across all those stations and then tying in and saying, which reference do I really believe? Because each of them has so there's a maximum likelihood estimator that you must have built into it. But in terms of innovation, I find it fascinating. I do worry a little bit about the antenna size. And in terms of coverage, it isn't the number, it's how many are in view in all locations.
Yeah, that's a really valuable comment. And on the antenna, it's actually depends on use cases. If you want to use it to drive a vehicle, it's probably not a good use case because it's a terrestrial, we will not have that accuracy. But if you want to synchronize a signal on a power substation, yeah, you could put a 50-meter high antenna and you could have even a line of sight, no multipath. You could get a really highly accurate time.
I would just add that I think, these types of questions and these observations are exactly why we're so happy to be here. And it's the type of feedback that we want to make sure that as we pursue this, that we're coming up with something that is useful and relevant, and again, we're just not off in a broadcaster vacuum designing something that nobody actually needs or will use.
Dana?
Yes, sir. So a couple of years ago, we published a paper about a national timing architecture that addresses the kind of things that Brad's talking about. And it reinforces the case that this is really technology infrastructure upon which all other kinds of things can build, but until we have it, these kind of endeavors are going to be increasingly, I won't say problematic, but difficult, because there's no foundational piece that synchronizes and makes it standard and everybody has the same time. So, but yeah, great stuff. Thanks, guys.
All right.
Thank you very much. I just had one comment. It's a governance comment. Occurred to me based on feedback he said he appreciated from us. I would just ask all the subcommittee chairs and members to think about how you establish habitual relationships, refresh them, and then so every once in a while, we may not need an entire briefing. You may want to say, based on our continual contact with them, here's an update on where they're at on it, so we can form that. But if we can institutionalize those paths of communication and continue to refresh what we know, we're going to get a lot of value out of these committees. And I won't tell you which ones to do it with, but these folks are looking to keep talking to us. So I think we need to look at the people we're dealing with out there and see where the proper targets are at. So thank you very much.
Thank you.
Awesome. I'm Dr. Judith Olson. I'm a physicist at Cold Quanta. It's a small quantum technology company based out of Boulder, Colorado. So you can tell from the name and the title slide, we're very invested in next generation technology based on quantum physics and kind of the new tools that having...
Close it, Mike, thank you.
Yeah, sorry. And the technologies that the quantum properties of matter allow us to advance. Quantum is kind of a dirty word these days a little bit. There's been a lot of money that has been invested in quantum technology, and the payout hasn't necessarily been realized with all of those investments. So Cold Quanta is forming a structure around the near-term benefits we can get from quantum technology in the next few years, as opposed to entirely banking on, quantum computing that could take decades still to come to fruition. And then my talk today, while I will review some of our other quantum technologies, it generally will be focused on atomic clocks, which is a very different tack than most of the talks you guys have had today. It's a great, amazing room of people to be presenting this kind of content with. But rather than focusing on the actual applications and the satellite structures, things like that, I'll be focusing on the core at the basis of all of these PNT systems, which is the atomic clock. So quantum technologies for space PNT, you guys already use these, you have for decades. Atomic clocks are fundamentally quantum. They're probably the oldest quantum technology in existence. There's an economic market out there based around these clocks. People are well aware of their applications. So it's a really good space for a quantum company to initially address. But in addition to clocks, there are lots of other technologies that are nearer term for space PNT. A big one on here is the radio frequency sensors that we have. There's been a lot of talk of antennas, in particular on the receiver end here. You can use the quantum properties of these atoms to have the energy rather than the wavelength kind of be the coupling factor. And that allows you to have receivers that normally would be the size of a person or larger, be about the size of a quarter. So that's definitely a lower TRL technology, but that is going to be the commercialization push after the clock effort at Cold Quanta. In addition to RF receivers, inertial navigation is another area that quantum technology really excels at. You can beat the performance of a ring gyro. The big deal there is really trying to get it down to a size, form factor, and price that make it so it's a viable technology. And then there's quantum computing and emulation. Those are a little bit further off the distance, but quantum emulation is already here. So Cold Quanta actually listed, it was one of Time's 200 best inventions of 2022 that our quantum matter emulation platform was featured on. And that allows you to go through, rather than having to form your own lab, you can use a cloud-based service to test what your inertial sensor would perform like, or your clock, or whatever quantum system you have based on atoms and lasers would perform like. So, most of these are areas that Cold Quanta is actively researching, but there's also optical communications, receivers, and emitters that I think this group is very familiar with, and that's a huge area that quantum is also enhancing. So just in case you guys don't know how a clock works, generally clocks are defined by these quantized energy levels. So your atoms can be in discrete states, and if you poke them just right, if you kick them with the right amount of energy, they will change states. In the simplest form, you can pretend an atom is effectively 2 levels. So here's an example of cesium. You can pretend, it's F equals 3 to F equals 4, and if you send in radiation at exactly the right frequency, the atom will change states. Ultimately, this means that your atoms can tell you what that frequency of the radiation was that interacted with them. So a passive atomic clock effectively works like this, where you have some initial source, either a laser or an RF, a signal, something along those lines, and we call that the local oscillator. That then interacts with your atoms. This could be, ions, molecules, whatever atomic ensemble you have there. And it then interacts with them in a way that they change states. That state change can be detected. A lot of times this is fluorescence detection, but there are a whole host of different techniques you can use there. And then based on that detection, you can generate a clock correction that says, my local oscillator was a hertz too high in frequency, we'll move it back. And then the cycle repeats consistently. And that's effectively how a clock works. That's how you get the quantum information out of these atoms. And atoms are great for things like this because they're all fundamentally identical. It lets you scale your system, have nice signal-to-noise properties. And that's essentially how these clocks work. Of course, nothing is ever as easy as it seems when you first draw a 2-level diagram. So for example, this is kind of the clock transition structure you have to be worried about if you were designing a strontium optical lattice clock. So things get rapidly more complicated, but the complications aren't all bad things. In a lot of ways, they give us new tools, quantum tools that allow you to build better clocks. And from my perspective, that the future here really has to do with these optical atomic clocks and using optical transitions, whereas most of the clocks available today, all of the commercial clocks available today, are based on radio frequency level transitions in the atoms. Even if they're using lasers to incite those, the local oscillator itself is not in the optical regime. And so that's going to unlock a whole new level of performance here. This is something that has only come about the last 20 years or so, where it's really been a viable technology. We've known about optical clocks for longer, but actually using them is very difficult. So having advanced lasers and electro-optics has allowed these optical clocks to advance rapidly in the last few decades. And that includes narrow line width lasers and then lasers at all sorts of different colors, because if you're building a very complicated clock, sometimes you want 6 or 7 lasers in that system. So you need a lot of different colors and frequencies that aren't always available. And then the other big breakthrough that's allowed optical atomic clocks to progress recently are optical frequency combs. So this is a fairly new technology around the turn of the century that this came about. And those allow you to take these optical frequencies and convert them down to RF signals that can be used by electronics and at a fairly small package. That technology is rapidly advancing. It used to be you'd need a whole room full of electronics to down convert things from optical to RF. And it was entirely bespoke. You'd have to design a new one for each clock. Now we have frequency combs, and it's entirely changed the world of optical clocks and how useful they can be. So optical clocks, I keep saying they're the future. Hopefully this plot gives you an idea of why that is. So this is a plot from the NASA Cold Atoms and Space Workshop I participated in last year that they have published. And it shows here kind of where microwave performance has typically been and where microwave measurements are. And it kind of shows that, this is a limit of using microwave systems. If you're measuring against a microwave clock and that is your reference, you can't measure better than that clock is. But optical clocks at this point are far better than microwave counterparts. So we have clocks out there that can tell time better than time is even defined in terms of the SI second. Like cesium fountain clocks, while they're the workhorse of timescales out there, we're in this new paradigm where we're telling time better than time is defined, and that makes things very tricky, and you end up having to use frequency ratio measurements and other tricks instead. So not only is this plot clearly showing, but if you pay attention to the scaling here, this is a log plot. So each time you go down another bar here, you're not increasing by a factor of 2, you're increasing by a factor of 10. So these clocks aren't just a little bit better than microwave clocks now, they're orders of magnitude better. These clocks are telling time thousands and millions of times better than you could with some of the microwave counterparts out there. So why are optical clocks so good then? This comes down to timing uncertainty. Effectively, there are 2 factors you care about when you're trying to measure a frequency. Inverse of frequency is time. So the better you can measure your frequency, the better you can tell time. And that has to do with both the actual frequency at which the clock is ticking, so F here. So the larger that is, the less uncertain you are, the better your clock is. So by going to optical frequencies at hundreds of terahertz as opposed to microwave clocks at megahertz or gigahertz level, you're getting an immediate improvement factor. If you had 2 identical clocks and the only difference was the local oscillator for the clock, optical would win easily by many orders of magnitude. On top of that, optical clocks have a lot of extremely narrow transitions that are accessible. So while I'm talking about 1 hertz kind of level transitions here, the next generation of optical commercial clocks won't be quite that, looking to go quite that far. But it gives you an idea of where we can go with this technology because there's lots of these really narrow transitions. Having a narrow transition means, when you shine your laser or your RF source at your atoms, it tells you very, very clearly with a very steep discriminator exactly if your laser is a little bit too high or too low, and it makes those corrections a lot easier. And then the last point here is a little bit more practical. You can generally build smaller physics packages for optical clocks if you're not having to worry about having an RF resonator or a cavity. They tend to also have the potential to be lower power. I'm sure anybody who's familiar with these could call me out on a lot of exceptions to this statement here. But generally, it helps. It also means you don't need to rely on long Ramsey times. So you don't need to have free fall fountain clocks to get really good performance. And anytime you have a clock with free fall, it has dead time in the cycle. It's more susceptible to shock, vibration. You need better lasers and local oscillators to actually realize it. And then it takes up more space. So all of those things become less severe of a challenge when you're dealing with an optical system for the most part. So optical clocks, they're a big game changer. This plot here, it's a standard tool used by optical metrologists and people doing timekeeping where the vertical axis here is performance. Generally, on these plots, it's kind of counterintuitive. Being near the top is bad. Or not bad, but it's worse timing. Being low is better timing. And this kind of gives you a lay of the land right now with what's commercially available. So if you're just relying on GPS, you really don't have very good short-term performance here. It averages down over time. If you have lots of time to be looking at these signals and collecting information on them, you can get really good. But usually these systems are then augmented by other references. So CSACs, PRS-10s, things along those lines tend to be incorporated in the GPS receivers to give you some of that improvement at short time scales. On top of that, we have cesium beams. Those are the workhorse of timescales used, around the globe. And then a little bit below that, we have passive and active hydrogen masers. And those are, the best clocks you can buy on the markets these days. There is one part of this plot that is hard to quantify, and I have some plots later that try to better explain how this impacts the cost, size, weight, and power of these systems. But generally, the worse performance you have, you can make it smaller. It's easier. You don't have as much insulation. You don't need to worry about so many shifts and problems. And since many of the systems that are larger, they rely on length, they're using dead time, they're Ramsey-type clocks, it's hard to build a small system from them. So generally, all of these, you'll see a trend that appears where you can have small, portable, nice things. Down here is where it gets more difficult, and the cost goes up, the size, the weight, and the power draw all go up. And then here's where optical clocks are. State-of-the-art optical clocks are ridiculously better. So we're talking millions of times better performance than some of the typical oscillators that are used in crystal oscillators, things like that. They're so good that even if they were available today, no one would know what to do with them, and it'd be very, very hard to actually transfer the time. So this is more of there just to show where we could push with this optical clock technology and why it's worth doing. It's not the kind of thing we're targeting for initial products, though, for sure. So, there are a lot of problems getting optical clocks out of the lab. There's a reason this hasn't been done. There's a reason that you can't go out and buy one of these right now today. And it comes down to two general things. There's more than this, but these are the two I'll focus on here. The big one is transferring or actually using that optical clock signal. Yes, we have combs now, but you want to transfer through free space with turbulence. If you're caring about your frequencies at a few parts in 10 to the 16, that matters. And you can't do much better fundamentally because of turbulence with the tools we have now. There's a lot of new tools in development, though, and they're moving really fast. So new time transfer techniques based on optical frequency combs, understanding that there are other networks we can use instead, fiber networks, things like that. If you want this today, but the tech isn't quite there. There are ways around it. Generally, this means a lot of these clocks are restricted to local networks, and so that's a big issue. Europe does have a nice connected network now of clocks connecting multiple metrology institutes. The United States is contemplating similar things here, but generally those networks are smaller and hard to realize. So in addition to how do you actually use these, the clocks themselves are difficult. Environmental susceptibility is high. Atoms make good sensors, which means they're sensitive to things, which is not what you want when you're building a clock. The whole point of building a clock is to make them only sensitive to your laser and nothing else, which requires a lot of solid engineering. The other nice thing, though, is there's a lot of different options for optical clocks. There's a lot of different species, different ways you can interrogate them. And that means you can pick a clock that will be fundamentally less sensitive to these problems. And then, I didn't mention this in the last slide, but high-performance commercial clocks these days, they need environmental chambers to operate. If you buy a cesium or a maser, I worked for the timescale for a while, you can't just buy them and use them. You buy them, and then you buy a chamber to put them in, and then you buy more things to augment the chamber to make the chamber even better. And that's what you need to do if you want to actually reach the specifications. So these are the tenets we've kind of built into our atomic clock commercialization effort. And our goal is to really make clocks that don't need environmental chambers to operate, that are small, that aren't sensitive to the things we don't want them to be, that can have shock and vibe, can survive sounding rockets, can operate over large temperature ranges without needing augmentation. And then, because there's no way to really utilize this excellent optical clock stability from lattice clocks and things like that these days, we're not bothering to try. So we're going with something that is much more feasible in terms of what the actual market demand is. And it makes our job of designing them a lot easier then. So this is a plot from an awesome MITRE paper that came out a few years ago. And it shows kind of how the commercial clock space lines up. So the plot on the left here is the time deviation after 1 day. So this is kind of the holdover you might expect if GPS went down or something along those lines and you were using this clock for timekeeping, how would it perform? And you notice a general trend here where there's less time holdover for smaller clocks like CSACs and things like that. And as you get to these bigger, more expensive clocks, you can have better holdover. But this bottom axis is the size. So that's what you're giving up here. If you want an active hydrogen maser, if you want any of these systems really, you're looking at something that weighs more than 30, 40 pounds. The active hydrogen masers are larger than a mini fridge. They come up to your waist. They're not transportable. They're barely portable. Like we've been trying to order one for about a year now, and every single time it gets stuck in customs and has issues and has to get sent back to the factory because it breaks. And then a forklift hit it, and it has to go back to the factory again. And the fact that it's hard to even get them just shipped to you to use, I think says a lot about where that technology is in terms of trying to make it portable. So then this plot on the right over here is a very similar one, except the axis here is the power draw that it takes. So a lot of the applications, once you do get into portable clocks and transportable systems and you want mounted assured PNT, you need to have low power draw. And that can be a very challenging thing if you aren't designing your clock to have low power from the get-go. So Cold Quanta's Gen 1 clock that we're working on falls right here. It's nothing super crazy out of the ordinary. The thing we're trying to do at this point is get a big clock, or not a big clock, get a small clock out in the market and start showing people how good these optical clocks can be, show that they are reliable. The awesome thing about the approach we've picked, though, is that we can rapidly scale down the size of this. So this clock right now, we're aiming for about 25 liters for the first physics package, or the first whole system, not the physics package. And the Gen 2 version will be able to be about 1/10 the size, and the Gen 3 version will be 1/10 the size from there. So it goes from something that you'd have to carry around, it's heavy, it's not ideal, to something that you could, in theory, start fitting in a pocket, that you could put in a handheld device, and make sure that these are transportable. Power draw wise, we're not doing anything too crazy, but we are trying to make sure that it's reasonable. And generally, as we work on this push over here, it goes along with the reduced size. As you get a smaller clock, you don't have to spend as much power heating things or stabilizing some of the clock subsystems. So that's really where we're trying to push. Right now, this Gen 1 system is based on data we actually have. So at this point, we're only measuring against a passive hydrogen maser. Every time we measure our clock, we only read out passive hydrogen maser-like performance. We're trying to get another system in so we can actually measure this, or pack everything up, bring it to NIST to do a measurement campaign there. So the data's there. We have these systems. We've built a few of them now. And Cold Quanta closed its Series B VC funding round with $110 million. So a significant portion of that is going back into atomic clock development so that we can push on this and have these out. So 2024 is when we expect for these to be commercially available for that Gen 1 type system. That being said, we are still actively developing these. If you have applications or stringent requirements for these that you would like to give us feedback on to make sure we're designing the optimal product for the user base, please reach out and let us know. So, we're pushing and getting better performance. The clocks we're working on right now can do better than active masers. We haven't been able to measure it yet due to measurement limitations, but in theory, it performs better than an active maser. So why does anybody care? If you suddenly had something that could have the performance of an active maser or better, but could eventually fit in your pocket, you can start doing crazy new things with it. So there's a lot of ultra-low phase noise applications, synthetic aperture radar, new dynamics for optical communications, encryption security options. When you have the best clock out there and your adversaries can't purchase it, they can't do any of the things you can in terms of being able to divide down time and have frequency resolution. And then there's ultra-long holdover applications, so, assured PNT, GPS denied operation. Right now, the holdover for our clock, we're aiming for about 1 week before it reaches, equivalent to where a cesium would be after a week. We think that's a pretty easy goal. Generally, we want them to be even better. We'd like to have these things operating for a month. It's just that will take more development time. And then ultra-stable timing frequencies. So, if you have better timing ability, you can do location accuracy well beyond GPS. You can start setting up local networks that have centimeter or better accuracy. And that's really, really important. And it lets you do things like geodesy, and then gravimetry is definitely a future area we're pushing in. The clock we're designing now is not ideally suited for gravimetry, but optical lattice clocks, you can tell if they've moved a millimeter at this point. You can see the gravitational redshift. And that means that they're excellent sensors for both natural disaster concerns, and then, seeing tunneling, things like that, mining, all sorts of applications you don't even realize are there till people start saying, hey, this is on the horizon. Start thinking about what you would do with this tech if it was available in a few years from now. So just to kind of summarize here a little bit, our RF sensing capabilities, I think, are probably going to overshadow our clocks rather rapidly as we bring up the TRL on those. So we have our RF sensors. These are some images I was allowed to share. The sensor itself, they're about the size of a quarter. And this thing has tunable range. They can go through, I believe they're aiming for 40 gigahertz near their upper range, but it's flexible. They can go higher than that as well. So it can replace these very, very large, bulky antennas. They don't do sending signals out, but the receipt end, they're excellent at, and they can do that with improved sensitivity over existing mechanical antennas. And then inertial measurement, accelerometers, gyros, quantum computing, emulation. It's going to be really useful, not as a direct application, I think, but more for people who are concerned with advanced materials development. Trying to make the lightest, most robust satellite you can. It helps if you have the materials there to do that. And then our atomic clocks, that's my bread and butter. We're making environmentally ruggedized clocks that effectively are going to act like an active maser, but in a much smaller box and extremely rugged for the environment. So our contact information is over here. If you have any clock questions, please let me know. Max Perez, it leads up our R&D group with other general inquiries, and then I put our RF sensing guys' contact info there, since that tends to be an area of interest for audiences like this. Thank you guys very much.
Thank you. Comments, questions? Pat? I was going to say it was a very timely brief, but go ahead.
So it sounds like you're putting a fountain clock in a cigarette package.
Yeah. There's no fountain.
Okay.
That is something we're trying to get away from.
Can you comment on the mercury ion clock the JPL has put
Yeah,
up?
DSAC, it's amazing. So DSAC is great for a lot of reasons. A big one is that it doesn't use lasers. Lasers are still a barrier. And in terms of the lifetimes of these systems, right now, laser lifetimes, it's going to be hard to get a clock out there that you can have operate for more than 10 years. 10 years is kind of the golden rule there. JPL's clock then can operate for much longer than that because they don't have these laser systems. It's also, it's just better engineered. They've been working on that problem for a long time. And so it's the kind of thing where their goal is to have effectively infinite holdover. The clocks we're designing for right now are not quite geared for that application space. They could be designed, but I think if we were going for the longest holdover we could for deep space navigation, we'd really be focused on a different way of operating these clocks. What we're doing now gives us both short-term and decent holdover, but that type of application is looking for indefinite holdover.
That's great. Yeah, I guess you don't care if you lose a nanosecond between here and Mars.
Probably not. I mean, it depends on how fast you're going, but.
Tom?
You mentioned that, you can, these are better than time is actually determined now. I mean, does this mean that what's used for TAI or that technology is obsolete and it's going to have to be replaced with things like this?
I mean, that's more of a BIPM question. No matter what answer I give you, I'll ruffle feathers if any of those people are listening. I mean, I've been to the BIPM meetings and actually sat in on the discussions about the redefinition of the SI second. It's definitely a thing that is coming on the horizon. The biggest barrier I see to that is that these clocks are hard to build. You don't want to redefine the time scale for the globe on something where there's only 10 of these clocks in existence and they take 12 grad students to maintain. That's not a good thing to do. That will give you a secure time scale that the globe can rely on. So it's part of why we're pushing. We're building our first optical lattice clock starting next year, actually. It's definitely much further away from, being commercially available, and there's a lot to do to get there. But that's the kind of thing that needs to happen for this SI second to be redefined. You need to be able to buy these. You need to be able to disseminate them. Every metrology institute needs a few of them because, stuff goes wrong. You want backups. You want an ensemble.
Brad?
Yeah, that really nice presentation. Thank you so much. Historically, the GPSers have tended to look at 10 to the 5th second Allen variance times. I'd just like to point out that the nifty thing about what you showed us is on the phase noise side, the lower frequencies, you also are superb, and there are a lot of reasons that GPS, particularly in jam resistance and long averaging times, really want that low phase noise. And
Yes.
so I just reinforcing your market need message.
Appreciate it. Yeah, it's a way for you to more immediately tell that GPS is being spoofed or jammed. If you have a better clock, you know if that GPS signal is going somewhere it shouldn't. It will likely, once these clocks are commercially available, it will probably unleash new waves of spoofing and jamming that are even harder to detect and slower turn on of the mechanism to actually disrupt the GPS signals. And that's where you really need these clocks to both have the short-term performance and the long-term holdover. So we're trying to design them not just for the market need now, but where we see this market going over the next decade plus.
Thank you. Our last presentation, I'll end with an historical note. I was a Loran C commanding officer in Southeast Asia when Vietnam fell. We are trying to keep our Loran signals online until they evacuated everybody out of the American embassy, and you've seen the helicopters and everybody on the rooftops. Our last station was on Kon Son Island off the Mekong Delta. The last message they got was, Air America helicopter coming, evacuate with the 2 cesium beam standards. Thank you.
Thank you very much. Appreciate it.
Well, thank you for that. All right, so everyone here sitting at the table is volunteering their time, and their time is very, very valuable. And you are national and international experts, and so from NASA and the interagency, we truly appreciate your contributions. And so the least we can do is set up a little bit of a social activity. So those of you that are members, government representatives that have supported this group today, and presenters. You would have gotten an email from Leisha. If you have any questions, you can come to me. Also, I've spoken with a few of you one-on-one. But bottom line, our social activity begins at 6:30, and we'll take it from there. So if you have any other questions or need any other details, just come and talk with me. So we'll see you there. Thank you.
Dinner's informal, take your ties off.